Good morning, everyone, and welcome to the third annual workshop on climate and atmosphere research and innovation in the Eastern Mediterranean and Middle East region. My name is Eleni Zinaros. I'm a project officer at the Climate and Atmosphere Research Center of the Cyprus Institute. And on behalf of KRC and the EMME Partner Consortium, I would like to thank you for joining us today. We have an exciting program in store for you with over 50 presenters reporting on recent relevant advances in the climate and atmospheric sciences field. Throughout the workshop, you'll be able to submit your questions at the Q&A chat at the bottom right of your screen to be passed on to the presenter. Please also feel free to share about the workshop and social media using the hashtag EMME for climate and tagging EMME on all social media. We will add these tags in the chat for your reference. We should also remind you that this workshop is being recorded for monitoring and reporting purposes and for the promotion of future events. In terms of the structure for today, we'll shortly start with the opening remarks and continue with the presentations. But before I do, I should give out some rules on how it will go on. Firstly, just to let you know, the oral presentations will be 7 minutes long with 2 minutes question at the end. I will give you 1 minute warning when you're closer to the time to finish to make sure that we keep up with time. In terms of the VPICO presentations, there will be 2 minutes each with no questions at the end. And again, when you're closer to the time to finish, I will let you know to wrap up, as we have 58 speakers and we want to make sure that we keep up with time and everyone gets to present. Now, without further ado, I would like to pass the floor to the chair of the program committee, Professor Sharbel Afif, professor at the St. Joseph University in Lebanon, and adjunct professor at the Cyprus Institute for the workshop's opening remarks. Enjoy.
So thank you, Eleni. Good morning, ladies and gentlemen, and welcome to the third online workshop on climate and atmosphere research and innovation in the Eastern Mediterranean and the Middle East. So as you already know, this workshop will tackle different topics related to studies on air pollution sources and impacts, modeling, atmospheric dust, climate and weather extremes, and instrumentation. First, I would like to thank the members of the scientific committee from the scientific committee from the region and also different parts of the world for their contribution and preparation of today's workshop and topics. So normally you should be able to see the names of the scientific committee. And I would like also to thank the organizing committee for their support and efforts in making today's event. I'm happy and delighted to share that this year's workshop gathers more than or almost 300 participants from 47 different countries, while last year's workshop gathered participants from 41 countries. And so from year to year, we keep breaking records, and this means a lot for us. And for also the interest you have in this workshop and your commitment. And so we have participants from different regions of the world, as you can see. So
Sharbel, sorry to interrupt. We cannot see your slides at the moment. So if you would like to share your screen again.
Yes. So yeah. Okay. So
perfect. Now we can see them.
Now it's fine. Okay. Thank you. So. Again, so these are the names of the scientific committee, as I told you, so from the region, but also from different parts of the world. Thank you. But also we have the organizing committee that deployed a lot of effort, and I would like to thank them again and again. And so this year we have almost 300 registered participants from around 47 different countries. That's a bit more than what we had last year. And so from year to year, since this is the third one, we'll keep on breaking records, and that means a lot also to us and the interest that you have in our workshop. Of course, the participants are professors, researchers, scientists, students, project officers, and so on, coming from public but also private sectors. We have 58 presenters today from 19 different countries who will share with us their knowledge and experience. And I would like to thank them in advance for this day that I'm sure will be very fruitful. So without further delay, I would like to thank you all for attending this workshop. I would like also to remind you, as my colleague EMME already indicated, that this event will be recorded. So you will have the chance to go back again and listen and view the presentations again. So there will be a repository as usual, and we'll have also the previous workshops there. Okay, and so without further delay, let us declare this workshop open, and I wish you a successful workshop and a great day ahead. Thank you for your attendance and attention. Thank you. Back to you, Elena.
Okay, so our first, of course, chair is Charbel. Charbel, I don't know if you would like to introduce Sergey Osipov, or would you like me to introduce him? But happy to do so if you like me to.
Go ahead, please. Hi, Sergey.
Yeah, okay.
Good morning.
Good morning, Sergey. So, Sergey, so Dr. Sergey Osipov is from KAUST. He's working now in Saudi Arabia and King Abdullah University of Science and Technology. So he's our first invited speaker, and he's going to present to us today air quality projections in the Middle East. So from observations to model validation and impacts. Good morning, Sergey, and thanks for being here with us today. Thanks a lot, and we're looking forward for your presentation.
Good morning, scholars. And before I begin, I would like to thank the organizer to speak today and to share some of the research I've been doing. I've been focusing on the region since 2011, and in the last 5 years, I switched the gears and started focusing on atmospheric chemistry and air quality. What I want to talk today is about observations, models, observational coverage and models, what progress we had in the region, and to outline some of the trends that we see. As you know, the region was largely data poor until 2017, when the Max Planck Institute for Chemistry organized the first ship campaign. The ship sailed around Arabian Peninsula for 3 months, collecting the first unique measurements and characterizing the atmospheric chemistry in the region. Since then, we had the ARED campaign and TOFA in 2023, measuring the heavy ozone pollution in the Arabian Gulf and the Shamal winds effects. Thanks to the effort of National Center for Environmental Compliance, we have the 240 air quality stations in Saudi Arabia and 20 more from our colleagues in Abu Dhabi Environmental Agency, Abu Dhabi. So at this point, I'd like to acknowledge the hard work of all researchers and people who collected this data and were open-minded about international collaborations, because these observations are essentially the backbone of the research, and that made the progress possible. To give you an idea, this is what the ship campaigns look like. This is dozens of researchers operating 5 crates of equipment on the ship, sampling various conditions at sea, including ship traffic, urban and dust pollution, petrochemical industry, and pristine conditions in the remote seas. The list of parameters measured during the Aqaba was exceptionally extensive, measuring most of the atmospheric chemistry, the trace gases, photolysis rates, OH reactivity, but most importantly, there was a comprehensive aerosol measurements, including the size resolved, the size distribution, and then the speciation and composition of fine and coarse aerosols, which was possible due to mass spectrometer and the ion chromatography. In addition to that, there was optical measurements, which was a key factor in constraining the dust emissions, and a number of parameters relating to clouds. So with the first observational baseline in the Middle East, we had a big step forward in understanding the atmospheric chemistry. Most importantly, we know the size resolve composition of the aerosols and their origin, whether they're anthropogenic or natural. This is, for example, the PM1 composition from Aqaba campaign. That was the discovery after the Aqaba study that dust is not everything here. You can see that most of the PM1 is anthropogenic, ammonium sulfate, carbonaceous aerosols, and the dust contribution is infrequent. You can also see considerable amount of water, which means that natural dust interacts with the pollution and swells. We see the regional gradients. For example, notoriously known the ozone pollution in the Arabian Gulf region, which can be compared to the Saudi Arabia with median values of approximately 4 times larger, much higher PM pollution. Most importantly, the observational baseline finally allowed us to release the bottleneck and validate our models. I use WAR for regional downscaling. For the retrospective studies, I rely on the reanalysis products such as MERA2, which includes the aerosol and trace gases simulation. For the future projections, Andrea Potzer from Max Planck is providing invaluable support in running the EMME model that allows us to set up the boundary conditions for the future runs. And of course, the emission inventories are a big part of this work. This is just a list of different sources, and I'm using the Hermes developed by the Barcelona Supercomputing Center, which is essential for this work. Here, I'd like to give you a very brief overview of the model validation and summarize some of the conclusions that we've reached over the years. So this is, for example, the model observation comparison at 10 minutes resolution after the Aqaba campaign. What you see is that model is able to capture the observations across 2 or 3 orders of magnitudes. And if there is an underestimation, if there is a bias and underestimation, meaning that we are having a lower estimate of the effects. We are able to capture the optical properties, and not only that, but also the size of the aerosols. And here I listed some of the major challenges in the region. So the most, in general, the region is known for notoriously underestimating the anthropogenic emissions. We had some success resolving this using the satellites. For example, EMME HTOP was a significant way, was a successful way to recover approximately 15% of the missing emissions. TROP-EMME and is a good way to recover NOx. I think Anthony is going to present today on this. Especially ammonia emissions are underestimated by a factor of more than 10. Black carbon emissions needs to be carefully looked into, and we can resolve it by considering the non-speciated PM2.5 and the emissions. Let me just, I cannot talk about ozone chemistry and all other processes, but let me just explain what happened with the aerosols here. So during the Aqaba campaign, we measured the size distribution, and we can integrate the size distribution up to any size for the comparison purposes. So in this case, for example, PM1, 2.5, and PM10. Within these modes, mass spectrometer and ion chromatography gave us a speciation of ammonium sulfate, organics, black carbon. And for the coarse mode, we know how much dust there is. So altogether, during the model validation step, we realized that as soon as we can match the observations of the speciated components, we are not representing the dust aerosols properly. As you know, the dust, as soon as we put optical constraints and dust deposition constraints, the problem became evident. As you know, the emissions of dust are tuned to match the optical measurements, and putting anything into the accumulation mode was producing inconsistent results with concentrations and optical depth measured during the Aqaba campaign. So basically, in the previous conventional approach, dust in this mode was erroneously added to compensate for the missing emissions. And what I want to point out is these particles in this size range are especially optically active, and which led to the underestimation of the contribution of the giant particles, what's known as larger coarser particles. So what we do now is I model dust as a unimodal size distribution, and I want to highlight that there is an understanding that there is more particles in the coarse mode that contribute significantly to the shortwave and longwave forcing, and there should be much less particles in the fine mode. I think Professor Stenchikov today will give his presentation where he arrived to similar conclusions independently, and he will highlight how models with a cutoff at 10 microns are underestimating the impact of the dust on climate and radiative transfer. Once we have a reliable model, we can start asking questions. And this is an example of air pollution study. Here we calculated the air pollution exposure. This is population weighted PM2.5. As you can see, anthropogenic sources here are so profound that they rival the natural sources. PM2.5 concentrations are approximately equal. And this is a composition of the PM2.5 material. And what stands out is the dominant role the carbonaceous aerosol play in the speciation. Carbonation aerosols are the most toxic and compared to the others. The air pollution exposure can be translated into the mortality. In Middle East, on average, approximately 10% of excess mortality is attributable to air pollution. And what I want to highlight here that this is a number comparable to the impacts of the COVID-19. And COVID-19 is a short-term disease, and air quality is a long-term health risk. And I think there is disproportion in the acknowledgement of these two problems. Corresponding numbers, for example, in Europe and Germany are 3 and 4%, showing that how severe the air pollution situation in the Middle East is. We can provide the economic incentive for this problem using the approach of statistical value of life, and this translates into approximately 5% GDP loss annually due to the excess mortality. Now I want to talk a little bit about the trends that we see in the region and discuss how the air quality and climate impacts are relevant to each other. The idea is to explore the historical trends and to assess the theoretically and practically possible limits into the future, looking into the future. The red line here shows the Middle East and North Africa. It shows the index of emissions since 1970. As you can see, for some of the air pollutants, the growth was tremendously linear. NOx grew 10 times, SO2 grew 8 times. And in global perspective, we see that some of the developed countries are on the opposite trajectory, reducing their emissions. George Zitis today will talk about how the reduced emissions in Europe are causing accelerated warming in the Mediterranean region. We know that there is discussions of 0.7 degrees warming in China after almost 90% of the emissions were cut off. So on the right, I'm comparing this linear trend that we see in EDGAR with CAM's future scenarios. COE is the current legislation baseline scenario, and the green and the orange line is the maximum feasibility reduction, which is often referred to the green line, is a health scenario. This is the scenario where we have the technology to cut down the emissions, and the red line is the complete fossil phase out of fossil fuels, complete phase out of fossil fuels. Yeah, so in terms of PM1 as a proxy for the health impact, we see that in the Middle East, the contribution of dust is relatively minor, and the entire pollution is anthropogenic, with large fraction of carbonaceous aerosols. As we look into the future, we expect approximately 40% increase if the current trend continues. And again, this is largely carbonaceous aerosols, black carbon and secondary organic aerosols. In terms of possible scenarios, the health scenario can reduce pollution essentially by 50%, and we can get less than 5 if we get rid of all fossil fuels. If you look at the PM2.5, we see, what I want you to know is that PM1 sits around 15 micrograms per cubic meter, and PM2.5 is the same number plus the contribution of the dust particles. So as we go into larger sizes, the contribution of dust increases. Here I want to use PM2.5 as a proxy for the radiative forcing and to highlight that the climate projections in the future should account not only changes in the dust, but also changes in the anthropogenic emissions, as they contribute to the optical depths equally in the region. And at the moment, we see that the difference between linear trend and the maximum and the health scenario, if the region decides to clean up the atmosphere, can be almost 50%. And I think we should really take a closer look at the back carbon, because it represents a significant fraction. It has higher toxicities than other aerosols, and also it has a very low single scattering albedo. So meaning that compared to sulfate aerosols, for example, it has a much stronger potential for climate warming. In terms of the direct radiative forcing of aerosols, I want to highlight that the aerosols in the region produce the world's largest radiative forcing in the climatological sense. And so this is a net cooling that offsets some of the rapid climate change that we see in the region. And this represents approximately equal contribution from natural and anthropogenic sources. To put these results into perspective and to highlight the importance of this effect, we did the fully coupled ocean atmosphere study, where we looked at the effects of the aerosols on the Red Sea. And we know that this radiative cooling reduces the sea surface temperature in the Red Sea by 0.4 to 0.6 Celsius. In the summer, over the southern Red Sea, this number reaches 1 degree Celsius. And if we compare this to the warming happening in the region, we know that the region is a hotspot, warming 2-3 times faster. The region already crossed the 1.5 degree threshold. And so if the Middle East were to clean up today, we would see immediately 0.3 degrees warming on top of that. I think my main message here is that the air quality and climate challenges are not standalone problems. We have to develop the machinery to model their impacts accurately. And in this region, the problem is that we have to resolve the marginal seas. We have to account for the, for example, the Red Sea it has the world's largest, strongest sea breezes, bringing the air masses as far as 200-300 kilometers inland. And this puts a challenge in representing these relatively small models that demand higher resolution. And this is only direct radiative forcing. I'm not talking even about the indirect effects such as clouds and precipitation. I think this is exactly my 15 minutes. I'd like to leave with this slide, which shows the complexity of the atmospheric chemistry and intensity of the atmospheric chemistry in the region. Here you can see the dust aerosol in pink in the proximity to the Badeli Depression and Rub al Khali Desert. You can see that the northern part of the domain is affected by organics, and the long-range transport takes place towards the Arabian Gulf. You can see that sulfate is especially pronounced in the southern Red Sea and the Arabian Gulf. And as soon as the sun rises, the photochemistry kicks in, oxidizing the trace gases and producing the aerosols. All right, thank you so much for your attention, and I'm happy to take any questions.
Thank you, Dr. Ozikov, for this very interesting presentation. It's really important, in fact, to have the access to the data from the air quality monitoring network to be able to check the performance of the models and so on, because this is what was a bottleneck, in fact, in the past. So if you have any questions.
There is one question, Charbel. Can you see it? I can read it out if you would like me to.
Yes, please, because I can't see it.
Yeah, of course. So the question for you, Sergey, is from Panos. Do emission scenarios consider future volcanic eruptions, for example, in some random occurrence?
Yelene's line is breaking. I've heard the. Can you hear me?
Yes. Should I try to say, can you hear me okay now?
Yes, I can hear. The question was about the future scenarios if they consider the volcanic eruptions, right?
So do emission scenarios consider future volcanic eruptions, for example, in some random occurrence similar to the 20th century?
Yes, so these scenarios consider only the anthropogenic changes in how the the volcanic eruptions and, for example, dust as a natural components. The volcanic eruptions are not included in these studies.
Okay, so Panos, if you have any follow-up question, please do submit it. Sergey, I have a question. In fact, one of the big questions that maybe is recurring a little bit in the region. So what about the contribution and how did you take into account the oil and gas industry and the production, the exploration, and so on in the future, and how much does it contribute to the PM concentrations and so on?
Definitely, I mean, we can break it down into the individual sectors because we have the, I mean, we have all the emissions included. And for some of the species, we know what are the dominating contributions. For example, energy generation, petrochemical industry, and shipping are the major contributors to the black carbon, NOx, and SOx emissions. There is a, as I showed you, there are gradients. For example, we know there is much more VOCs and organic aerosols in the northern part of the domain. You saw in the animation that Rabich, one of the huge, largest petrochemical facilities, I think that's responsible for half of the emissions in the region in this part of the world, and another half comes from here. This is largely due to oil and gas industry. And then we see the influence from the Iran, from the Tigris-Euphrates region. Many of these emissions are missing in the emission inventories, and we see the signatures of formaldehyde, ROX, and the black carbon. So there is a understanding what are the leading sources, but yes, there is, to answer your question quantitatively exactly, we can further analysis would be required.
Okay, great. Thank you, Sergey, for your answer. Eleni, is there any other questions? Because for me, I can't see any other questions in the chat.
We cannot. We have one more question. What is the effect from the dust covering the Eastern Med area coming from the war zones with dangerous particles?
Oh, it's a tough question. There are several developments in the region that I mean needs to be included. For example, we know that there is NEOM region being actively built in the northern part of the Red Sea. It's a huge amount of earthworks, and it creates a local source of dust pollution. Yes, there is the dust coming from the war zones. This has to be quantified from the models, from the satellites, from the measurements. There are techniques that are being developed in KAUST to inverse the strengths of the sources and their allocation. And then, yes, the approach would be the same. We would have to calculate the exposure and translate it into the mortality. But I mean, this is as far as I can speculate on this topic.
Okay, so thank you, Sergey, for the presentation. Very interesting, especially what it can give in terms of development and answering questions in the region later on. So thanks a lot. And yeah, go ahead.
Yeah, I'd like to thank you for having me and to highlight the role that Cyprus Institute is playing in the region for the last several years. I think it's due to Cyprus pushing for international collaborations and organizing these the workshops such as this one makes a big difference in acknowledging the climate change and air quality problems. So thank you again for having me.
Thank you, Sergey. And so now we move to the oral presentations. And so now we will have Pantelis Georgiadis. So hope I pronounce the name well. So from the Cyprus Institute.
Yeah, can you hear me right?
Yeah, great.
Okay. Good morning,
Yeah.
everybody.
Okay, so yeah, if you can just have a full screen.
Yes.
Okay, great. Great. So please,
good morning, everybody. I'm an associate research scientist at Custos C at the Cyprus Institute. And today I'm going to talk to you about how we use machine learning to estimate the concentration of ultrafine particles on a global scale. To start with, let's very briefly talk about what are ultrafine particles, which are particulate matter in the atmosphere in the aerosol phase with an aerodynamic radius or a diameter of 100 nanometers or less. So because of their size and despite their size, they dominate in terms of numbers in the ambient air. And until a few years ago, we didn't realize how bad they were for our health. There's a very large growing concern regarding the health effects of ultrafine particles, since to their size are able to circumvent primary airway defenses and enter the systemic regulations, and also that they have a large ratio of surface area compared to their size. And there has been numerous papers in the past years linking them to cardiovascular, respiratory, central nervous system, diabetes, cancer effects. So as you realize, it's becoming a real problem now. Their main source is combustion, either from industrial emissions, vehicles, or forest fires, especially from diesel engines. Since due to their size, these particles are able to pass through all the filters we use to cut large ones. So why use AI to estimate their concentrations? Because there's a limited amount of ground stations worldwide that actually measure them. There's haven't been many standardized methods of monitoring the concentration of such particles, and we need very high resolution maps in order to do epidemiological studies and come up with policies on to limit their effects. There have been a few computational methods being employed to produce those data sets. And here you can see a very recent 10-kilometer data set produced by our colleagues in the Max Planck Institute for Chemistry, which are also involved in this project. In order to train the models I'm going to present, we used every single ground station we could find in the past 22 years on the planet that either measures particle size distributions or particle number concentrations. For the particle number concentrations, the assumption is that because they dominate in size, they correlate very well to the total number of particles being measured. As a feature set, we used the 1 kilometer nitrogen dioxide yearly average data set. It was published in Lancet Planetary Health. 100-meter land use data set, the global population data, and also because the only creature on planet Earth that likes to burn stuff is humans, we use a lot of anthropogenic data sets was like the built-up volume, degree of urbanization, and human settlement. The target grid resolution for this model is to produce a 1 kilometer global map of ultrafine particle concentration. I trained 2 models, a random forest regressor and an XGBoost regressor. As you can see, they both perform similarly. Mean absolute error and root mean square are very similar. So we actually went with random forest because in the lower end, in the XGBoost, there's a slight overestimation of lower end concentration, whereas in the random forest, it performs slightly better. First place we used this model to predict the concentration of Cyprus because we know the topography population. You can very clearly see that the model identifies the cities, the highways, lower concentrations up in the mountain. So that was a thumbs up that, okay, we have something correct here. Then we compared it to the other state of the art at the moment, the 10-kilometer dataset from Marias Cole and Andrea Botzer. And again, you can see even though there's completely different methods, this is a mathematical model, this is machine learning from data. The concentration of ultrafine particles agrees very well, especially in India and China, which are major polluters. And then we went on to actually do the global maps. Here you can see India, you can see the major cities, but also the nice thing is that you can also see the intra-city concentration. So it's just at a blob, you can actually see the variation within cities.
1 minute left.
Okay, again, in China, you can identify the major cities, a road network. And here we can see the first global map at 1 kilometer of UFPs. In South Africa, you can see cities, a road network. And in Europe, Paris, London, Barcelona, Marseille here are very clearly seen. And in the USA, a nice thing that even if we have high concentration areas, you can still see the road network in there, which is a known emitter of ultrafine particles due to the combustion of the engines. And that was it. Thank you to Professor Jos Lelivert and Matthias Kohl from Max Planck, Theo from KRC, and Michalis Nicolau and Konstantin Dovrolis from Castor C, which are the collaborators in the project. And thank you. If you have any questions, please let me know.
So thank you, Pantelis, for the presentation. Very interesting indeed. So do we have, please post your questions so that, okay, so we have one question for now. So I will read you the question. What are the key parameters that affect the ultrafine particle concentrations and the size distributions based on the ML results you have?
We also did some feature importance analysis from the algorithms that I didn't have too much time to show, and the most important features that came up was degree of urbanization, the built-up volume, and the nitrogen dioxide input, which makes sense because people emit a lot of emissions, usually by burning things, and that produces a lot of ultrafine particles.
Okay, thank you. I have a question regarding, now that so the air quality directive, the European air quality directive, is being revised now, and
yes.
So practically it's being asked to add ultrafine particles also in the parameters. So how will this affect? What will it bring more than just checking the performance? How can the things be like complementary?
So with this, okay, this is still a work in progress, so I can't say it's 100% accurate, but when we can actually see where the highest concentrations of ultraviolet particles are within the cities, we can take measures to reduce them. Like there's now major cities that put traffic limitations to polluting cars, green centers. So if we actually know where the highest concentrations are, we can take measures to reduce them and probably reduce the health effects of them as well.
Okay, and so so you have any special, let's say, requirements for to get the UFP concentrations? Do you need to have a specific size distribution or not, or OPC is fine or not? So what is the best measurement technique for you to be able to compare with your work?
I'm not very familiar with the instruments that people actually use them, but I know we excluded a lot of stations that either didn't measure regularly or they had erroneous and very noisy measurements. Optical measurements are usually very sensitive to coagulation, so there's a lot of subtleties you need to do to actually the criteria to include the data in the dataset.
Okay. Okay, great. So thank you, Pantelis, for
Thank you very much.
your presentation. And so now we move to Professor Mohammed Yassin, Mohammed Fathi Yassin. So he's from the Kuwait Institute for Scientific Research from Qusr in Kuwait. Hello, Dr. Yassin. And so we're really excited to have some research from Kuwait. So the floor is yours. Dr. Yassin, do you hear me? Okay. Okay, go ahead if you can begin, but I can't hear you. I can't hear you. Maybe if you want, we can move to the next, we can switch and move to the next presentation and then come back to Professor Yassin if Calliope is ready. So we go to Calliope maybe first and then come back to Dr. Yassin.
Good morning. Could you hear me?
Good morning. Yes, we can hear you.
Yeah, I'm ready.
Okay, great. So maybe we can move to your presentation on submicron organic aerosols, and then we come back to Professor Yassin just after your presentation. Okay, great.
Okay, it's in full mode. The screen is in full mode. It's okay now?
Yes. Yeah. It's in presentation mode.
Okay.
It's fine. Yes. Thank you.
Okay. Hello, everyone. My name is Calliope Trinoli. I am a PhD student in the APCG team of the National Observatory of Athens. Today, I'm really happy to present you on the third annual online scientific workshop, our study based on long-term source apportionment of submicron aerosol at the urban environment of Athens in Greece. The importance of this work lies in the fact that air pollution is one of the current and the biggest current and future environmental threats to human health and climate change. Exposure to submicron particulate matter is known to have severe impacts to the respiratory system and is recognized as a leading cause of premature mortality in Europe. As particulate matter is a complex mixture of chemical species originated from a variety of sources, both anthropogenic and natural, we analyzed the chemical composition of fine aerosol in Athens to determine their levels, seasonality, diurnal patterns, their associated sources, and mixing processes in the atmosphere. Let's start with the best part of our work. All the measurements were conducted, sorry. Okay, it's okay now. All the measurements were conducted in this amazing place, close to Acropolis, with a view of Parthenon. In our study, there is the physio monitoring site. In our study, 5 years measurements from July 2016 until August 2021 were conducted in physio super site and include chemical composition and mass loadings by an aerosol chemical speciation monitor. The chemical composition are for non-refractory constituents of submicron ambient aerosols by an aerosol chemical speciation monitor with time resolution 30 minutes. Parallel measurements from a dual spot 7 wavelength allometer were performed and equivalent black carbon providing a solid and liquid fuel as wood burning and fossil fuel component respectively hereafter. And finally, measurements for PM2.5 from filter samples, low and high volume as well. In this picture, we can see a full, in this slide, we can see a full picture of the evolution of PM1 during the study period in Athens. According to monthly average concentrations and the pie charts of their contributions, we can see that organic matter contributed the largest fraction to submicron particulate matter, almost 60% on an annual basis. And the highest concentration occurring during winter due to increased emissions from residential wood burning. And secondary maxima, also in summer, suggest long-range transported pollution and secondary formation processes. Nitrate and chloride exhibited a clear seasonal cycle with maximum values during winter and minimum values during summer. On the other hand, sulfate and ammonium exhibited a reverse trend as a result of enhanced photochemistry in summer. Now, based on the monthly variability.
Hello?
Sorry? Sorry? There is another opened microphone, I think. Based on the monthly variability of particulate matter PM1 of our study period, in which 2 lockdown periods were included in, we have to emphasize that during the first lockdown, the levels for all the PM1 were lower, except organic matter, but during the second lockdown period, the concentration of all PM1 were significantly lower compared to their corresponding concentrations during the previous years. Given that organic matter comprises significant fractions to fine aerosols, monitoring their levels and identifying their sources is a key component for developing further emission reduction strategies. The source apportionment was conducted via positive matrix factorization using the SOFI Pro toolkit and implementing the multilinear engine solver. And the source apportionment analysis identified 5 components for the cold period, namely hydrocarbon-like organic aerosol, biomass burning-like organic aerosol, cooking-like organic aerosol, less and more oxidized oxygenated organic aerosol as well. And 4 components during the warm period, namely HOA, COA, LO, and MO, OOA. We can see that HOA follows a more complex weekly dial pattern with morning peaks due to traffic rush hour and evening peaks. Its pattern is similar to BC liquid fuel except that evening peaks of HOA occur later than VC liquid fuel. Biomass burning organic aerosol diurnal cycles display a well-marked patterns with high nighttime maxima due to residential wood burning emissions during winter. And the same pattern follows BC solid fuel, except the small morning peaks. The variations in less oxidized oxygenated organic aerosol display higher concentrations during nighttime, with relatively association with nitrate variations, apart indicating nighttime chemistry, apart from the morning nitrate peaks due to traffic. And more oxidized oxygenated organic aerosol dial patterns present a weaker variability and a weak correlation with sulfate for the entire period, indicating their different source origins to some extent.
1 minute left.
Okay, the diurnal variations of the identified organic aerosol components are presented in these figures for cold and warm period respectively. In cold period, all organic aerosol components present higher concentrations during nighttime, also favored by the shallow mixing layer height, while the HOA morning peak is also pronounced. A characteristic is the evening peak in HOA, directly affected by the charred rolling emissions from grill houses and restaurants in Athens. In the warm period, the diurnal variability and the diurnal cycles weaken as a result of dispersion of pollutants under a higher mixing layer height and more regional contribution to organic aerosol. In the second figures, a mass fraction of each organic aerosol component is presented to help us to understand how the organic aerosol composition changes under different loadings. For this purpose, our dataset was divided into 10 bins, containing the same number of points based on organic aerosol mass concentration. So the fraction of BBOA and low OA components increase significantly with increasing fine PM in winter, while more oxidized oxygenated organic aerosol drops drastically, indicating the large effect of residential wood burning in the turbid winter conditions in Athens. In summer, the variability is limited, indicating more homogeneous atmospheric conditions. Now, on monthly basis, all organic aerosol components maximize during winter months due to increased for domestic heating and favorable meteorological conditions of low mixing layer height, while more oxidized oxygenated organic aerosol exhibited the less monthly variability with increased concentration in summer, signaling secondary organic aerosol formations due to increased photochemical reactions in the Mediterranean. The percentage of the main organic aerosols are presented in the next tables. Sorry, I have to change the slides. Something to keep it in mind for this from this presentation. This work provides a comprehensive overview of the organic aerosol sources in Athens with highly resolved source apportionment results. Sorry. Okay. During winter, primary organic aerosol contributes almost 50% of the total organic fraction. In contrast, in the summer, which only contributes 25%, and the rest is linked to SOA, respectively, secondary organic aerosol, respectively. Increased organic aerosol concentration in Athens due to residential wood burning and the sulfate maximized in summer due to photochemical reactions. And last but not least, biomass burning and less oxidized oxygenated organic aerosols were strongly associated with domestic heating, while more oxidized oxygenated organic aerosol with regional organic aerosols in the Mediterranean. Thank you, and sorry for running out of time.
So thank you for your.
Sorry, I had small problems with the microphone. One microphone was opened, and I have a simple problem. Okay.
No problem. So, so we have a question from Dr. Chan. So, saying that your results seem to suggest, your diurnal results seem to suggest that photochemical SOA formation is not important. Is there any reason for that?
The sulfate photochemical reactions. Sorry, could you repeat, please?
Yes.
The sulfate photochemical, is not important.
No. So the question is, the diurnal results seem to suggest that photochemical secondary organic aerosol formation, SOA, is not important. Is there any reason for that?
I don't think that the results show something like that, because in which graph, specifically, in this, maybe.
In general, so the formation of secondary organic aerosol.
There are results for secondary organic aerosol, and in this slide, I think that I told that signaling secondary organic aerosol formation due to increased photochemical reaction is more important in summer in the Mediterranean. But I didn't tell that it's not important.
Okay. Okay, great. So thank you for the presentation. And now we can switch back to Professor Yassin, Ahmad Yassin from PISR. Hope, okay, we just need to check for the sound. Dr. Yassin, if you can just try to.
Yes, you listen me?
Yes. We just need to have your
Give me. Can you share my screen?
Yes, I see your screen, but we need to have it in presentation mode. Yes.
Now, okay.
Yeah, if you can just change the display settings. Up on the left, up on your left.
Up in the left? Yes.
On your left, yes, here. No, the second one, display settings.
Yes, this?
Yes, and put it.
Multi?
Duplicate. Yes, this one. Duplicate slideshow.
Okay.
Okay, great.
Now, okay?
Yes.
Okay.
Yes, great.
Okay.
Thank you.
Okay.
The floor is
Okay. Thank you, Dr. Sharp, for inviting me to submit part from our project. This project is not completed now, is the first stage. So thank you very much for giving me this chance. So today I will submit part from this project. The title, Impact of the Construction, Revised and Conventional Asphalt Roads in Air Quality Study Case, here a pilot study in Kuwait. My agenda today in this study overview for the study, objectives of the study, methodology and result and discussion, and last conclusion. Overview for the study. As we know, air quality as the critical factor in the well-being for urban population and the overall health in the environmental. So we know that outdoor air pollution is the fourth causes for this worldwide lying around about 4.2 million deaths per year. The quality of the air we breathe is the interactive linked to construction and maintenance of road infrastructure. As the global population continues to urbanize, the demanded efficiency durable roads network has never been greater. However, the conventional material and practice used in construction, practically the production and installation of the conventional asphalt roads, have raised concern about their environmental impact. Around 40% of urban area are covered by asphalt pavement fraction that keeps increase the urbanization. Rubberized asphalt, incorporated recycled and material typically discrete tires into asphalt mix. Therefore, this study presents a pilot study that examines the impact of construction of rubberized and conventional asphalt roads on air quality. This in unique urban area of Kuwait. While the environmental challenge associated with asphalt roads global concern in Kuwait here with the extreme climate and hot and arid hot conditions provide integrating seating of the infrastructure. This study explores the potential benefits of about rubberized asphalt in region where air quality and climate resilience are prominent. Our objective of this study is to assess the air quality implication of rubberized asphalt compared to the conventional asphalt routes in Kuwait, offering foundation understanding of the environmental benefit of the alternative construction material. Thus, we aim to provide empirical data on empirical construction materials on air quality and term of the health and well-being of residents in area. So our methodology first for this, just I will give brief for the description for the site. We will put our mobile lab in the second road here in Kuwait. This road is heavy crowded by car, but when we start our experimental is no car at this time. So we put here our mobile lab, and we take about 2 months for construction for conventional asphalt, and 2 months for rubberized for asphalt. And this is our mobile lab here, belong to our institute, Kuwait Institute for Research Science. So at this time, we monitoring about 6 or 7 pollutant, NOx and NO and NO2 and SO2 and ozone and H2S and CO2. And in future, we're going to monitor. In future, not now. In future, we will going to VOC, volatile hydrocarbon. So now we detect about 7 pollutant. And about meteorological data, as we know, at this time, during our experimental, the wind direction coming from northwest, making about 45% of all hourly wind direction in this direction. The maximum speed during our monitoring about 16.6 meter per second, and the minimum about 1.5 meter per second. And temperature is very important for us in Kuwait here, as we know the temperature varied significant in Kuwait due to the thermal stability. The temperature wind during our experimental change from 11.6 and to 2.5 centigrade. And for the result here, I will submit a few results about for the ozone. Before submit my result, we comparison the result with the Kuwait ambient air quality standard here in Kuwait. For ozone, we can see this figure, the upper figure, the result during the rubberized asphalt. The low figure, this is belongs the conventional asphalt. So we can see here the concentration of ozone is big during construction. During the rubberized asphalt is about 63.2, 91.87 part per billion. But all results for ozone under low the Kuwait ambient air quality standard. Kuwait ambient air quality standard for ozone about 70 part per million, and this figure indicate for NO and NO2 and NOx, and we can see also upper figure for rubberized asphalt, and down figure, this is for conventional asphalt. We can see here the maximum pollutant here is belong to NO2, and about is 47.2 to 164.53 part per million, and all the concentration for NO2 also is found below Kiba EBA. And for this figure, this is for CO. It's the maximum can see here during the also rubberized asphalt. Also, the result is belong to Kiba ABA. And the last result here, I will submit about SO2. SO2, you can see here also all the result we get under below quit ABA. So the maximum for SO2 about 46 to 27 part per million. And for my conclusion today is just a reduction concentration in air pollutant here during our construction. The data monitoring obtained during construction for the rubberized asphalt demonstrated the emission of pollutant from road surface were considerably lower than those for conventional asphalt. Using recycled rubbles in the asphalt mixture is believed to be the main for rubberizing the main contributing factor to reduce the emission. The study also found the concentration level in these pollutants all below in the quit ABA ambient air quality. So this is as a brief. I talk very fast because I don't have time. So thank you for your attention. Thank you. So I am ready to answer any questions.
Thank you, Dr. Yassin. So I have a question for you. Do you plan to have measurements, for example, for PAHs, polycyclic aromatic hydrocarbons, and then some assessment on health, as health impacts and so on later on from
yes. Yes. This is the first stage we're going to assess the VOC, but we will use our here we will use the canister, and also we have total hydrocarbon in our mobile lab. So during assess the VOC will calculate depended the empirical equation for ABA for health assessment equation for cancer and non-cancer.
Okay. Okay, great. Thank you, Doctor, for the interesting presentation. Now we can pass to Alkistis from Cyprus Institute. So Alkistis Papetta that will be presenting about the remote sensing observations. So Alkistis, the floor is yours.
Hello everyone, hope you can see my screen. So my name is Alkistis. I'm a PhD candidate at the Cyprus Institute, and today I'm presenting about the remote sensing observations that we obtained during our READ campaign. That was a ship campaign in the Mediterranean and Middle East. So I would like to start with the motivation and campaign objectives. As you might all know, the EMME region is considered as a climate change hotspot and is often affected by this effect. And it often experiences poor air quality that is affecting the people living there. In order to address this, we embarked the ARID campaign that was atmospheric research expedition to Abu Dhabi. And it was a campaign that started from Vigo in Spain and traveled all the way to Abu Dhabi within the period of 25th of November until 20th of December. This campaign was as complementary to the winter Aqaba that was previously introduced also by Sergey. And the main objectives of the campaign was to provide in the otherwise limited observation data in this region, and also to study greenhouse gases and aerosol optical properties and their chemical composition in this area. On the right, you can see the route of this ship and a picture of the research vessel that traveled in this route. As part of the instrumentation that was quite comprehensive, that we had reactive and greenhouse gases sensors and aerosol optical properties, physical properties, chemical properties. Can you please mute?
يا باشمهندس اي استفسارات؟
Or can someone mute this person? I don't know how it works. Okay, maybe I can proceed now. So as part of this instrumentation, we also had remote sensing observations with the main aim to provide boundary layer height and height result information. Among these instruments was the Vaisala oscillometer that was providing aerosol backscatter, boundary layer height, and cloud height, and as well as EMME sun photometer modified for marine applications and was able to measure multi-wavelength solar irradiances, aerosol optical depth, and angstrom exponent. On the right, you can see some photos of the installation on the sheet. And with this, I would like to start by giving you an overview of the sun photometer observations. So here we have on the left the aerosol optical depth, and on the right the angstrom exponent. On the lower plots you can see the time series of these two parameters, and on the upper plots the map giving the magnitude of the two parameters. Focusing first on the aerosol optical depth, you can find some increase of the aerosol optical depth after the Suez Canal. And this shows higher presence of aerosols after this leg of the campaign. Whilst on the right, the angstrom exponent seems to remain around 1. So that means that the increase of the aerosol optical depth was mainly due to fine particles like urban pollution or due to industrial activity in the area. With this, I would like to continue to the overview of the oscillometer observations, where on the top we have the height result time series of the backscatter as it was measured by the oscillometer, where the color indicates the greener or the red, the more red color behind there is due to higher backscatter, where the red dots show the derived boundary layer height. On the lower plot, you can see how the boundary layer height was varying throughout the campaign. And what we see by just a visual inspection of this plot is, again, a change of regime after Suez Canal, where we can see a higher backscatter from aerosols and more elevated layers after Suez Canal. And it's a similar behavior as the one that we see from the sun photometer. Only that now we also have the information of the vertical distribution.
1 minute left.
Yes, I would like to show how this backscatter was varying in the different areas of the campaign. So starting from the Mediterranean, these two cases show lower backscatter within the boundary layer, and that particles were mainly remaining within this layer. Proceeding now to Suez Canal and Red Sea, you can clearly see how the backscatter within the boundary layer increases with this greener color, and that we most of the time had concentrations of aerosol in also elevated layers. In the last leg of the campaign, where was the Arabian Gulf, we've also observed high backscatter in both the boundary layer and elevated layers. So to understand the origin of the particles, we ran a back trajectory analysis for the cases that I showed before. And what I've seen is that in the first part of the campaign in the Mediterranean, the presence of particles was mainly due to long transport of aerosols, whereas in the last part of the campaign, after the Suez Canal, particles were originating mainly from local sources. So this brings me to my summary. So during our campaign, we've obtained a comprehensive data set with observations of greenhouse gases and aerosols over the Mediterranean and the EMME region. And what I've shown here, these are just preliminary results that show high aerosol concentrations within the boundary layer after Suez Canal. My next step of this analysis is to go into more detailed exploration of the data and combine different sources of data. As we can see on the right, for example, we had also in situ PM measurements. And I would like to proceed with retrieving aerosol physical parameters from the collocated samplometer oscillometer observations and do an integrated analysis again with the various sensors that we had on board. As the last part of this, I would like to apply different boundary layer retrieval algorithms, and the examples are seen here. With this, I would like to thank you for listening to this presentation, and also I would like to thank the people that were on board the ship during the campaign, and also the people that helped in realizing this campaign. So thank you.
Thank you, Alkistis, so for the presentation and for the preliminary results you have. I have a question for you. Did you have any observation, let's say obvious observation on the impact of oil and gas platforms when you were when the ship passed next to them and so on, or no, not really? Did you have like a signature from them? Or
there are some indications, but I would need to go into more, let's say, in higher resolution data, because for now I was just exploring the hourly data. And even on this, we can see some impact. So as I showed, after Suez Canal, we already see finer particles, indication of finer particles, because this is a preliminary analysis.
Okay, great. So thank you, Alkistis, for the presentation and promising results. Now we'll pass to Eva. Who will talk to us about the emission inventory for Cyprus. So Eva Eriksson from the Cyprus Institute. Great, so you just need to...
Good morning, everybody. Can you hear me now?
Yes, we hear
okay.
You.
Can you also see my screen?
Yes, but not in presentation mode.
Just a second.
We see the full PowerPoint software. Okay, great.
And now?
Yes, great. Thank you.
Okay. So thank you very much for giving me this opportunity to be with you this morning. My name is Eva Eriksson, and I'm working at Aria Technology, which is a private French company. And we're specialized in air quality management and modeling, and we're also working with emission inventory work because this is very much related also to air quality modeling. And in this presentation, I will show you what we did together with the Cyprus Institute in putting together an emission modeling chain. It was within the EMME Care Boost project #1, which was financed by European Union, where we established and monitor regional pollution emission inventory, which is focused on the East Mediterranean and Middle East area. So the situation when we started in this project was that at Cyprus Institute, what they're working with air quality modeling, they have used an emission inventory. Sorry, I just have to move a little bit my windows here so I can see my screen myself. So they have worked with emission inventory that comes from the Labor of Inspection, which is the national entity in charge of emission inventory in Cyprus. They had the problem was for the Cyprus team that for air quality modeling, the emission inventory, which was in gridded version, which is necessary for air quality modeling, this is quite old. It was from the year 2015. And there was no information on activity data that could be used or emission factors in order to update this emission inventory to a more recent year. So every year, this gridded emission inventory was getting older and older. And there was the question, how could we update the emission inventory for air quality modeling? So we were working on different hypotheses, but we found that the best information to use was still the emission inventory that was prepared by labor inspection, because they do prepare a yearly update of this inventory, but not in gridded format. So the challenge of the BROS project was how to obtain an emission inventory which was disaggregated in time and in space, so that it could also be used on a yearly basis for air quality modeling. For this, we used different tools, and there was a big phase, of course, of collecting different type of data in the beginning of the project. So there was the emission data from the labor of inspection, which needed some complementary information. So there's a lot of GIS data also, cartography and thematic maps that can be used as proxies for distributing emissions, and the definition of time modulations for the inventory. And then we used GIS tools for preparation and visualization of data. And finally, we put in place a tool which is called Emission Manager tool, which does the disaggregation of emissions and put it into a gridded format, which is also modulated in time, which is what we call the model-ready emission data. So we started from total emissions, which were declared in the Cyprus National Informatory Inventory. And we also had a bottom-up inventory for large point sources in Cyprus, including also the thermodynamical parameters, such as height, diameter, speed, temperature, for speed and temperature for the gas, exhaust gas, and the height and diameter of the stacks. And then we deduced the large point sources, these emissions, from the total emissions in order to avoid double counting. And for the remaining emissions, after reducing large point source emissions, we used available GIS data, which were collected from different sources. Some of them were already available at the Cyprus Institute. In some cases, we used Core Land Cover or national GIS databases. Another problem was what to do with the northern part of Cyprus, where we had no information. And here we also worked with trying to identify at least the main sources, which were power plants and road traffic that were integrated. And after adding this part, we did the time modulation. Here we had difficulties finding local information on time modulation, so most of it was prepared with Edgar time modulation files. Okay, so we prepared, we ran after area emission manager module for obtaining gridded speciated files in netCDF format. A tool called Area City Everywhere was also used in order to get the information on traffic, because there was no information on traffic counting in Cyprus. So we used the Area City Everywhere tool, which extracts road net from OpenStreetMap and analyzes the characteristics on the different roads in terms of lanes, speed limits, etc., and builds a random forest model and estimates traffic flow, and thereafter runs a traffic emission model to get the emissions and the fuel consumption with the traffic model. So with this tool, we did obtain the emissions in a disaggregated way on the different roads in Cyprus, and we also added the northern part here with the Area City Everywhere tool. So you can see in the bottom figure here, we have added the northern part, and this was used finally for the spatial disaggregation, because we wanted to use the total emissions reported by the labor of inspection in Cyprus and the area city everywhere tool was used for the spatial disaggregation of these emissions. So with the emission manager, we did the different steps in processing the gridded file necessary for air quality modeling, which did the speciation of VOC and PM emissions, specialized and graded file format creation, also the selection of the pollutants that we wanted to use for air quality modeling, the time modulation, and the merging of the final different point area and line sources to get the total inventory, which is in the files we put together in this project, resolution of about 1 kilometer, so 0.01 grid resolution. So here we can see an extract from the output. This is for PM25 for year 2019 for the Cyprus inventory. So this was this is the first spatial and temporal disaggregation of the national inventory data, which was carried out, and a large part of this was to find the step-by-step the different procedures for the Cyprus Institute team to put in place in order to start from existing inventory data and obtain model-ready air quality files, emission files. And we did also end the project with the recommendations for future work, because this was the first step where we also could identify different possibilities of improvements. So we suggest try to consolidate the collaboration with labor inspection to try to extend the level of detail for the spatial and temporal disaggregation by also collecting information on time modulation, on stack dimensions, where for more sources than was included in this first inventory, and as well as to collect the GIS data from the national entities. There's also ongoing projects with traffic counting data, which could easily be added when used with the traffic model when they become available. And there is a new project starting up also for the northern part of Cyprus, which could be interested in order to add more information on the northern part of Cyprus for the emission inventory. And we're also waiting for the comparisons with dispersion modeling using this inventory that we prepared with the BOS Project 1 to see in comparison with the other existing inventories what and trying in scenario mode what kind of results this would give, if this how much and how it improves, or if we need to complete it in order to get a better consistency with the existing emission inventory. So I hope I didn't use up too much time. Please let me know if you have any questions.
So thank you, Eva. So from Area Technologies of the Cyprus Institute, I have a small question for you. What about the uncertainty? Will you be also calculating the uncertainty on the emission inventory you're establishing?
Yeah, actually, we didn't calculate the uncertainty because it was already made. It's already made in the report from the Labor of Inspection. They are the ones declaring emissions for Cyprus to European Union. So they do have in their report estimation of uncertainties. I didn't put them here in this presentation, but they have been estimated on a national level. And so the added uncertainty afterwards would be in terms of the level of detail for the spatial disaggregation. But I think it's difficult to normally what you estimate is the total emissions, the uncertainty for the total emissions, depending on the input data that have been used for this calculation. They can be found in the labor inspection report. And then you can, by using air quality modeling, you can compare the results with measurements, for example, of air quality concentrations in the air, and try to understand how, like for other emission inventories, and see which ones are the most consistent with measurements, and try to look for reasons of differences and improvements of how to get better consistency between modeling and measurements.
Okay, thank you, Eva. So now we move to Feng Zhang from the City University of Hong Kong. So can you just please go ahead with the presentation mode? We can't see your screen now.
Hello.
No, I can't see your screen yet.
Oh, sorry, I forgot to share. So can you see my screen?
No, not yet.
Oh,
So this will be our last presentation
yes.
in the session.
So is it okay now?
It appeared for a second and then it went disappeared again.
Okay, let me try again.
Yes, now we see your screen. You just need to put it in presentation mode. Okay. Okay, great.
Okay.
So the floor is yours.
Okay, thank you for your introduction. This is Ruifeng Zhang. I'm currently, sorry, I need to hide the. I'm currently in City University of Hong Kong in Professor Chek Chen's research group, and later I will join his research group in course as a postdoc. And today I'm going to talk about enhanced sulfate formation mediated by nitrate photolysis, chlorine chemistry, and photosanitization in atmospheric particles. So first is introduction part. So recent field measurement shows that sulfate and organic composition are the most abundant component in the Mediterranean region, and we can see that sulfate and the organic matter contribute like around 35% and 23% respectively, and also the ammonia, nitrate, and the sea salt also contribute to the PM2.5, although their proportion is relatively smaller than the sulfate and organic matter. And also in this Middle East and the Mediterranean region, due to the high light irradiation, so the photochemical reactions can be the one of important process in forming the secondary aerosols. And in this talk, we will focus on the sulfate formation. Here is a quick overview of sulfate formation pathway that have been mentioned in previous studies. So it mainly includes the gas phase oxidation by OH radicals and also the several aqueous oxidation of dissolved SO2, like by transmetal ions, and also and also the photosanitizers. However, the chemical transport model simulation found all these mechanisms are able to fully explain the high concentration of sulfate observed in the atmosphere. So the thing is, considering all this background and also high concentration of sulfate in the Middle East, we have been trying to find other new process. And the experiment setup used in our study is in situ Raman flow cell. So basically, we adjust the wet flow rate and dry flow rate to achieve the desired RH inside of flow cell. And we use Raman spectroscopy to detect the particle composition during the reaction. And here is an example showing the sulfate and nitrate Raman spectrum. Firstly, I will introduce the sulfate formation from nitrate photolysis. That is, we recently reported the new sulfate formation pathway. So briefly, the nitrate can be photolyzed to produce reactive species, and this reactive species can further react with the dissolved SO2 to generate sulfate. And based on our experiment finding, we develop an equation that is SO2 uptake coefficient as a function of nitrate photolysis rate. So this equation can be further incorporated in the chemical transport modeling to further evaluate this process in the atmosphere. And furthermore, we investigate the how the halide ions affect nitrate photolysis rate and also the sulfate formation rate. Since due to the high surface propensity of halide ions, so the presence of halide ions can attract nitrate ions toward the gas particle interface. And at the interface, there is a reduced solvent cage effect. So the nitrate photolysis can be further enhanced. And also presence of halide ions can further promote the sulfate formation. And based on the reported role of nitrate photolysis in forming sulfate. So furthermore, we investigate the interaction of nitrate photolysis and chlorine chemistry in forming sulfate. So in the coastal range, the upon adsorption of NO2 by sea salt, so its hydrolysis can further generate nitrate. And under irradiation, the nitrate photolysis can generate the OH radicals, as I mentioned earlier. And the formed OH radical can further react with the chloride ions that can further generate this reactive chlorine species. And additionally, the photo-induced transfer of chloride ions can also generate the chlorine radicals. So all these reactive chlorine species can further react with dissolved SO2 to generate sulfate. And also, based
1 minute
on
left.
Okay. Also, based on our experiment result, we have developed these equations, that is SO2 uptake coefficient as a function of nitrate photolysis rate and chloride photolysis. So based on our reported role of nitrate photolysis and chlorine chemistry in forming sulfate, and also since in the Middle East there is a high level of light intensity and also the high concentration of organic matter in the atmosphere, and the presence of marine environment, we propose another potential pathway, that is, since organic matter can form anthropogenic activities and also some chromophoric dissolved organic matter can form the marine environment. So certain species can absorb light under irradiation to become triplet state. And the previous studies have shown that triplets that can further react with the chloride ions to generate reactive species. So we speculate that this reactive species can further react with SO2 to generate sulfate. So to verify our hypothesis, we have performed some experiment involved chloride ions and also photosynthesizer. So in this experiment, we use imidazole 2-carboxyaldehyde, we call it IC in short, as an effective photosynthesizer. So IC typically is generated from glycol and ammonia. And glycol is one of most abundant dicarbonyl in the atmosphere. It can be from biogenic source, and the ammonia, it can be generated from the fertilizers and also potential fuels. So here is a result showing that sulfate formation in the presence of chloride ions and the photosynthesizer. So here we choose the imidazole as a less effective photosynthesizer and IC is effective photosynthesizer. The experiment result clearly showed the high sulfate formation rate in the premixed ammonia chloride plus IC. And also we did not see the significant sulfate formation in the absence of chloride ions. And also we noted that sulfate formation rate is higher in the premixed ammonia chloride plus IC compared with the ammonia chloride plus ammonia nitrate. So this system represents the interaction of the chlorine chemistry and the nitrate photolysis, as I mentioned earlier. So overall, we think that interaction of chlorine chemistry and photosensitization process is a much effective process in forming reactants. Okay, it's come to the conclusion part. So based on the field measurement, the secondary aerosols contributes most to the PM 2.5. However, our understanding of the formation of this secondary aerosol is still remain limited. And also air quality model underestimates the sulfate concentration. And our laboratory research explore new mechanisms of missing sulfate from the nitric photolysis chlorine chemistry and photosynthesization. And future study on SOA formation from this process are needed, and we call for more lab modeling field synergistic studies to fully assess the significance of these potential pathways in the atmosphere. Okay, that's all. Thank you for your attention.
Thank you for the presentation and the interesting results, especially that are very relevant to the Middle East. I have a question.
Sure.
From Panos saying, well done for the work. Not clear which property of the increasing heat waves in the Middle East affect the chemical reactions you mentioned. Are they temperature dependent?
Typically, and all the reactions I mentioned relative to the photochemical reaction, so that is related to the light irradiation. So I think in summer, the light intensity in Middle East or Mediterranean region is quite high. So I think the photochemical reactions in this range should be quite effective.
Okay, great. So thank you for the answers, and thanks for the great presentation.
Thank you.
So this session comes to an end. Now back to you, Eleni, and thanks for everybody for attending and for your questions and interest.
Many thanks, Dr. Afif, for chairing the air pollution sources and impacts session. So we're going to have a very short 10-minute break, and we should be back for the VBIGO presentations. So it's 10:43 now, so let's say 10:55, we should be back to continue. Okay, thank you, everyone.
studenti, quindi la certezza.
Okay, thank you everyone for coming back. I will just quickly introduce our chair for this session, for the VPICO session, Professor Fatma Öztürk. which is a professor at the Boluaband İzzet Baysal University in Turkey. Just a quick reminder to keep it within the 2 minutes because we have a lot of presentations to go through. So I'm going to give the floor to Professor Fatma, and I will be handling the presentations. So I will let you know when you're about to wrap up. Can you see my screen?
Yes.
Yes, excellent. So I'll let Professor Fatma to introduce the first speaker.
Thank you, Eleni, for introduction. And our first speaker is Zhang Kong Liang from King Abdullah University of Science and Technology, Saudi Arabia. And Zhang Kong, floor is yours. You have only 2 minutes. Please keep up with the time. Thank you.
Sorry, just one small thing, Eleni. So you need just to put it in presentation presenter mode.
Okay, thank you. Let me just try it again because I cannot see it when I have it on full mode.
Yes, and then display settings. Yeah, exactly. Okay, great. Thank you.
Let's start. Sorry. Okay,
yes, you can
okay.
start.
Okay. Hello, everyone. This is Dan Tong from the Czech Chance Group in King Abdullah University of Science and Technology. Today I'm going to present.
No voice.
Sorry. The voice is low.
We cannot hear you very well. If you can try speaking closer to your microphone, maybe.
Okay. So let me use this. Sorry. Is it better? Sorry, can you hear me?
I can hear a lot of interruption for some reason. I don't know if it's coming from you.
I'm sorry. Hello?
Okay, now we can hear you. You can go.
Now you can hear me, right? Okay,
Yes.
Okay, thank you. So this is Sankong from Professor Shek Chen's group in KAUST, and today I want to talk about secondary photochemistry take place in the incense burning particle. We know incense burning is a very popular religious activities in many parts of the world, like China, any other countries in Asia, India, as well as Middle East. So we know that it emits a lot of particles, but we rarely look into will there be any other chemistry to severe the air quality, air pollutions, why the particles were emitted to the atmosphere. So in this, we examine the photochemistry between the incense burning particle and the sulfur dioxide under the sunlight. We use Fs, number fraction of sulfate containing particles, as a proxy of the sulfate formation. That means the secondary pollutant formation in the atmosphere. We can see that under dark conditions, there will be rapid sulfate formations, and it increases as a function of relative humidity because of the increased water, aerosol water, liquid water content. And during the light on, the sulfate formation, especially under low relative humidity, got an increase. because of the concentration effect of the photosensitizer presented in the incense burning particle. We can see that if we increase the concentration of sulfur dioxide and increase the relative humidity, we find more and more organic carbon and sulfur co-containing particles form. That means there is a co-formation of sulfate, and the organic carbon in the incense burning particle as a secondary pollutant. And using we parameterize this efficiency and to model the sulfate formation rate in a typical India, which is popular in burning incense. And we found with UV, that means sunlight in the environment, the sulfate formation is much more rapid than compared with in the dark. So the conclusion is the sunlight can drive rapid sulfate formation and secondary organic aerosol formation in incense burning particles, which can severe the air pollution in our surrounding environment. So that's what I want to present. Thank you.
Thank you. Let's go to the next one. Professor Fatma, just give us a second and we'll.
Okay, our next speaker is Mark Vadal. He is from University de Littoral Cateau d'Opale, and floor is yours, Mark.
Thank you.
You're welcome.
So hello everyone. Today I'm presenting a part of our research work recently published entitled The Source Apportionment of PM2.5 in an East Mediterranean Site. So as it has already been mentioned, inhaling particles, especially PM2.5, can cause diverse health effects. That is why it is important to discover which species and or sources contribute the most to the toxicity of these particles. And that is possible by evaluating the oxidative potential. So in this study, the oxidative potential measurements, as well as the source apportionment of PM2.5, were done on samples collected in an urban site, which is under the influence of the biggest power plant running on heavy fuel oil in Lebanon, and characterized by a high density of population. So the sampling was conducted for approximately a year, and the samples were then chemically characterized for their carbonaceous fraction, water-soluble ions, major and trace elements, as well as different families of organic compounds. And on the other hand, two acellular methods, which are the ascorbic acid, AA, and DTO-tritol, DTT, assays were adopted so to evaluate the oxidative potential. So as for the results, so the OP values that we have obtained in this study were in the same range of those found in other urban and industrial sites. OPAA seemed to be more sensitive to organic compounds, especially those emitted from combustion sources, while high correlations were found between OP-DTT and elements emitted from vehicular emissions and heavy fuel oil combustion. Additionally, the apportionment of oxidative potential using a multiple linear regression model showed that local anthropogenic sources, especially biomass burning, vehicular emissions, and heavy fuel oil combustion, contribute to at least 62% of the values of OPAA or OP-DTT. And by that, it is important to focus on these sources in order to reduce the impact of PM2.5 on human health. And finally, as for the seasonal variations, the contribution of biomass burning in winter to the values of oxidative potential was at least 33 times higher compared to summer, while the highest contribution between the sources was found for heavy fuel oil combustion during the summer period. Thank you.
Thank you, Mark. And our next speaker is Anthony Ray Pommier from the Cyprus Institute. And floor is yours.
Anthony has some issues with the sound, so if we can move on to the next one, Professor Fatma, and then we can come back.
Okay, the next speaker is Maximilian Zezarvetas from the Cyprus Institute. You can go on, Maximilian. Thank you.
Thank you. Good morning. So the presentation I will be giving, or the summary I will be giving this morning, is of a study that was published in Science of the Total Environment this summer. entitled Emissions of Volatile Organic Compounds from Residential Biomass Burning and Their Rapid Chemical Transformations. You can access this paper through the QR code in the corner. The study was carried out between 2021 and 2022 in Ioannina during the winter. This is a small urban city located in northwestern Greece and settled between the mountains. So during winter, it experiences intense air pollution events due to the low boundary layer and not a lot of aeration of the city. You can see through the second pictures. And we, the Cyprus Institute, contributed a PTR of MS, which you can see located in the van station that was parked outside the air quality station. The time series in the center of the slide shows the intensifying nighttime pollution events, which were happening all the way through to Christmas and New Year's night, which are highlighted. So the nighttime pollution had species such as acetonitrile, which you can see in the diurnal cycles. This is usually attributed to biomass burning, but we also saw daytime peaks in toluene and xylenes, which are happening with traffic in the morning, and then species like formic acid, which were increasing throughout the day, which is synonymous to photochemical production. Those conclusions were confirmed by PMF analysis, which showed more than 50% of the VOC were coming from biomass burning, to the lower extent primary, and then more so to secondary, and also coming from fossil fuel and photochemical production. The paper further highlights emission very high pollutant concentrations. We calculated emission factors from those PMFs and also highlighted very extreme OH reactivity, which suggests bad air quality again. Thank you.
Thank you, Maximilian. If Anthony is ready, we can go back. If not,
yeah, Anthony, if you can try to, we'll try to unmute you. If you can unmute yourself, see if we can go now.
are you ready, Anthony? No?
Can you hear me now?
Yes.
Yes.
Finally,
Very
sorry.
well. It's okay.
So, good
Go
morning.
ahead.
So the purpose of this presentation is to show you that it's possible to detect and quantify NOx emissions from space and use these quantifications to improve air quality monitoring. And to do this, the main instrument is TROPOMI, which is able to observe the NO2 pollution from space at high resolution and with a daily frequency. And the images it provides allow detecting the main pollution hotspots, especially in the Eastern Mediterranean and Middle East, for which the cloud cover is low. And to convert the pollution levels observed from space to actual emissions without relying too much on external data, the simplest way is to use a flux divergence scheme, which uses forecast wind and concentrations to infer daytime emissions. And if the results that are obtained are average enough, we can distinguish urban centers from industrial isolated. On the three examples here, which are Riyadh, Saudi Arabia, Qatar, and Cyprus, we can see that megacities have high emissions on wide areas, and we can also see isolated power plants acting like point sources that can be fitted with a Gaussian. And when emissions from sources like that are estimated, they can be compared to existing inventories. Typically, it's the case for the power plants in the north of Qatar and for the Vasilikos power plant in Cyprus, where global inventories like CAMS or EDGAR have emissions higher than estimated ones. And these differences may question the construction of such inventories, but it can also be a way to fill gaps in these inventories. And it's the case of Riyadh, for which the emissions of the two power plants in the east of the city do not appear in global inventories. It's also the case for the two power plants in the north coast of Cyprus, which are reported in global inventories, but not in regional ones. So overall, I would say that these quantifications from space can provide, in certain cases, alternatives to bottom-up inventories to improve air quality monitoring. And I deeply hope that future improvements to this method will allow doing more. Thank you very much.
Thank you, Anthony. And our next speaker is Minas Ayokevidas from the Cyprus Institute, and floor is yours. Thank you.
Good morning. Can you hear me well?
Yes, very well.
Okay. Thank you, Eleni, Dr. Sturk. Today we'd like to present a recent work on the atmospheric occurrence of the highly toxic polychlorinated naphthalines, or PCNs, which is part of our broad spectrum research on persistent organic pollutants, or POPs, in Cyprus, mostly due to lack of any corresponding information on intentional use, particularly for the occupied part of the island. PCNs were first patented as dielectric fluids, and here are the main sources: waste burning, old capacitors, and other old building materials, construction materials. 50 gaseous and particulate phase samples were separately collected and analyzed in our lab. First, we examined the thermodynamic behavior. Slopes from the relation of surface air enthalpies and temperature are shown in the graph on the center. Temperature dependence was strong, with steep slopes for almost all congeners present in hollow wax mixtures, indicative of secondary recycling, but shallower for most of the combustion-related ones, highlighted with these red frames. We also applied a series of molecular ratios. Here on the left, congeners in red are strongly influenced by combustion sources, while none of our samples was placed directly into margins designating technical mixtures. Other sources, namely thermal, seem to contribute, particularly during January and some days in March. Contribution of thermal processes was confirmed here on the right. The ratio of combustion related to total PCNs gets lower and close to evaporation as temperature increases. We also evaluated gas particle partitioning. The AB with the green line and mixed with blue line sorptive equilibrium models predicted better the partitioning, and the urban areas adsorptive model for the more fluorinated and some combustion CNs. However, our own constructed empirical model based on quantum mechanics scored overall the best fit in performance. To sum up, thermal processes regulate the atmospheric variability of PCNs, with a strong presence of revolatilization sources from stockpile contaminated sites. Thank you.
Thank you, Minas. And we move on to our next speaker, Theo Economou from the Cyprus Institute. And floor is yours, Theo.
Thank you. Good morning. My name is Theo Economou. I'm an associate research scientist at the Cyprus Institute. I'd like to present some work on how we quantify synergies between environmental stresses on human mortality. This is a work between the Cyprus Institute and the University of Thessaloniki under the auspices of the LIFE series project. So to try and link environmental exposures like temperatures on daily mortality, we use what we call distributed lag nonlinear models, or DNLMs. This is a statistical sort of regression tool, which produce plots like the one you see on the top left, which is a quantification of the relative risk of mortality as a function of apparent temperature in this case. So it's a function of humidity and temperature, and a temporal lag. So it picks up the accumulation of risk during, say, very hot periods or indeed very cold periods. The plot relates to data from the city of Thessaloniki. And what we see in the bottom right corner of it, the red blob there means there's elevated risk. The red means more mortality risk than what we would expect when we have very hot and humid weather for a short time period. what we did in this piece of work is to extend the methodology of DNLMs to include joint effects from other exposures or stressors, such as air quality. So the bottom left plot, the three of them there, is showing the temperature effect for different values of the air pollutant PM10. And you can see for PM10 is 1 of 104 on the leftmost plot. The red becomes a bit more red, so there's an elevated risk from having hot weather, humid weather, and also polluted air. We can use these mortality risk estimates, combine them with observations of mortality counts to try and estimate the proportion of deaths that we observed that are attributable to these sort of exposures. These are the three plots on the right panel that show this for PM10, ozone, and NO2. So if we focus on PM10, what we see is for low, medium, and high, these are the bars, low, medium, and high PM10 levels for different intensities of heat, from extreme cold to extreme hot. What we see is that the red bars, the height of the red bars increases as we have high PM10 level and extreme heat. So hot and polluted is bad news. The same goes for NO2. Less so for ozone, but it's still true when you have medium or high ozone levels and it's hot, you'd have a lot more mortality than you'd expect. So basically, our study, our implementation of our framework has confirmed the hypothesis that mortality risk due to heat stress is actually compounded quite a lot by air pollution, and that varies between pollutants. At least this is true for the city of Thessaloniki, which is true that it's one of the most polluted in Europe. And as far as we know, this is the first study to have looked at this in such detail. I mean, the synergy between the stressors. Thank you.
Thank you, Theo. And the next speaker is Yonilda Kuşsa from the Cyprus Institute, and floor is yours. Thank you.
Thank you, everyone. So I'm Yoni Kuşsa. I'm from the Cyprus Institute, and I coordinate the emissions team that also supports national stakeholders in their reporting obligations towards European and international directives. So we have collaborated with established partners in Europe in the framework of the World Emission Project. It's a European Space Agency funded project, and its aim was to provide global emission monitoring service using satellite data for their constraining. And this satellite-derived emission inventory then were compared with bottom-up inventories in close collaboration with end users. And one such user and case study was Cyprus, to validate the emissions of carbon dioxide and NOx emission flags against the nationally reported emission inventories. There are two phases of the project, and they produce different products. Phase 1 uses a priori data from TNO that is mostly based on EMME national budgets, and the constraint was with OMI data. Phase 2 products use Carbon Monitor and CEDS for air pollutants and a priori emission data, and the correction is done with TROPOMI that we know have a higher resolution observations. Now, there are some specific conditions in Cyprus, as you've heard in the previous presentation, about the northern part not being regulated and not being reported, so there are no actual estimates there. We made an effort to have some assumptions, and also as you see in the small map in the middle of the plot, the resolution of such data do not allow for a very direct comparison with point or small area sources. However, we've seen that in the phase 2 products, the reported inventory is higher for CO2 than the estimates from the project, and the opposite stands for NOx. However, in phase 2, there are very few years, only 4 years available there. We see that both CO2 and NOx are higher values in the reported emissions than the project satellite-derived emissions. And if we go into sectoral analysis, the two main sectors that need to be verified and further analyzed is energy and road transport. However, both data miss the reduction in emissions during COVID 2020 due to the restrictions, and they are not able to capture this, as you see in the first two plots of the right plots. Boarding on new projects that if you are in the emissions framework, you would know that there are many projects that work with satellite inversions. We would like to extend here collaboration partnership to any countries in the region that would like to use our expertise in replicating this study for the evaluation of the national emissions in the EMME region. Thank you very much.
Thank you, Yonilda. And I would like to give the floor to Corey McClintic from Cyprus Institute. And floor is yours. Thank you.
Hi, good morning. Can you hear me?
Yes.
Great. So my name is Corey McClintock. I'm also on the National Emissions Reporting team. And I'm presenting some preliminary work on, sorry, someone has included my presentation from last year and not my presentation from this year.
This is the slide I was sent. Would you like
we
to share
just
your screen?
go to the next presentation?
Oh, we can go to the next one. Yeah. I mean, this is the slide I was sent, so.
Oh, we can move to the next speaker, and we can
move to the next one, and then we can come back at the end. Yes.
Okay. And next speaker is Eliane Farah from St. Joseph University of Beirut. And yeah, floor is yours, Eliane. Thank you.
Thank you. Hello, everyone. I'll be presenting to you my research work entitled Speciation of the PM2.5 carbonaceous fraction in an urban site in Greater Cairo area, done in collaboration between St. Joseph University in Lebanon and Université du Littoral Côte d'Opale in France in the framework of the Polcare project. This project aims at assessing the different potential pollution sources and the human health risk associated with this pollution in Greater Cairo area, which is considered as one of the most polluted megacities in the world. In order to achieve these objectives, an intensive sampling campaign has been carried out over a period of 2 months at the rooftop of the National Research Center in Cairo. Following that, the samples were analyzed for their carbonaceous fraction and their organic compounds. The preliminary results showed that the PM2.5 concentrations ranged from 47 to 507 micrograms per cubic meter during the sampling period, with an average of 145 micrograms per cubic meter. Road traffic was a remarkable source of pollution that could be identified by the ratio of OC over EC ranging between 2.2 and 5.4, indicating combustion sources besides the abundance of C24 and alkanes, high concentrations of hopanes and PAH, as well as the ratio of benzoa-anthracene over benzoa-anthracene plus chrysene, showing an average of 0.36, indicating pyrogenic emissions such as vehicular emissions related to gasoline emissions. Other combustion sources are revealed, such as waste burning identified by high phthalates concentrations and biomass burning identified by OC over EC concentration ratios higher than 6 and high concentrations of levoglucosan. On the other hand, primary biogenic emissions are determined by the presence of sugars as well as C27, C29, and C31 in alkanes, in addition to a considerable fraction of secondary organic aerosols such as isoprene, alpha-pinene, and beta-caryophyllene oxidation products. The combination of these data with the characterization of inorganic species of PM will help us to further identify sources and quantify their contribution later on via source apportionment models such as PMF. Thank you.
And thank you, Eliane. And if Dr. Corey is ready, we can leave the floor to her. And not, we can move.
Screen now.
Yes.
Okay, I'll just go into full screen. I'm Corey McClintock. I'm from the National Emissions team. And I'm doing a preliminary estimate on the short-lived pollutants released from a wildfire in Cyprus. So emissions from forest fires qualify as a memo item in the EMME reporting, which means that they're not included in national totals. They should be reported separately. but as of the latest Cyprus informative inventory report, they're not estimated. So I wanted to look at a recent large event in Cyprus and see how the totals released compared to the national totals. Just as a general background, in the EU, the short-lived air pollutants make up a relatively small amount of emissions, but they can be much higher for certain countries. Cyprus is situated in a Mediterranean climate, and we have an expected increase in wildfires. And also in 2021, I chose that year because we had this fire that was reported as our worst fire in recent decades. And in fact, in that year, according to the European Fire Information System, we had the highest burn percentage of national area in the European Union. In general, we ranked 4th, but that year we were highest. So quickly, looking at the method and the results, we have the Korean land cover classification clipped to the shapefile of the fire event, which classified areas burned as damaged, destroyed, or possibly damaged. We did a conservative estimate and excluded possibly damaged areas, but because we have this breakdown by species, where we've got forest area but also agriculture area, we could do a tier 2 calculation. And this yielded pollutants, we're looking here in the results relative to the Cyprus national total, quite high for carbon monoxide, 86%, about 9% for non-methyl volatile organic compounds. So as the fires can represent a large amount of total emissions for particular species, their accurate monitoring and quantification is vital. Thank you very much.
Thank you. And Dr. Michel Dury from University of Nicosia is our next speaker. And floor is yours. But we cannot hear you right now.
Hear me? Okay. Good morning.
Good morning.
Can you hear me now?
Yes.
Okay, great. This is preliminary research on secondary pollutants formed from the exhaust gases in vehicles. And this secondary pollution is formed from thermomolecular and photochemical reactions that are exacerbated in Cyprus because of the high solar radioactivity. Furthermore, there are frequent dust storms that occur. There have been 9 to date in 2023, and these dust particles act as nucleation and condensation sites for possible SOA formation. Because of the fine particle size of PM2.5, it poses a heightened risk for cardiovascular and respiratory deaths, whereas ozone is known to cause inflammation in the lungs. Research in Cyprus focuses on PM2.5, PM10, NOx, and CO2 traffic mitigation, and there's less research on VOCs and traffic. Research has estimated that 60 to 90% of VOCs are involved in the formation of secondary PM2.5, and the proportion of secondary PM2.5 can range from 30 to 90% of total PM2.5. In the poster here, the uppermost graph shows VOC mass in 2021 calculated in cohort, and it shows that 25% of VOCs were liberated from motorcycles. Emissions masses were also calculated empirically and using traffic volume from the Ministry of Transport. However, these emissions estimations varied greatly between the emission inventory and the measurements from traffic sites all around Cyprus. Secondary PM2.5 was calculated using SOA product formation factors and mortality rates using risk exposure coefficients for NO2, SO2, PM2.5, and ozone. It was found that premature cardio deaths from secondary PM2.5 constituted about 40% of total cardio deaths from PM2.5. Using the average PM2.5 concentration of 12 micrograms per cubic meter recorded during the 2.5-month COVID lockdown period, which indicates and represents a period of reduced traffic pollution sources, we predicted a 42% reduction in mortality from cardio from PM 2.5 exposure. And ozone concentration in the same year resulted in 7 all-cause premature deaths per 100,000 inhabitants. The replacement of petrol motorcycles with electric ones will reduce the VOC concentrations that we experience in Cyprus. Thank you.
Thank you, Dr. Michel. And our next speaker is Dr. Nancy Fakri from St. Joseph University of Beirut, Lebanon. And floor is yours, Nancy. Thank you.
Hello, everyone. Today I will present our recent work on chemical characterization of PM in the tunnel of a Middle Eastern capital. So road transport is an important source of pollution in the Middle East, and Lebanon represents one case study of the region. The emission inventory and previous source apportionment studies have both showed that road transport is an important source of pollution in Beirut. Therefore, it should be investigated in a deeper way. So a tunnel study was conducted in Salim Islam for 5 days in 2014, where filters were collected simultaneously inside and outside the tunnel during 14 sampling periods. Chemical analysis was performed on some fraction of the filter, and the emission factor, which is defined as mass of pollutant per unit of fuel consumed or distance driven, was calculated for the Lebanese fleet. The emission factor of the PM 2.5 component, including OC, EC, ions, elements, and organic component, were calculated and compared to results of other tunnel studies. HGVs are not allowed to circulate on weekends and during weekdays in the morning and the evening, which allowed us to isolate the LDB from the total fleet. The emission factor in Salim Islam were 2 to 5 times higher than compared to other tunnel studies. The high emission factor could be explained by the high vehicle age of the Lebanese fleet, the local maintenance practice such as the removal of the catalyst due to its high maintenance costs, along with weak law enforcement. Finally, to assess the contribution of exhaust and non-exhaust emission, we have explored the sensitivity of the chemical mass balance results to source a profile of exhaust and non-exhaust emission obtained through positive matrix factorization collected from 3 sites in Lebanon, 2 urban sites, Hirsh and Zouk, and 1 suburban site, USG. CMB results have revealed a high contribution from non-exhaust emission. Non-exhaust emission are generated by resuspension of road dust, the abrasion of brake and tire, and the deterioration of road surface. Thank you.
Thank you, Dr. Nancy, for the presentation. And our next speaker is Dr. Ahmet Arca. He is from the Cyprus Institute, and floor is yours, Dr. Ahmet. Is Ahmet Arca here?
I am here now, I think.
Okay, floor is yours then.
Hi guys, I am Ahmet Arca, as well introduced. I'm from Cyprus Institute. Today I am going to succinctly present our approach to an early warning support system for climate-sensitive vector-borne diseases. The VECLIM project. The VECLIM project is supported by the Cyprus Institute and Wellcome Trust, and it is a useful resource developed to help the scientists as well as healthcare providers and policymakers in the planning and implementation of targeted disease vector control measures. So, climate change has a great impact on the geographical distribution of disease vectors such as mosquitoes. Especially the so-called tiger mosquito is now spreading into new areas where they hadn't been seen before. With these mosquitoes, vector-borne diseases such as dengue, chikungunya, Zika, they're also spreading. Our approach in helping with this problem is to create a dynamic open access repository that will integrate climate and environmental data with vector pathogen models, climate projections, environmental variables, and surveillance data. So we aim to deliver accessible evidence-based risk assessments, risk maps, seasonal activity, temporal projections of vector activity and disease transmission. And we aim to deliver this information in a platform, veclim.com. And we believe that this will provide a data-driven approach to health planning. You can see veclim.com as an interactive geographical information system We built it using React at the front end and mainly Python at the back end. Veclim is optimized for easy navigation and data presentation. Within the site, we will provide visualization options as well as possibilities to run customized scenarios and inform users about possible risks. We suggest that you go and visit veclim.com. We believe that it is an essential tool for adapting to the increased risk of vector-borne diseases due to climate change. And we welcome any engagement and collaboration with the scientific community to enhance the utility and impact of veclim. Thank you.
Thank you, Dr. Arca. And our next speaker is Gian Domenico Burro from Cyprus Institute, and floor is yours.
Good morning, everybody. I cannot see my presentation. Okay, perfect. So yes, today I'm gonna show you some preliminary results of part of my PhD project. And in this study, let's say, I wanted to compare the urban Italian effect and intensity from observation and the simulation. So with respect to the simulation, we used the WRF model coupled with the urban canopy model and two different planetary boundary layers. With regards to the observation, the data that we used were provided by the Cyprus Department of Meteorology. And as you can see in the picture at the center of the poster, for the greater area of Nicosia, we have 6 stations, but for this study, we used the Nicosia urban station and Astromeritis as a rural station. The period of the study was from the 10th of July 2021 until the 10th of August, and we didn't only compare the absolute values for 2 meters higher temperature maximum and minimum, but we also estimated the intensity of urban Thailand from observation and the model. And as you can see in the plots in the here on the left side, one thing that is quickly visualized is that the model, especially for maximum temperature, is capable to follow quite well the observation trend. And another important thing is that, and the interesting thing is that the intensity of urban Thailand is varying within the day, but also day by day. So the black dot line is the one related to observations, while the red line is related to YSU planetary boundary layer, and the green line is Bullock. So these are the preliminary results, and next further work that will be accomplished will be a wind speed analysis in order to define some calm days and other further simulations with a more advanced urban canopy model. Thank you.
Thank you, doctors. And we move to the Dr. Asmahan Ali Otman from University of Zawiya, Libya. Are you here, Asmahan? Yes. Is Asmahan here? No?
Good morning.
Good morning. We are hearing
دكتور
you.
اسمهان. اوكي دكتور اسمهان علي المختار عثمان، عضو هيئة تدريس او ديبارتمنت جيوغرافي زاوية يونيفرسيتي. Title study variation in trends maximum temperature change in the Libya cost for period 1961 2099 when using special techniques. The study related forecasting in maximum temperature for 3 stations in Coast Libya, Benina meteorological station and Sirte meteorological station, and Tripoli Airport meteorological station for the period 2010-2099. And beside on the day and beside that 1061 to 1019 using the GCM model and regional model Headley Center, which is the period beside an greenhouse gases construction. Result the three study station agree in their strong correlation with element 260 of the GCM model, which in temperature below 2 meters will differ in their level of correlation with other elements. Second, their agreement between the study station, the direction of change maximum temperature toward the future period converted day beside period, and they are concerned with the scenarios A to A. It shows that their discovery with between 4 period for each station at significant level of less than 0.05. The result of simple linear regression and variation also converted that the maximum temperature trend to rest in the winter and spring season took positive values of variable B, and direction in the summer and fall season took negative values of the variable. Thank you.
Thank you, Asfahan. And Dr. Christos Zelefontos from the Cyprus Institute will present his presentation, and floor is yours.
Hi, I'm Christos, a PhD student at the Cyprus Institute. Sorry, I hear some sounds at the background. I don't. Okay, so this study investigates new particle formation events within the Asian tropos aerosol layer over the Asian monsoon region using the EMME model, and we implement parameterizations from the cloud chamber at CERN to get the results. So the atoll is a major aerosol source in the upper troposphere and low stratosphere with profound climatic and socioeconomic implications. So our research integrates observational data from the MIPAS instrument within the EMME satellite and the StratoClim campaign with EMME modeling. We see here that on part 2 of the poster, the NH3 vertical profiles, and we see that the eastern part exceeds the western and baseline parts, but in our model in particular, we see that there's a tendency to overestimate ammonia. So on part 3, you see there that in our model, there's a coincidence of ammonia with cloud cover and convection. So we believe that this higher amount of ammonia is a result of more convective events. So when the convective updraft flux is higher, we get this higher ammonia amounts in cloudy days. And that's another proof for this is the fact that during this in part 4 here, we see that there's that the model agrees with the aircraft observations, that the aircraft observation managed to get this high ammonia mixing ratios in one day, which agrees with what we see in the model, which further backups our claim that probably this MIP has missed these high ammonia amounts in cloudy days. And then we we have like we compare to the StratoClim campaign. So these are flight campaign. Yeah, sorry, I can. Okay. So and we see that we get good agreement of our model with the observations of StratoClim. I also noticed that the format changed of the somehow, but yeah, I mean, yeah, so there's good agreement, and we see that we have incorporated the parameterization from the cloud experiments, the nucleation parameterizations from the cloud experiment at CERN. So that's what we see in part 6. So we see that the ternary and synergistic nucleation rates, which are the curves in purple and red, are dominant within the atal region, which is at the back in gray, and are responsible for almost all the particles that are formed within the atal. We aim to quantify these multi-agent nucleation events, explore associated atmospheric and climatic consequences, and provide a comprehensive analysis of the particle composition and size distribution of the Asian tropos aerosol layer. And we aim to deepen our understanding of aerosol climate interactions over the Asian monsoon region. Thank you.
Thank you, Dr. Christos. And we move to the Dr. Nikki Paisi from the Cyprus Institute. And floor is yours. Hello.
Good morning. I'm Nikki Paisi. I'm a PhD student at the Climate and Atmosphere Research Center of the Cyprus Institute. And this presentation is about modeling of carbonaceous aerosols for air pollution health impact studies in Europe. So it's important to obtain representative concentration of fine particulate matter to capture accurate exposure level and excess mortality estimates. And in this work, we used the WRF-Chem model, air quality model, to simulate fine particulate matter and the carbonaceous aerosols over Europe. And with different sensitivity tests on emission changes and meteorology, we aim to improve the model performance. Then we wanted to quantify excess mortality and from the best performing model configuration and compare the results with the default using the global exposure mortality risk model. Table 1 summarizes the different sensitivity tests we used, and Table 2 some statistical metrics to assess model performance for fine particulate matter and the carbonaceous aerosols. We can see notable improvements from the sensitivity test, and the model reaches adequate accuracy thresholds for PM2.5 in both simulation, and it is able to support health impact studies. However, organic aerosols are not accurately modeled in the default setup, and it requires modeling adjustment to obtain representative results. This difference between the two simulations resulted in 105,000 excess deaths per year difference, which is 15% higher than the default, and of which 52,000 excess deaths are due to carbonaceous aerosols, which were captured by our modeling improvements. And these are equal to 65% higher than the ones obtained from the default. Based on the above, the contribution of carbonaceous aerosols to excess mortality is 70%. However, this is still a lower limit, since further improvements are possible, and we did not account in this case for the potential increased toxicity of these particles. More information can be found in this paper here on the right, which was recently accepted for publication in Air Quality, Atmosphere and Health. Thank you.
Thank you, Dr. Paisi. And our next speaker is Dr. Areti Papa from University of Patras Department of Physics, Greece. And if you are ready.
Can you hear me?
Yes, please go on.
Okay. Good morning. I'm Areti Papa, and I will present my study on the evaluation of the meteorological forcing and its impact on air quality prediction. High-resolution models have become vital for improved regional air quality forecasting. So the aim of this study is to evaluate the high-resolution ability WRF models to simulate the main weather parameters in a major coastal urban area in the East Mediterranean Sea in order to gain valuable insights into the model performance. to note that WRF is a state-of-the-art numerical weather prediction system. Additionally, this study examines the influence of WRF as the meteorological driver for an air quality system for the same area. Evaluation is based on in-situ observation and is conducted using a series of statistical metrics. The model aligns best with observed values for the variable of atmospheric temperature, solar radiation, and relative humidity, but it systematically overestimates the wind speed, particularly at night. These biases stem from the model's boundary layer seams. Throughout the year, the accuracy of wind prediction is closely tied to the precision of PM2.5 forecasts. Wind error have a more pronounced effect during the cold season at most stations when local emissions are elevated, impacting both daytime and nighttime predictions. During warmer season, wind-related effects are most noticeable during the day. High emission areas are less affected by wind inaccuracy, while during cold season, suburban areas face noticeable PM2.5 shifts due to wind and pollution migration. Thank you very much for your attention.
Thank you, Dr. Papa. And the next speaker is Dr. Katyana Konstantinidou from the Cyprus Institute, and the floor is yours.
Hello, everybody. Can you hear me? Can you hear me?
Yes, we can hear you.
Oh, thank you. I'm Katyana Konstantinidou. I'm a postdoc at the Cyprus Institute, and today I will present to you work on the simulated future thermal stability over cities in Cyprus. Urbanization affects the population of the city due to, through changes caused on the land surface properties of the area, therefore, which alter the surface energy balance of the city, and since then the climatic conditions over the region, including humidity and temperature, which are the climatic variables used to compute the wet bulb temperature, used in this study as a metric to investigate how thermally comfortable are cities simulated to be in the future. Using the output of the WRF model simulation driven by SEMS4 model under the RCP.5 scenario with a horizontal resolution of 4 kilometers for a future and a control and a future period of time. We analyzed the results over Cyprus, over the whole island of Cyprus, and separately over Nicosia and Limassol for the summer season. We set a dangerous threshold of the wet bulb temperature, which is more than 30 degrees Celsius, and a survivability limit of over 35 degrees Celsius. Having in mind this, we see that the summer average projections of the maximum wet bulb temperature shown on the presented on the maps here show a simulated increase of up to 77 degrees Celsius over specific locations over the whole island of Cyprus compared to the recent past. When seeing the results shown on the table, we see that the values of the simulated maximum wet bulb temperature over Nicosia and Limassol in the future seem to be approaching the dangerous threshold of the 30 degrees Celsius, but not reaching it. Then we see a high increase of the maximum projected heat stress over both cities in Cyprus in the future of about 5 degrees Celsius. Thank you for your attention.
Thank you, Dr. Katyana. And the next speaker is Dr. Konstantina Kontosi from the Cyprus Institute. The floor is yours.
Good morning. Can you hear me?
Yes, very well.
Okay, thank you. My name is Konstantina Koutroumano. I am a PhD student at the Cyprus Institute and the National and Kapodistrian University of Athens, and I will present you part of my PhD. So we used the WRF model that was coupled with a single layer in order to dynamically downscale the investigated variables from the regional to the local scale. The WRF model ran for the years of 2008 and 2001, and in these years we found the days that we had a heat wave phenomenon, and we found 32 days in total. So in the bottom left figures we can see the third domain of the WRF model, which was the area of our study, and the upper of the two figures shows the domain from a satellite image. Whereas the bottom one illustrates the land use classification that was derived from a dataset that combines the land use classification from the Copernicus Global Land Cover Dataset, the MODIS, and the WDAPT LCZ. And in this map, we can distinguish the urban areas, which are illustrated with gray and black colors, and the black color represents the most densely built up areas. Moreover, on the upper right, we can see the variables of maximum air temperature, the LST, and the wet bulb. And we took into consideration this variable in order to estimate the exposure. And the figures illustrate the spatial distribution of the temporal average of the days that we had the heat wave event. And also we use satellite data in order to compute the NDVI, which is a vegetation index, and we also took it into consideration in order to estimate the exposure there. And then concerning the sensitivity part, we use the data for the population of citizens that are older than 65 years old, because we know that they are more vulnerable to this excessive heat. And finally, we used the machine learning technique of clustering with k-means in order to combine the exposure and the sensitivity into different classes of risks. And here we can see the results of the 5 and 10 classes on the bottom right plots. And as the colors of the map go from blue to the red, it means that the risk of this class increases. And we can see that in the case of the 5 classes, we can distinguish the urban areas which have the higher risk. However, we cannot see any intra-urban variability. And however, in the case of the 10 classes, we can see this intra-urban variability, and we can also recognize the LCZ 3 and 6 that correspond to the compact and open low-rise buildings respectively. Thank you.
And thank you, Dr. Konstantina. And we move on to the next speaker, Dr. Sabri Mutlu. He's from Istanbul Technical University, and floor is yours.
Hello, everyone. I guess my voice is clear, so I jump into my presentation. This is my ongoing PhD thesis. Some preliminary results I would like to show you. My motivation is to investigate the water circulation of İzmit Bay. İzmit Bay is located at the easternmost end of the Marmara Sea. It's very important for the country because its location is strategic in terms of industry, transportation, pollution, highways, railways, navy, etc. So the water circulation of the bay is a key element for a healthy and resilient marine environment, since it regulates nutrient distribution, sedimentation, oxygen levels, heat, and pollution levels. As you know, Turkey is a developing country, so sometimes water treatment systems are behind, so the circulation is critical. Anyway, I jump into the methodology. We have to classify wind speeds for the bay because Beaufort scale is valid for oceans and is a wide scale. So we define the new wind speeds for the forcing of the model. As seen on the red dot in the figure, on the left bottom is the location of the weather station, and we defined wind speeds and also wind directions. For the water circulation model, we prefer MIT GCM. MIT GCM is a valid and well popular known water circulation model. We have to customize for the bay, and we have to adjust some parameters. And also we define the western boundary as an open boundary in order to simulate open ocean conditions. But in this case, we have to choose Orlansky method instead of real-time or in situ data. As you see in the middle of the presentation is the initial condition of the salinity and temperature. It's homogeneously distributed for the domain area, but you see that below 50 meters, the lower layer is formed by Mediterranean water mass originated from eastern Levantine basin. Anyway, I would like to jump to my results. As you see that the process is adiabatic. This means that there is no heat change between the ocean and atmosphere, but any water mass formed when the wind speed is high. First of all, I would like to say that under weak winds, wind forcing, the bay water is stagnant or quasi-stagnant. This means that the water circulation is under control of open boundary conditions. But when the wind becomes significant at higher speeds, the direction is quite important. As you see that on the right figures in the presentation, you see that the salinity of the surface waters have great variation in case of the wind direction coming from the southeast, southwest, or northeast. The most important finding, according to my study, is that the winds with west component creates an accumulation of upper layer water towards in the bay. It's considered as an onshore wind forces downwelling in the eastern basin. On the other hand, the winds with east component creates an upwelling regions because of the transportation of water base outside the region. I'm gonna show more results in the following months. Now my article is under evaluation. Thank you for your time.
Thank you, Dr. Mutlu. And our next speaker is Kyriakos Sophocleous from the Cyprus Institute.
Hello, can you hear me?
Yes, we are hearing you. Floor is yours.
Okay. IEEE standards most commonly used representations for real numbers is a double precision with 64 bits per memory address, and also a single precision with 32 bits per memory address. Both these representations use 1 bit for sign and standard length binary strings for the exponent and the significand. Double precision has been the most common representation used in atmospheric chemical kinetic simulations. However, moving towards higher resolution and complexity simulations, performance and scalability are restricted by the required amounts of memory, while power consumption is increased. In addition, since a floating point variable is represented by a finite number of bits, computer hardware is limited when representing an arbitrary real number range. In order to fit into a designated number of bits, many real numbers are rounded after mapping. Posits are a direct replacement of the floating point representation. With an n-bit posit consists of 1 bit for the sign and variable number of bits for regime, exponent, and fraction. And this novelty for this representation allows for a tapered accuracy. which means that numbers that are close to unity in magnitude, which are the most commonly used in calculations, are more accurate than extremely large or extremely small numbers that are not so common. Replacing floats with posits is expected to provide more accurate species concentrations and reaction rates for the same size memory addresses, faster operations and for similar resources, and lower power usage. And there are many cases in which 64-bit double precision can be safely replaced by 32-bit posits, enabling faster memory transfer, better scalability, and effectively halving the required memory. Our job was to develop some OD solvers, Rosenbrock OD solvers, with emulated 32-bit posits. This work was done in Julia language, and used them on the small stratospheric model, common chemical mechanism with 5 active species and 10 reactions. Replacing double precision with these posits produced 1% relative difference on results with half the required memory. Posits also managed to maintain stability for longer simulations where single precision fails, and produced more accurate results with the same memory utilization. For our future plans, by the way, this is my last year's presentation, the one that you are showing. I don't know why.
This is what I was sent. So the slides were sent by the presenters. This is what I have.
Anyway, our plan is to test solvers with more complex mechanisms, and preliminary results have shown that some of the most sensitive variables need to be kept in double precision.
Okay, thank you, Doctor. And we move on to the next speaker, Dr. Georgia Lazoglu from the Cyprus Institute.
Can you hear me?
Yes.
Okay, thank you.
Please go ahead.
So, my name is Georgia Lazoglu, and I'm a postdoc researcher at the Cyprus Institute. And today I will present my study entitled Predicting Future Wet and Dry Spells Duration in Europe, and analysis with bias-corrected QGAM data. So the first aim of this study is to use a novel and recently introduced statistical method, the QGAM, which is a combination of quantile mapping and generalized additive models. And then using this bias-corrected data with this method to quantify future changes in wet and dry spells across Europe. So for this reason, we are using data from 2 sources, the observational data from the GSOD and data from a Eurocortex climate model. These data are for 5 European stations, which represent some case studies with different climate characteristics. So we use the historical period as a calibration period and data until the end of the century for bias correcting and quantify the spells. So the results show us that the QGAM method can significantly improve the number of dry days that simulated from models. And additionally, the rain data approach is more accurately approach the observed ones. As it concerns the future data, we noticed that the frequency and duration of dry spells will be increased in the future, and the most extreme dry spells are projected for the end of the century according to the business as usual scenario. For the wet spells, the frequency and duration will be decreased in the future, and the fewest episodes with the minimum duration are projected again at the end of the century until with the business as usual scenario. And last but not least, the annual precipitation from wet spells is projected to be minimized in the future. Thank you very much.
Thank you, Doctor. And we move on to the next speaker, Dr. Iliana Kosopi from National Observatory of Athens. The floor is yours.
Hello, everyone. I am Iliana Koutoupi, and I am a PhD student at the National Observatory of Athens. In this study, we utilize geopotential data at 500 hectopascal during the summer months for 40 years above the Mediterranean in order to describe the omega blocks trends. Using the methodology shown on the slide, based on the location and the pressure gradient of the high system and the two lows, we conclude that the omega extent has noted an increase, meaning more extremes affecting more regions. Also, the high location seems to have moved up to 3 degrees towards the north, meaning that heat penetrates deeper into Europe. Most of the omegas are observed during July above West Europe, have a duration of up to 8 days, and are related to the negative null phase. Their frequency seems steady and the blocking intensity is larger after 2000. Event duration and intensity present a statistically significant correlation with the excess heat factor. From the omegas in Europe, 83% of them affect the Mediterranean and especially 12% affects Greece. An omega that seriously affected Europe was during 4 to 10 September 2023. Heat wave in West Europe and floods in Greece and Spain. As we can see, temperature reached 33 degrees in UK and 38 in France. Germany, Austria and Norway experienced heat wave conditions too. On the other hand, we can see heavy rainfall of about 800 millimeters in just 18 hours in Greek regions when Mediterranean Daniel formed, and floods in Spain due to the cut-off lows. From this study, we conclude that omegas will continue their presence in Europe and the Mediterranean, and this is the reason why further investigation is needed regarding the omegas features trend over the next years. Thank you.
Thank you, Dr. Iliana. And we move to Dr. Eyna Ezeldi from Egyptian Meteorological Authority from Egypt.
Okay, can you hear me?
Yes, very well. Go ahead, please.
Okay, thank you. I am Rania Azidin from the Egyptian Meteorological Authority, and today I will talk about comparison study between heat indexes of different algorithms over Egypt. As a stronger link between global warming due to climate change and changing weather patterns in the form of increasing intensity and frequency of extreme events such as heat waves. And heat waves occur as a result of high temperatures and high humidity and may persist for more than 2 days, and this may cause a lot of disease. So it is very important to study heat index that combines air temperatures and humidity to represent human perceived equivalent temperatures, which hold the apparent temperature and define how hot it would feel. And for this study, we use the daily weather data of mean air temperatures and mean dew-point temperature of 20 stations over Egypt for the periods of 2000 from 2000 to 2015 from the NOAA site. And for this study, we do three comparisons. First, we calculated the index of the data within weather range of statement table, where temperatures between 20 to 50 degrees Celsius and moistures represented by relative humidity or dew point. And for this study, we using unweighted and weighted algorithms. Unweighted to calculate absolute difference, and weighted to calculate numbers of occurrence, which calculate ratio, which represented weights. And the second, we calculated heat index of the data outside the red range, which represented temperature less than 20 degrees Celsius of statements original tables. And finally, we comparisons between different algorithms using Pearson's correlation coefficient to measure the how strong relationship between these algorithms. Figure 1 represented mean of air temperatures, up figures, and relative humidity for each station during this period over Egypt. And this figure 2 represented distributions of the daily mean temperature with dew point, left image, and the daily mean temperature with relative humidity, right image of 20 stations over Egypt, and the most frequent condition of the given data represented by the yellow area. And figure 3 represented examples for relative humidity. Left table represents the number of occurrence of each weather conditions from statement table of the given data. For example, if temperature equal 40 and relative humidity equal 20, these weather conditions will occur about 20 times. And the right table represented the ratio of occurrence of each condition or weighted algorithm. Figure 4 represented final result of comparison of temperatures and relative humidity and also dew point. Left table represented metrics in degrees Celsius describing how well different heat index algorithms cohere with the original concepts of statements apparent temperature. We find the first 4 algorithms are the best for Egypt station for the relative humidity, and 9, 7, 2, and 3 are the best for dew point conditions. On the right table, Pearson's correlation coefficient to measure how strong a relationship between 21 heat index algorithms. And we find that a lot of algorithms produce the perfect or equal 1 or high positive correlation about or greater than 0.9, and some algorithms like 15, 20, and 21 produced a moderate correlate. Thank you.
And thank you to Raina, Dr. Raina. And our next speaker is Dr. Lauren Baer from Justus Liebig University of Gießen, Germany. And floor is yours, doctor.
Yes. Hello, good morning, everyone. Can you hear me?
Yes, very well. Go ahead, please.
In my short PICO, I would like to introduce a global approach to define concurrent atmospheric and marine heat waves. Since atmospheric and marine heat waves are becoming more frequent and lasting longer, there is a growing need to study their co-occurrence because their ecological impact and economic consequences could be greater than that of an individual event. The key objective of this study is therefore to provide a consistent and globally applicable approach to define and detect concurrent heat waves. We define a marine or an atmospheric heat wave when at least 5 or 3 consecutive days, respectively, exceed a daily threshold defined as the 90th percentile, based on a 30-year historical baseline period. In the next step, we build our approach of a concurrent heat wave that can either be defined as a simultaneously occurring heat wave or a concurrent atmospheric and marine heat wave occurring with a certain time lag by using a method called event coincidence analysis, or ECA, that investigates statistical interrelationships between event time series and quantifies the strength, trigger, and time lag of such interrelationships. Coming to the 40-year mean heat wave characteristics of simultaneously occurring heat waves compared to standalone atmospheric and marine heat waves, it appears that concurrent heat waves are less frequent in both realms, shorter than marine heat waves, and of comparable duration to atmospheric heat waves. And lastly, they are more intense than atmospheric and marine heat waves, which is the most important result of our analysis, demonstrating the growing need to study concurrent heat waves. Setting the atmosphere as the trigger in the ECA, these maps show the lags with the highest probability to observe a marine heat wave after an atmospheric heat wave was observed, as well as the coincidence rate. On average, during summer, we observe a 0 time lag in most parts of the Mediterranean due to the shallow mixed layer of the ocean, and a higher lag, for example, in the Aegean Sea, here resulting from the Etesian wind systems and corresponding upwelling. Thank you very much.
Thank you, Dr. Larin. And we move to the next speaker, Dr. Eman Said Mohammed from the Egyptian Meteorological Authority from Egypt. Are you ready?
Okay, can you hear me?
Yes, we are hearing you. Floor is yours.
Okay. Hello, my name is Iman Said. I am a researcher at Egyptian Meteorological Authority. I'm here today to talk about the worst snowstorm indicates affected large parts on Middle East in December 2030, like Egypt, Jordan, Cyprus, Lebanon, and we called it Alexa storm. For the first time, we see snowfall on the Egyptian capital Cairo in more than 100 years ago. I will discuss this extreme case through studying air temperature, rainfall amount, and amount of snow falling, especially on St. Catherine. First, the data I used are observations data operated by Egyptian Meteorological Authority for 5 stations like St. Catherine, Cairo, Nozha and Burj Al Arab, in Alexandria and Marsa Matruh. Also used the reanalysis data of ERA 5 and ERA 5 land with resolution 25 kilometer and 10 kilometer. Also using a natural color RGB image from EMSAT. As we shown in these 5 charts of hourly temperature indicates that temperature dropped below normal for continuous 6 days from 11 December to 16 December, and the nighttime dropped to 5 degrees Celsius at Cairo, and over St. Catherine temperature dropped to -2 degrees Celsius, and heavy snow falling for 7 hours, and it's rarely to occur with this intense. For confirmation, reanalysis data, ERA 5 with resolution 25 kilometer are used, which showed the agreement with actual data shown above that indicates that daily mean temperature over Egypt reached to about 9 degrees Celsius in continued period from 10 December to 16 December. Also, reanalysis data was used to determine the total accumulated rain that fall over Egypt during this Alexa storm, which showed that its peak was on 13 December and reached to 140 millimeter of daily rain. Finally, I will talk about the snow that fall on Egypt for the first time, especially on St. Catherine, by using reanalysis data, ERA 5 land resolution 10 kilometer of this period, and this indicates that the thickness of snow depths reach 3.7 centimeter over St. Catherine, and this rarely happens. Also using climatological data for 30 years from 1980 to 2010 from ERA 5 land, and calculating seasonal average of months December, January, and February, and with comparison with seasonal average of 2013 year, we found that from this comparison that thickness of the snow depth is above normal by 1.04 centimeter, and this is huge difference that indicate how this Alexa storm is hazard in this time. And all these observations and reanalysis data is agree with the satellite image as we shown the image from 12 December during the storm, and the image from 15 December after Alexa storm arriving and leaving over Egypt. Thanks for your listening.
Thank you, Emma. And I am inviting to Dr. Rihan Al-Saidi from the University of Jordan. And the floor is yours, Dr. Rihan.
Thank you. Okay, greeting everyone. I am Rihan Saudi from the University of Jordan, and today I will be sharing insight from our study on the relationship between GRACE follow, satellite missions, terrestrial water storage, and the standardized precipitation index in arid region, specifically Amman Zarqa Basin in Jordan, from 2008 to 2018. Our main aim is to assess the effectiveness of GRACE data in tracking hydrological drought. Just a quick brief about GRACE. It is a satellite mission launched by NASA and DLR in 22, measuring Earth water mass by studying Earth gravitational force. Terrestrial water storage anomaly data is available with a spatial resolution of 1 by 1 degrees and can be freely accessed on NASA website. For our study, GRACE data alongside daily rainfall data from 4 stations in the Amman Zarqa Basin were used. This basin, located in northern Jordan, as shown, and it is a crucial area with the country's highest population and industrial activities. 1 month SPI were calculated and compared with the monthly equivalent water thickness from GRACE data. The correlation coefficient between the variables were calculated. The result shows no correlation as illustrated on the diagrams. This lack of connection between the variables might be attributed to the uncertainties in GRACE data, or there could be a component on the terrestrial water storage, as it includes surface water, soil moisture, and groundwater storage that remain unaffected by the rainfall variability. And thank you for your attention.
And we thank you. And the next speaker is Dr. Anastasios Rovihakis from the Technical University of Crete. And floor is yours.
Yeah, hi everybody. My name is Anastasios Rovihakis, and today I'm going to show you some of our recent findings regarding the effects of wildfires on local weather. So for this project, we basically ran 2 sets of simulations using the WRF-Chem model. One set of simulation was using the wildfire emission data to represent reality as closely as possible. And we also performed some counterfactual experiments for the same time period, but without any wildfires, to basically make comparisons between the two. And the comparisons between those 2 sets of experiments, when it comes to temperature differences, can be seen in figure A, where we basically saw that the areas in blue end up having a degree lower temperatures when compared to the areas in red. Now, the areas in blue were underneath the smoke plume, and basically to explain those differences in temperature, we calculated the radiation budget as seen in figure B. Basically, this coincides very well with figure A because all the areas underneath the smoke plume were basically end up having and receiving lower radiation budget because the smoke plume particles have very strong reflective properties, and so they end up reflecting most of the radiation back into space, and that explains the lower and higher temperatures. Now, if we isolate only the smoke plume affected areas in Greece that are marked inside the red circles in figure C, we can then compare them with the rest of the areas that are not affected by wildfires. And this comparison can be seen in figure D. And this is the main outcome of this project, where we basically saw that as air pollution from wildfires increases, temperature tends to decrease for those smoke plume affected areas. And the exact opposite is true for the rest of the areas in Greece that were not affected by wildfire. For those areas, as air pollution increases, and mind you, this is air pollution from cities or agricultural activities. As this type of air pollution increases, temperature also tends to increase. And that's pretty much it for me, I guess.
So,
okay. Thank you. And our next speaker is Christian Milke from German Federal Environmental Agency from Germany. And if you are ready.
yeah, thank you very much.
Yeah.
But I'm from the German inventory team, and I've been working together with partners from Sweden, Italy, and the Netherlands, as well as Switzerland, on this large project Avengers, which really works on the legacy of the project Verify that you can see here on the left. So state of the art is that we really got to talk with inventory folks together with the modelers, and that was done for the first time within Verify, and we were able to produce also inversion results, as you can see in the lower left of the image. But if you also have a scout around for other independent data which is able to verify your emission inventory and your national totals, for example, for methane or for CO2, You will briefly go to the global models, for example, from ECMWF, which only have a resolution of 2 to 3 degrees spatially, and they are not easy to handle for inventory experts because they are non-modeling experts. And they are also lacking, of course, the tinker points able to understand and interpret the data. So within Avengers, we will build flexible inversion tool for the inventory community that you see here to the right. We will have a high resolution grid of 1 by 1 degree with a possible zoom in further. We will offer a GUI interface as well as a Jupyter script, and also create a Git, which will be also created here by the German Environmental Agency here together with me, and together with the modelers. What we will try to develop is this tool for an inventory agency, so that we will be able to learn on what is really going on in the background of the atmospheric modeling, so that we will be far better able and suited to interpret this data to be able to answer to the 2019 IPCC refinements for QA and QC, so that we can then use this model output in order to verify our national totals of the 3 greenhouse gases. And I will challenge, or I invite all of the inventory folks that are present here in this conference to approach either me or Yunilda that you've previously seen. If you are interested in this FIT IC tool, and if you are wanting also to take part as a test customer of that tool for your emission inventory, then please approach us and we'll be glad to help you aboard the FIT IC Avengers test users train. Thank you very much.
Thank you, Doctor. And next speaker is Dr. Samira Kodayar from the Mediterranean Center of Environmental Studies from Spain. If you are ready, we can leave the floor to you.
Morning, can you hear me?
Yes, very well.
Very
Go ahead,
good.
please.
Thank you very much. Good morning, everyone. I would like to use this opportunity just to introduce very briefly a recently funded cost action, FutureMed, a transdisciplinary network to bridge climate science and impacts on society. So basically, the main motivation of this effort is the fact that we all know that the Mediterranean region is really recognized as a climate change hotspot as a whole, where current change and future scenarios consistently point to significant and increasing risks in the future. So there are, of course, many different risks and impacts affecting the region and affecting all different departments of the atmospheric, ocean and land climate system. And of course, all the socioeconomic priority sectors in the region, such as, for example, human health, water resources, or food production. Despite all the knowledge gained during the last decade with respect to many different aspects of climate change impacts in the region, at this point, I think all community, the science community knows and is clear about the fact that to achieve progress, we really need and is necessary to move beyond silo approaches towards integrated efforts. And here when FutureMed comes in play, this effort has the overarching aim to serve as a transdisciplinary platform or network to bridge high impact weather and climate change impacts knowledge between and connecting scientific communities, key stakeholders, and citizens. So we like to say that our main goal is really to gain knowledge not only about what the weather will be, but what the weather will do in this region. So please, if you can click once over my slide.
It's only once.
Okay, doesn't matter. So there was a second picture on that, and I would just say it by heart. So basically, the structure of the cost action, as I think it's important to get to know that, is formed by 4 main working groups. And in these working groups, working group 1, 2, 3, and 4, that are really transdisciplinary, but also flexible and strongly working together, we will have in working group 1 a team working on hazards and socioeconomic impact, just to bridge weather and climate modeling with actual socioeconomic impacts. We will have a second working group 2 on climate adaptation decision and support tools, just providing an overview of what is right now existing and developing research for a future agenda together with stakeholders. Then there will be a working group 3 that will be or will ensure a strong cross-sectoral engagement from policymakers, decision makers, and citizens. And of course, in working group 4, we will work very hard to really support network activities through communication and through dissemination of our results. So if you are interested in this cost action, please just Google it by name, and I invite you to participate, just enrolling in one of the working groups, and you will receive very soon information about our activities in the future. So thank you very much.
Thank you, Doctor. And I am inviting Franco Marenko from the Cyprus Institute. Is Dr. Franco here?
Franco, you're muted, I think. So if you can unmute
Can
yourself.
you hear me now?
Yes, yes.
Yes, you are hearing very well.
Perfect. Sorry for that. So I'm here to show the activities of the Cyprus Institute in the calibration validation campaign for Earth Care using UAVs and LiDARs. And first of all, I'd like to introduce to you Earth Care. That's a satellite mission that's going to be launched in 2024 for the understanding better of clouds aerosols and how they affect the Earth radiation budgets. And what we want to do is to calibrate and validate, together with teams all over the world, this new satellites using measurements from UAVs and ground-based remote sensing. You can see some examples in the bottom left here. And actually, we've already started to do that, which you may ask, how can we have started to do that before the satellite is launched? But we're actually taking part in a rehearsal campaign that's going to prepare the future calibration and validation that you can see here in the middle. And so we've started doing some measurements which are going to replicate what we will be able to do when the FKR satellite is launched. And we are part of a number of projects, which is the pilot project, which is the one you can see in the middle for the rehearsal campaign. And we're also in a project with the Eratosthenes Center of Excellence, which is called Coral, which is going to be the main project for this calibration and validation. And finally, we are partners in a project based in Spain on the calibration and validation of ceilometers, which you can see on the bottom right. And that's all I wanted to say. Thank you very much for listening. And yeah, thank you.
Doctor. And the next speaker is Dr. Georgi Themistokoulos from Agricultural Research Institute of Cyprus. And floor is yours. Is Dr. Georgi here?
Hello, can you hear me?
Okay. Yes,
okay.
Now we are hearing.
Okay, good. Hello, everyone. I'm George, a postdoctoral researcher based on the Agricultural Research Institute in Cyprus. And today I would like to very briefly present to you a newly developed algorithm which was designed to efficiently process data coming from systems such as automated non-steady state soil chambers. So these systems measure soil gas exchange, and you can subsequently use it to measure the gas flux for various greenhouse gases. However, one of the issues with these datasets is that they provide very complex, very large datasets, which are difficult to process and obtain an actual flux value from. So one way of bypassing that problem is this algorithm that you can see the outline on the bottom. Basically, it's an interactive, user-friendly software that can be run from R, and you get all the data The data is subsequently screened using various criteria, and the regression model that best describes that relationship is fed based on those criteria. And the user can get a flux value from it. So as an illustration, we got data from a real experiment at 38 days. So you can see from the figure in the middle that you get your gas flux for various gases depending on your analyzer. Here we got CO2, methane, and nitrous oxide. And the algorithm can later do an upscale to daily fluxes, as you can see on the figure on the right. So all of it is done automatically, and because we are limited on time, if you want to know more about it, then just get in touch with me. Thank you very much.
Thank you, Doctor. And I move to the next speaker, Dr. Maria Kezodi from the Cyprus Institute.
Yes, hello, I'm Franco Marenko again. Sorry, Maria cannot make the presentation because of health reasons, so I'm going to give it for her.
It's okay.
So I'm going to present the Edu for Climate campaign. And this is a campaign that has two objectives: to monitor in real time particulate matter and gases in air pollution hotspots, and in particular in the EMME region, and the validation of a state-of-the-art LiDAR, which is called PMI, for three-dimensional retrievals of particulate matter. And this campaign is going to involve, well, the instruments that I mentioned, the Remetis PMI, and some UAVs that's going to be working concurrently. And so we are going to be using optical particle counters and also novel, cost-effective SO2 and CO2 sensors. And a number of experiments will be done mainly in Cyprus. And we are going to plan to map emissions at the port of Limassol, and also stack emissions at power plants, cement works, and quarries. And a few figures around the poster show the instrumentation we're going to have. And again, thank you all for listening.
Thank you, Doctor. And I am inviting our last PICO presenter, Dr. Dimitri Krasnov from Estonian University of Life Science from Estonia. And floor is yours, Doctor.
Hello, can you hear me?
Yes, very well.
Okay, hello everyone. To begin, I would like to express my gratitude to organizers to having me here, especially Eleni, who deal with my slide mess. So thank you very much. So the purpose of this presentation is to show a UV-based sampler for volatile organic compounds. So in 2021, can you see my mouse? Probably not. Okay, I measured the VOC using the commercial available DJI drone with the installed SKC pump with a single inlet. And using this simple setup plus ground-based and tower-based measurements, I was able to investigate both vertical and horizontal distribution of volatile organic compounds. Obtained concentration was merged with the micrometeorological data, land cover data, and eddy-covariance data. And utilizing the footprint model, so we were able to identify the source contribution area to the measure signal, or simple terms, where the signal came from. In 2022, we applied to AtMax's DNA in order to develop the new sampler for, okay, I missed my presentation. I don't see my presentation for some reason.
Yeah, we are not seeing two as well. Dr. Diana Francis, or Eleni, are you there?
It seems that I've lost my share screen ability. Just give me a second, I'll bring it back on.
Okay, okay, thank you.
Okay, so we applied for ATMA Access DNA and we got accepted, and the new sampler was developed by Cyprus Institute USLL laboratory, and already in the October 2023, so we ran the field campaign with the new sampler, and the new sampler, as you can see on the rightmost pictures, have the 4 inlets. And this design allows us to use the different sampling strategies, like 1 by 1, which is perfect for consequences sampling, for example, in the different altitudes, or like in different horizontal spots. At the same time, it's the system allows to use the together design, which means that we can sample two samples, to take 2 samples at the same time, which allow us to, for example, compare the different sorbent inside the sorbent tubes. And currently, we keep testing the system here in Estonia. Yeah, that's it from me. Thank you.
Okay, thank you very much. And I think we have completed the PICO session with the presentations, but I can open the floor for discussions if any of the attendees has questions to our presenters. We can initiate the discussion.
I think there are no questions for this session. If there are any questions, submit them to the chat. You can send them later because we're already at lunchtime, if that's okay. Yeah. So now we're going to have a break until 1:30, and then we will be back for the next session. Many thanks, Professor Fatma, for facilitating this session, and we should be back in 45 minutes.
Thank you, Eleni.
Thank you. Thank you.
Hello.
Hello.
Okay. Just would like to check if you can listen
Yes,
me.
Yes, we can hear you. Yes.
Eleni, there's Lucia, which has the role of only for listening. Now we need to. She's already connected.
Yeah,
we
yeah,
made
but
her presenter.
yeah.
Yes.
Yeah.
We made her presenter,
Yes,
Shabal,
please.
so she should be able to share her screen. But should I introduce Dr. Diana first to chair the session, and then we go into?
Yes, please.
Yes. Okay. Excellent.
Yes, please.
Excellent.
Eleni, may I ask a question? It is Georgi Stenchikov. I have the first talk after so keynote. So should I do anything? We checked yesterday. It looked like I can share my screen. Do you want to check if I can share the screen?
If you want to do it after the invited speaker first, because we gave the right to Lucia to present first, and then as soon as she's finished, we can check. Is that okay?
No, I will present.
Okay.
I will present after invite a speaker, so that will be
yes.
No way to check, but that's okay. If you can do, let's do it. If not, so we will try it on the way.
Yeah, it should be okay. We will give you presenters right as soon as we're done, so we don't lose any time now. So
okay,
we're all back.
Good.
No worries. So welcome back, everyone. Our next session is atmospheric dust, climate change, and weather extremes. It will be chaired by Dr. Diana Francis from Khalifa University in UAE. So I'm going to go to Dr. Diana to introduce our invited speaker. Thank you.
Hello, everyone, and welcome to the atmospheric dust, climate change, and weather extreme session of this annual workshop. And we are happy today to welcome Dr. Lucia Muna from the National Center for Research in Italy. Dr. Lucia, can you hear us?
Yes. Okay. I will share.
Okay, the floor is yours, please.
Okay. Thank you for the introduction. I'm very happy to give you this presentation. I just wanted to. Okay. So, can you see the presentation in presentation mode? Okay. So I will talk today about atmospheric desert dust and about impact and measurement for this relevant constituent of the atmosphere and why this can be of interest for East Mediterranean and the Middle East, so in the region of interest of this conference. I just want to underline a few things before starting. So I'm working at the National Research Council in Italy, but I'm also part of ACTRIS, which is a European research infrastructure for aerosol cloud and trace gases. So it's really relevant for this kind of application. So let's start on desert dust, why and how they are important in general. And often desert dust are summarized in a short acronym, which is sand and dust storms, SDS. And I just reported here a few examples of big desert dust events. So starting from the left, we have a dust storm in Iran, which was also part of a bulletin from WMO about airborne dust. So you can see this really huge amount, like a wall of desert dust lofted in the air from the surface from South region in Iran and going toward a village. On the right side, you can see the sky completely yellow and orange in Heraklion in Crete in 2018, but also over the Alps in 2021. And indeed, there were a lot of newspaper reporting about this colored snow because of the presence of the dust. So what we have here is desert dust, which is lifted in the air and then transported, and this can have a lot of impacts. And the transport is is happening in different ways. So there is the local transportation with a huge amount of dust transported in the places, but there is also the possibility that the dust is transported over longer distances. This is just a plot showing that the dust lifted in the air in Africa then is typically transported towards South America. And indeed, there are some investigation about the fertilizing properties of the desert dust for Amazon basin. So some impacts of the desert dust on the environment. This is a nice plot showing how the dust can be lifted and transported and going and interfering with hurricanes, biosphere, indirect effect, and so on. So just summarizing, the main aspect on which the desert dust can have some impacts is the climate, the weather, and the ecosystem. Climate, because the dust particle, like all the aerosol particle, can affect the radiation budget of our planet. And considering the desert dust is the biggest source of aerosol into the atmosphere, it's clear that this contribution can be really relevant. Then desert dust can have an impact on the cloud formation. So, acting as condensation nuclei, both for the clouds, both for the ice particle, is really relevant how this can interact with the humidity component of the atmosphere, and so working on cloud formation and having again impact on precipitation, but also on the radiation budget, because clouds has a role on the radiation budget. As I said before, desert dust can have an impact on the cloud formation and so also on the precipitation processes, but also on the hurricane formation. Then desert dust can have an impact on the ecosystem because they are deposited and settled on the ground, so having some impacts on the biosphere and on the ocean, so leading to a contribution of minerals to the oceans. But dust has also impacts on socioeconomic sectors. These are the most relevant ones. First of all, the first thing that came to our mind is air quality and public health. And this is because this tiny particle can have an impact on the respiration activity of the human being, but also it has been seen that having a lot of particles going deeply into the body, they can produce disease on the cardiovascular system, but also there is an evidence of higher incidence of meningitis in cases of big and severe dust events in some locations on the globe. Sorry. Then there are impacts on transportation and aviation. So considering places close to the source region, cases like the ones that I showed before with this kind of wall of dust arriving in the place, this implies, of course, low visibility. So it's not possible to take off a landing in such places. On the other side, such kind a lot of particles on the ground also reduce the possibility of landing and again to take off from airport because of slithering problems. And dust in the air, so even not at the ground but at higher altitudes, can have some impacts on the engines and reducing the time life of airplanes. So this has clearly impacts on this socioeconomic sector. Then another sector of interest is the production of solar energy and so power plants. And this is because the presence of the dust reduces the incoming solar irradiance. Then there is the soiling on the panels, so making them dirty, and so the needs of cleaning them up, and so producing a lower energy in case of big dust event and soiling on the panels. So it's really important to understand more and to monitoring the desert dust. How this can be done through observation in a wide vision of this term. So what we can have are satellite observation, models, and in situ observation. So we have here just one example of satellite measurement. This is a LiDAR working from the space. Then we have, this is one example of observation just showing the presence of the dust. I think this is Corsica region. And from the ground, we can have measurements from LiDARs, for example, which are active sensors, and from photometers, so providing the site's distribution. And in situ, so collecting the concentration of the particle at the ground. So just few examples of the main categories of observations. Then we have the simulation as well. So this is one example of multimodal products generated from different prediction models. This is under the framework of WMO initiative for monitoring and advisoring the sun and dust storm. So it's WMO SDS WOS system. And this kind of forecast is available at this website. So you can look here to median forecast, the mean forecast, the standard deviation, and the range. So how the different models see in different way the situation. And this is really important for understanding better what will happen in the next days. So in general, we have dust observation and simulation. We can combine them, and of course they have pros and cons. This is just one example. This is a forecast of dust optical depth. So the optical depth related only to the desert dust over the region, which is called North Africa, Mediterranean, and Europe, and East. So this is the multimodal. And again, this is one example, is September 2021. And here on the right are observation. On the top is just a picture taken at my observatory here in Potenza. And you can see here a layer of dust and above some clouds. And on the bottom, the temporal evolution of LiDAR signals. And these are cross-polarized LiDAR signals, so showing particles which are spherical. And you can see here this layer is related to the dust, and here we have the clouds at upper levels. So like in the picture, let's say. And this was showing you that observation can provide more information with respect to the forecast for what's concerned this vertical profiling and this co-presence of aerosol and cloud, while the forecast can provide to you the overview of what is happening in every time of the day and over a wide region. So limitation and good things for the models. Limitation, there are predictions and it's not the reality. There are some uncertainty and disagreement with respect to the observation. And for what concerns the observation, we have as a limitation low spatial coverage, low temporal coverage for the satellite. And from the remote sensing, typically we have low data availability when the weather conditions are very bad. So model reanalysis, which is the combination of observation and models, can be very good for overcoming this kind of limitation. So optimizing the estimation of the future condition through the analysis and reconstructing the past condition through reanalysis. So, and this is one example of reanalysis. So using observation inside the model in some ways, or through the assimilation of the models. And this is the dust AOD in the Eastern Mediterranean and Middle East. So coming back to the region of interest. So you can see here the different months and the season on the right. And going towards the brown colors, it means higher presence of the dust. So, sorry, okay. So what is here evident is that the brownie regions are the source regions. And so you can see that the eastern region, the Middle East region is a source region. And this is The main activity is during spring and summer, but it is not negligible neither in winter and in autumn. While for what concerns the Middle East, is exactly like the rest of the Mediterranean, is affected by the dust in the most only, I mean, in spring, summer, but also winter and autumn, so for all the periods. These are data provided by the Monarch reanalysis that you can find more information in this paper by Di Tommaso. So, which are the observations in East Mediterranean and Middle East available for the dust? So for the models, we have different single models and some ensembles that you can find again on the SDS website, but also the reanalysis provided by Monarch in 2007-2016 period, and the data are reachable at this link. And then we have a specific measurement. What we can have are aeronaut measurements, MISR measurement. This is a microsonal interferometer system, which is a satellite data provided by NASA. MIRAS that combine MODIS data and the mirror reanalysis. Information are available at this paper. And then we have Calypso, so profiling measurement provided from the space. And there is specifically a data set about dust, which is provided by, it's called the LIVAS data set, and observation are provided here. So we used all this information for assessing also the Monarch reanalysis. And I just want to mention also that in May 2024, EarthCare will be launched. And so this will provide vertical measurement of dust together with the other aerosol particles over the globe. So dust observation in the Eastern Mediterranean and Middle East, we can say that they are from ground-based components, there is positive observation in the region. Satellite and model data can be used, but we can wonder about the reliability of the models in the region. So for the near real-time data, so the forecast provided by SDS there is a continuous evaluation in near real time, and the scores of the model are provided on the website. So this information can be retrieved directly there. And then we work, and it was the work of a colleague of mine for his PhD thesis, but also for this paper that I reported here, to compare the dust optical depth provided by Monarch with multi-sensor product. And so we look at the performances of this model and for the different regions, which are these blocks here that you can see. And so we have here we have the Monarch DOD, and this is what we have from the observation. And then in the other two row, you can see mean bias, root mean square error, fractional gross error, and the correlation coefficient, and the number of observations compared to the model. And just for having you, this is a table with the different scores for the different regions, and we have a Middle East, Mediterranean Sea. I don't want to go into details, but you can see here from the mean bias that in the Mediterranean and in the Middle East, the mean bias is very low, is one of the best score in the whole region that we worked on, and also the correlation coefficient is very good. So what we can say is that we have very good performance. Still, for the performance of the reanalysis, we compared the Monarch, so the reanalysis profiles, with the LIVAS profiles, so observation provided by satellite-borne LiDAR for aerosol. And on the top, we have comparison for the Mediterranean Sea region, and on the bottom, the Middle East. And you can see that the profile there is a very good comparison, in particular on the Middle East, with some difference only here in the low troposphere, very low troposphere, close to the ground during the spring period. And for what concerns the Mediterranean Sea, the differences are really related only to the boundary layer. Also for the variability, this is well captured by the Monarch reanalysis. So on average, we can say that there is a very good score on these two regions. This summarizes the analysis of the performance of the model on the region. And then I just want to present you some climatology on these two regions. And we look at the DOD on the Mediterranean Sea and the Middle East. So on the horizontal, we have the years 2007, 2016 as provided by the model, and in the vertical we have the different months from January to December. And the color stands for the dusty color optical depth. So you can see the big difference between the dust optical depth in the Middle East respect to the Mediterranean Sea, and this is because Middle East is a source region. And you can see how depending on the season and the month, the different entity of the production of dust in the Middle East. And also you can see on the Mediterranean Sea that the DOD is higher during the spring and summer. And then we have anomaly in this optical depth. Anomaly respect to the normal months. So considering which is the mean in the different months and looking for anomalies respect to this average. And so you can see here the Mediterranean Sea and on the right the Middle East. Red color means DOD higher than the climatological average, and blue color is for low DOD respect to the normal average. And so you can see that the intensity of the anomaly, of course, is lower in the over the Mediterranean Sea, while in the Middle East is higher, and this is because this is a source region, so also the relative differences are higher. And that in 2008 to 2013, some positive anomaly happened, but then in 2014, 2016, the most of the anomalies are negative anomalies. And this is connected to what we looked for about dust trend in this region. So here we have dust COD, the average in the time, and reported over the time. Mediterranean Sea on the left, Middle East on the right again, and looking and making a linear fit for identifying
1 minute left.
Yes, eventually dust trend. And what we have is a very low slope, negative slope for the East Mediterranean with a p-value, which is a statistical test that we did on the significance of the trend, which is 0.4 almost. That means that this trend is not statistically significant. For the Middle East, we have a more pronounced slope and a lower p-value, but still not sufficiently low to be considered as statistically significant. And so I'm going to conclude to thank you for your attention and to acknowledge the Daskin project that funded a lot of the things that I showed you, and of course the work from Mialis for his PhD thesis. Thank you.
Thank you so much, Dr. Lucia, for the interesting introduction, actually, for the rest of the talks. I'd like to ask you one question regarding to how actually in the monarch analysis the presence of clouds is treated.
Okay, so in the forecast as well is not present, of course, the clouds because they are not let's say modeled, so they are disregarded. But on the other side, it was used as a simulation, modest data, deep blue data, specific retrieval, and so the presence of the cloud is skipped using the modest data that are assimilated into the model analysis. So it's from the observation. Clouds here. And making the comparison, we skipped the clouds using for the observational side. For each one of the datasets, we use the proper cloud screening algorithm, let's say, for each one of the sensors that we use for the comparison.
Okay, thank you so much. So we thank you for your presentation, and I'd like to remind all the attendants to send their questions in the chat. And now we'll move on to our next speaker, Professor Yurgi Stenchikov from KAUST, and he will be talking about the giant dust impacts.
Hello, do you hear me?
Prof. Yurgi, we can hear you, yes, perfect.
Very good.
Can you please put it in full mode?
Yes, I did. Just delete.
Yeah, perfect.
Okay. Thanks very much. So I'm Georgi Stenchikov. I'm professor at King Abdullah University of Science and Technology. KAUST is located at the coast of Red Sea, in the middle of South region in the Arabian Peninsula. So I will be talking on quantifying the effect of giant dust particles on radiative forcing, deposition rate, and atmospheric loading over the Middle East. So the invited speaker described very well all so negative effect of dust on climate. I would not say it is negative, but impact of climate and environment. So I will not repeat this. I just shortly mentioned that Arabian Peninsula. So it's not only the hottest place in the world, one of the hottest, but it warms faster than average of the globe, about 2-3 times. Dust is important climate factor. It impacts climate. For example, the radiative forcing in summer of the southern Red Sea is probably the largest in the world, reaching 40-50 watt per meter squared. Saharan dust affects circulation and shifts the rain belt to the north, increasing precipitation in summer in Sahel. Dust affects precipitation, and we have to account for dust effect when we plan seeding experiments in desert region. And dust, of course, affects quality. So the most important is the effect of dust on radiation, because it produces most of the impacts, but also mass balance and deposition of dust could produce are important, because deposition of dust in the regional seas provide nutrients to the seas, and deposition dust, for example, on solar panels, so affects harvesting of solar radiation. Although the estimates of dust generation and deposition is actually so differ in the models by order of magnitude. Emission of dust differs from 500 megaton to 5 gigaton, and this strongly depends on dust size distribution that affects estimates. Usually, dust models, dust generation models are tuned by fitting the observed optical depths. It's what so usually observed from satellites. We observed radiative effect of dust and could report the dust optical depths. And after them, so loading, mass loading of dust could be calculated so using optical properties of dust. It is recognized that coarse dust is underestimated in the models, and significantly this affects so optical radiative impact of dust, and so other factors. I cite here the recent review by IDB with Jasper Koch. This effect is especially pronounced in the source regions where dust is generated, so regions like Middle East, and dust generation is a complex process that is tuned, as I said, usually using aerosol optical depths. So in this work, we constrained WRF-Chem model by observations of aerosol optical depths, dust deposition, and RNet particle size distribution to estimate contribution of coarse dust in dust emission, radiative effect, and dust deposition, and quantify the dust mass balance. The paper is in press in Journal of Geophysical Research. On the right-hand side of this slide, you see how dust is tuned by optical depths, and we also can tune dust size distribution using IronNet. So at the end, when we compare to dust deposition, we see that up-to-date model underestimates dust deposition about 3 times. It means they underestimate deposition and emission. And here, so from the models, we use free-running models and reanalysis, MACC and Mirror-2 reanalysis. So all of them underestimate dust, and reason is more or less known because the models do not account for large particles. The largest particle that usually is accounted in the models is 20 micron in diameter, and this is not enough. So at KAUST, we have dust observations. We have for at least 15 years. For 12 years, we have IronNet. We produce use handheld sun photometer to measure optical depths over at sea, and we use micropulse LiDAR to measure vertical distribution of dust. So these 3 instruments are part of the NASA networks, and the data are available from NASA website. So we also measure dust deposition using this simple device that requires a lot of processing, and using this device we so measure size distribution of deposited dust, and of course so its mineralogical structure and dust distribution, so dust deposition in time. So for accounting physical effects, we use regional model WRF-Chem, and in this study, here you see so dust generation parameterization, where SP plays the role of size distribution of emitted dust. And we found that to account for coarse particles, we have to change the size distribution and account for giant particles. And what we did, we did in this paper, we increased emission of giant dust until 70% in comparison with 10% in standard runs, and we were able to reproduce observed deposition rate, blue and yellow you see on the slide. And if you look at distribution effect of fine and coarse dust on loading of dust in atmosphere, we see that despite giant dust is 70% emitted mass, it causes only 25% of loading. And most of the radiative forcing is produced by fine dust, and coarse dust produces very little. But if you look at the deposition, 80% of deposition is produced by coarse dust, and it increases total deposition to the about 3 times over land and 2.5 times over sea. And we can reproduce well optical depths. You see this here, the comparison with IronNet. We reproduce size distribution, and we have this blob of large particles that is not accounted for in IronNet. And so here our finding, so WRF produces relatively well the distribution of dust and its radiative properties, enhancing the emission of giant dust, caused a tripling of dust emission and dust deposition. Giant dust comprises 26% of atmospheric loading, 73% of emission, and 80% of deposition. So impact of giant dust on solar radiation about 10%. So the previous calculations in terms of radiation were relatively well done. So if you talk about deposition and mass balance, so it was missed so about 3 times. Thank you very much.
Thank you very much for these interesting results. I do have only one question. Given the importance of giant dust, especially that they are not in IronNet measurements for now, are there any perspective or discussions with IronNet in order to introduce these particles in their observation network?
So IronNet, I discussed this with Oleg Dubovik, who developed this retrieval algorithm for IronNet. We also cooperate with Oleg on retrieval algorithm for LiDARs, and we looked specifically for impact of coarse dust, and they want to modify the retrieval algorithm to include the retrieval of coarse dust particles. So this is understood, and so there are some work in this direction.
Great, thank you so much for your presentation. Okay, we'll move on to our next speaker, Adrienne Reynaud from Oberon France, and we'll be talking about also dust monitoring using IROTAPE. Adrienne, are you here? Hello? Is
Hello.
Adrienne with us?
Yes, can you hear me?
Yes, we can hear you, and your presentation is up, so please go ahead.
Okay, good, thank you. So first of all, I wanted to thank the organizer for the opportunity to present this work, and I will also thank the partners for this study, which are the Cyprus Institute and the LSCE, for giving us the ability to test our system. Sorry. Okay, our system in Cyprus. So the objective of this talk is to present some preliminary results about a campaign to test the IROTAPE, and the ultimate goal of this work is to be able to monitor dust particles. I will start with a quick word about Oberon. So Oberon Sciences was founded back in 2021 in March by 2 researchers from CA and CNRS, which are French research institutes. And we are currently a team of 10 people, and we are working on designing, developing, and operating environmental monitoring instruments. And so today I will speak about the IROTAPE, which is one of our instruments, which is based on the IRST standard, which is used to collect bioaerosol. And this is an online and mid-cost instrument that is able to perform real-time particle imaging, and from this it can build granulometry by seeing at the particles that it collects, but I will explain that in details a bit later. It's also a system that is connected to a network, and that can be used remotely, which allows us to install instruments in different places. So how does this instrument works? So it's both collects and perform the imaging of the particles on board and in situ. So it's equipped with a sampler and an impactor that collects the particles and impact them on a transparent duct tape, which is in green here. Once it's deposited, it's unlighted with different lighting techniques, and a picture is taken thanks to a microscope. So the objective that is currently on the T is a time 10 objective, sorry, and there is a stepper motor that allows the microscope to perform an autofocus. The duct tape is mounted also on steppers that allows the instrument to uncoil it in order to avoid saturation of the optical stage and to collect the particles and to save them in the box of the instrument, so they can be analyzed afterwards. Once the images are taken, they are sent to a server where they are analyzed, and it also collects weather data, because there is a weather station attached to the sensor. So this is the kind of images that can be taken. Here it's mainly pollens. So I think it's chestnut pollens, and you can see different lighting. The first one is the lateral lighting. The second one is the UV, and then there is a transmission lighting that allows to observe different features of the particles. And we believe that thanks to these various lightings, we will be able to detect the different dust particles. For now, it's used for bioaerosols and mainly pollens, and an AI algorithm is used to classify them. And the first step that we address for dust monitoring is the accuracy of the concentration measurement. And the first test we've done was here at Oberon on the balcony, using several instruments that you can see on the picture here, together with a FIDAS. And you can see on the right the time series showing the difference between the concentration that have been measured by the FIDAS and the concentration measured by the aerotape. So this is the data for 5 to 10 microns, and it shows a good agreement. And we kept going with this experiment by installing one in the Cyprus Institute and the Atmospheric Observatory, where we compared the measurement of the aerotape with the one of the TIOM and the FIDAS instrument that are reference instrument for aerosol concentration measurements. And again, it shows a good agreement, and the trends are very consistent. So here is the comparison with the concentrations, and here, if we zoom down on this event, we can see that as the instrument is based on image processing, we can observe the image for every concentration, and you can see that for the peak there is a high number of particles that is actually observed, which decreases with the concentration. So the next steps will be to address the source apportionment. Now we have the images of the particle for every concentration, but we want to know exactly what particles should be associated with, if it's Saharan dust particle or if it's sea salt. And this will be the next steps. So as a conclusion, and to sum up what has been said, the method was based on image analysis, and the measurement have been compared to reference instruments, and showing good results. And the next step will be to develop or at least optimize the microscopy techniques that are currently on board of the instruments, to produce a labeled particle, so that we can train an algorithm later on, and then optimize the hardware and implement everything in an instrument to do real environmental tests, which will also be compared to chemistry analysis to label particles, and probably perform another loop to better optimize the classification algorithm. And with that, I would like to thank you for your attention. And if you have any question, don't hesitate to ask them now or to send us an email. Thank you.
Thank you so much, Adrian. I don't see questions in the chat. I do have one. Do you think these filters are, or the instruments tape are adapted for arid regions where the emissions are much higher and the positions are much higher than in France, for instance?
So that's exactly the objective of the next campaigns. It will be to adapt the instrument to harsh conditions. It is both for the high concentration, but also for the high temperatures. But yes, since we control the encoding of the tape and the sampling time, we can by increasing the velocity of the tape and reducing the sampling time, we can address this high concentration.
Okay, great. Thank you so much.
Thank you.
Okay, then we move on to our next speaker, Dr. Fragiskos Kikou from Greece. And he will be talking to us about exploring heat stress impact on human health. Are you with us? Hello?
Yes, hello.
Hi, yes.
Can
we
you
can
hear
hear
me?
you and you're, yes, perfect. You can go ahead, please.
Okay, thank you. Hello, everyone. My name is Fragiskos Kikou. I'm a postgraduate student at the Aristotle University of Thessaloniki on the program of Meteorology, Climatology, and Atmospheric Environment. I was an intern for the summer internship project of the Cyprus Institute with Theo Economou and Georgia Lazglou in order to help me complete my thesis, which is about heat waves in Cyprus and exploring the association of heat waves with heat stress and public health with my professor Christina Agnostopoulou. So today I will present to you some of my results. I like to divide my thesis into 4 sectors. The first one is about the climatology in terms of temperature, and next the heat waves or extreme warm periods, as I prefer to say. So for both of these sectors, we use grid temperature data from the ERA5 land dataset that covers the period from 1979 to 2019. And the heat stress was studied by using the Universal Thermoclimate Index that was extracted from the ERA5 heat dataset. And last, the health part was studied by using the mortality and morbidity data that we had in our disposal from the Health Monitoring Unit of the Ministry of Health and the Statistical Service of the Republic of Cyprus. These data cover the period from 2004 to 2019, and the aim was to find an association with heat stress in order to find future projections. So starting with climatology, a trend analysis was performed, and as we can see here, Cyprus presents a gradual increase in maximum, minimum, and mean temperature for the last 4 decades. Since our health data covers the period 2004 to 2019, a further trend analysis was performed by dividing our period into 2 subperiods from 1979 to 1999 and from 2000 to 2019. As we see from these box plots, the 2000 to 2019 period exhibits a shift in the whole distribution, and particularly for the high extremes. Next, we did the same thing, but in a monthly analysis where we can see the same thing. And moving on to the heat waves, we studied them by using the extreme temperature days, which are the days where the daily maximum and minimum temperature exceeds the 95th percentile for the warm months of Cyprus, which are considered from May to September. So what we did is that at first we calculate the temperature threshold for maximum and minimum temperature for each grid point and each month in order to estimate the total number of extreme temperature days for each grid point of each month. So from this animated picture, we can see that the maximum number of extreme temperature days, surprisingly, is located in the western part of Cyprus, which is a mountainous area. And also we can see that June and May has the maximum total number of extreme temperature days. So this is probably explained by the fact that for this particular area of Cyprus and also for those specific months, the temperature thresholds are lower, so they were more prone to be exceeded in the case of an early heat wave in Cyprus. Then we studied the number of extreme temperature days in Cyprus by month in order to estimate the specific years and months with the highest number of extreme temperature days. And also we found out that July is the month with frequent occurrence of high number of extreme temperature days. Then moving on to the heat stress was studied by using the UTCI, which is used to describe how the human body experiences atmospheric conditions. Its value depends on the temperature, humidity, wind, and solar radiation. And the choice of UTCI was not random, as according to the literature, it presents the best biothermal conditions for human beings compared to other indices. What we did is that we chose 3 different grid points in Cyprus on the same latitude that represent different geomorphological characteristics of the island in order to estimate the yearly frequency of UTCI heat stress categories. So starting from the left to the right, the grid point number 23 describes the mountainous area, number 25 describes the interior of the island, and the number 27 describes a coastal area. From the conversion of these 3 grid points, we can see that the interior of the island, as it was expected, has the highest percentage of the strong and very strong heat stress category. But despite this, we can say that for all the grid points in Cyprus, for the 50% of days, people experiences heat stress, even if it is for the lower category, which is the moderate heat stress category. So in this table, we can see the cases of the most severe extreme temperature events as they arise by taking into account the duration, intensity, coverage in terms of grid points and heat stress. From this table, we can see that on July to August 2010, we had the maximum temperature and heat stress value, which correspond to the extreme heat stress. And also we can see that on the same period, a few days later in August 2010, we had the maximum duration of extreme temperature days on 12 days, 12 consecutive days. Then moving on, in this table, we have the same years and months or cases for the previous table where we had the most severe cases. And what we did is that we divided each month into 3 sub-periods of 10 days duration in order to estimate the correlation of the daily maximum UTCI with mortality and hospital admissions. From the results of this table, we can see that there is a certain positive correlation, but this correlation depends on the month and on the year, but we can see that in some cases, it does not succeed to capture any significant correlation. So having that in mind, this motivates us to use some more sophisticated statistical methods, as GAMS, which are the generalized additive models, in order to capture the relation, which is non-linear, between heat stress with mortality and morbidity data to estimate future projections of relative risk for people in Cyprus.
1 minute left.
Thank you for your attention.
Perfect time.
Thank you so much for your presentation. No questions from the audience. I wanted to ask you if you had actually looked into the combination of heat and humidity, because we know in most of the countries in our region, it's mostly the humidity that is, causing extreme stress on public health.
Yes, that's why we chose the UTCI, because UTCI it's a biothermal index that concludes humidity in the estimation of the UTCI value.
Mm-hmm. So basically, humidity is included in your
yes.
in your result. Okay, thank you so much.
Thank you.
Okay, we move on to our next speaker, and the last speaker of this session will be Dr. George Zettis from Cyprus Institute. And he will be talking about...
Sorry to interrupt. We have one more speaker after George Zettis. We have Jocelyn after George.
Okay. Sorry. Yeah, that's right. Sorry about that. So now our speaker is George Zettis, and he will be talking about drivers of accelerated warming in the EMME region. George, are you with us?
Yes, can you hear me?
Yes, perfect. Go ahead, please.
Good afternoon, everyone. My name is George Zettis. I'm working at the Climate and Atmosphere Research Center of the Cyprus Institute, and today I'm going to talk about a study which is entitled Drivers of Accelerated Warming in Mediterranean Climate Type Regions. And most of this analysis was in the framework of the master thesis of Diego Diales Flores, who was a talented student, master student, who is now pursuing a PhD in Switzerland. I would like to thank also the several contributors to this study, many of whom are together with us in the panel. So the motivation behind this study, we have seen in many studies that the broader region of the Mediterranean is warming faster than the global average warming rates, and actually faster than many other inhabited parts of the world. And this is the case particularly for the last 4 decades. So we wanted to look in more detail what has caused this acceleration that we see mainly after 1980s. Also some modeling studies and future projections, as we see here on the bottom left, they show us that this warming amplification will continue, will manifest also during the rest of the 21st century. So our main objective is to make an updated assessment of temperature trends, both global and also in the regions that are characterized as Mediterranean climate types. And we will see later that these climate regimes is not only found in the Mediterranean, but in other parts of the world, for example, Northern America, Southern America, Southern Australia, and limited parts of Southern Africa. So we updated this trend assessment for the last 120 years and also the last 40 years where we see this warming acceleration. We wanted to design a temperature reconstruction model, which is described here in the bottom right. And this is not very sophisticated, but it's quite efficient model. It's based on multivariate lagged regression, allowing also interactions between the predictors. And we did this in order to decompose the contribution and quantify the contribution of its temperature driver. And finally, we want to assess the relative importance of these drivers. We've used monthly data of temperature. We use the CRU credit observations. And for the temperature drivers, our predictors, we included well-mixed greenhouse gas radiative forcing, the total solar irradiance, and the multivariate ENSO index. These 3 are global drivers, whereas we also consider 2 regional drivers, which is the soil moisture based on the ERA5 reanalysis, and the total AOD to see the effect of aerosols. And this is again based on reanalysis data, the MERA2. And here I must also say that before the analysis, we removed the seasonality and we considered also some time lags based on the literature. Let's move to some results. And here we see the updated trend analysis. With the blue plots here, we see the global trends. With red, the global Mediterranean regions, and the individual Mediterranean climate type regions with the orange box plots. And we see that for the, if we consider the last 120 years, the trends are quite similar between the Mediterranean and the global trends. But if we see in the bottom plot and we focus only over the last 4 decades, we will see that we notice an accelerated warming that is mostly evident in the Mediterranean region. And this current trend is about exceeds 0.4 degrees Celsius per decade. And this is quite stronger compared to the global trends and also to the global Mediterranean regions average. And here we see the relative contribution of the different temperature drivers as derived from our reconstruction model. And we see here with the orange and red colors, the global Mediterranean climate type regions that we've described before. And here we see the percentage of variance explained by each temperature driver. And we see that the warming caused by the greenhouse gases is dominant through all Mediterranean climate type regions. For example, for the Mediterranean, we see an increased component of the AOD trends and also soil moisture. The regions that are adjacent to the Pacific, we see an increased contribution also from the ENSO, where we see a stronger signature of contribution of ENSO to the variance explained. Let's have a closer look to the Mediterranean basin, which is the region that shows the strongest warming. And we see here the observed trends with the black curve, and the orange represents the reconstruction from the model. And we see that there is a quite good agreement, and the model is able to represent quite well about 90% of the observed variance. And on the bottom panels, we see the contribution of the different drivers. And as I mentioned before, we see that the radiative forcing of the well-mixed greenhouse gases is quite dominant. This is the case for all regions, and this is estimated to about 0.2 degrees per decade. 0.2 degrees Celsius per decade. We see also a quite important trend with respect to the contribution of aerosols, and here we include both anthropogenic and natural aerosols. For example, we see here a strong cooling due to large volcanic eruptions, and we see an overall positive contribution, which is mostly related to the reduction of anthropogenic aerosols over the last 3 to 4 decades. We see a quite significant trend related to soil moisture. So this is a feedback which is well known in this type of climate zones. When there is a decrease in the rainfall and soil moisture, we tend to have positive contribution to temperature due to reduced evapotranspiration. So this is another important contributor to this warming acceleration. Other global drivers such as ENSO and total solar irradiance are not so important, and we do not see very strong trends. This is the final slide where we look in more detail the contribution of soil moisture. Here we did a composite analysis. So we saw temperature anomalies during the driest and the wettest years of our time series, and we see that mainly the northern hemisphere, we see that indeed during the driest year we observe quite positive temperature anomalies. And on the right plot we see that we analyze some observations of sulfate aerosols, quite long time series from Phinokalia and Athens stations in Crete. And again, here we demonstrate that these time series are anti-correlated with the trends of temperature, giving us additional hints that the aerosols can also contribute to this recent warming acceleration in the region. If you are more interested to this result, please you can have a more detailed look in this recently published article in Nature Partner Journal Climate and Atmospheric Science. And here I would like to thank you for your attention. Thank you very much.
Thank you very much, George, for the great presentation and results. I do not see any question in the chat. I do have one question. When you consider the radiative forcing of aerosols, are you considering also up to the stratosphere or only troposphere?
Actually, here we analyze the time series of AOD, so it's not we didn't explicitly study the radiative effect, but it's the total column AOD that we considered.
Okay, thank you so much. Okay,
very
thank you.
much.
And we move to the next speaker.
Thank
Dr.
you. Yes, I'm Jocelyne Gerard. Do you hear me?
Gerard from sorry?
St. Joseph University. Do you hear me?
Yes, yes, please. Go ahead.
Okay. So this research is part of an Archbam project led by the University of Rouen. This multidisciplinary project brings together researchers from France, Lebanon, Cyprus, Germany, and Belgium. One of the objectives of this project is to understand the spatial structure of meteorological parameters, such temperature and precipitation, because the final aim is to reconstruct the spatial variability of the past climate. Well, we are interested by the evolution of this spatial structure. And finally, we have to identify the hottest periods to meet another objective of the project, which is identify the cause of the triggering of certain disease. But this understanding must be done on a fine scale, even on a stationary scale. But when we work at this fine scale, we are facing multiple problems. This slide summarizes all the problems that need to be solved because we need to work at the scale of a meteorological station. To illustrate my talk, I will take as an example the Larnaca case. Here, as you can observe, that if we want to understand the trend, the evolution of the temperature, we see that the temporal period is important to take into account. It is very well known. So you see that the trend at the first figure is not the same that the NCDC data. But if we take only the same period from 1970 to 2000, we see that the trend is almost the same. But when we have interruption in data, we have to homogenize the information. It is a recommendation of Météo France and all the meteorological institutions. Well, here, if we homogenize, we are facing another problem, excuse me, because as you can see, with homogenized data, we observe no trend. So the question, why? Is it the methodology that we have adopted? We don't know. And finally, we analyze the trend of all stations. And as we can see that almost all the station doesn't have significant trend. This is the first problem we are facing. Now, the second part of my presentation is based on the NCDC data to understand the trend and to identify the hottest day. Well, here I saw it is interesting to compare the trend of the beginning of the 20th century with the actual data. What we can see that in the beginning of the 1900s, we observed no significant trend. We can even note a slight decrease. Currently, the trend towards thermal rise is clear, but the trend of Nicosia is not the same of that of Larnaca. Now, if we focus on the deviation to the average, we can see that at the beginning of the 20th century, the difference were small with an annual variability. Currently, we notice a clear increase of the difference. And in Nicosia, the deviation is more important than in Larnaca. Finally, if we look at the number of hot days, we notice an increase, whatever is the station. Two remarks. At the beginning of the 20th century, the numbers of days decreased and then increased since the 1920s. But the trend is increasing continuously since the 1970s. However, we can make a remark. Larnaca, unlike other stations, is experiencing a decrease. Why? Is it due to data quality, change of station? We can ask such questions. Finally, if we only retain the maximum value of numbers of consecutive days of heat, we observe that in the beginning of the 20th century, we reach an episode of 10 days. Currently, the number of consecutive days is increasing in all stations with a peak of 45 days. In the end, we wanted to know if the dates of heat episodes were common to all stations. In fact, the results show that out of more than 1,800 events lasting more than 2 days, there are only 600 episodes common between 2 and 4 stations, which means above 30% of the event. And 6% have common to 3 to 4 stations. So how can we explain the spatial variability of these results? In conclusion, what I want to say, if we want to work at the scale of a station, we are facing many problems. First of all, we have many different sources for one station. So we must justify the choice of the type of the data we are going to use. Secondly, we have different trends from a station to another. We have also a spatial variability of annual number of heat waves. Why? First of all, we can say it is the quality of the data, but we must explain those differences according to location, according to the environment. Are they near cities? What is the effect of the urban heat island? So we need to explain those changes before spatialization, especially if we want to integrate archives data. And finally, one of my perspectives is to compare Cyprus, which is a mountainous island, with Lebanon, which is a mountainous continental country. Thank you.
Thank you very much, Jocelyn. And Diana had to go, unfortunately. Dr. Diana had to go. So I think now we have a 10-minute break. So let's say it's 2:45. We should be back in 10 minutes at 14:55 to start with the next session about new instrumentation and research infrastructure. So we should be back in 10 minutes. Thank you. Let's see if Professor Salwa Hassan is here to chair. Ah, there she is, lovely. So the chair of our next session, the new instrumentation and research infrastructure, is Professor Salwa Hassan from the National Research Center in Egypt. So I will give the floor to the professor.
Thank you, Lini. Hello, everyone. Thank you for the organizer. And I would like to thank you for giving this chance to me to be part of this important event. The first speaker in this Institute.
Hello, everyone. Can you hear me?
Hello?
Hello, can you hear me?
Hello?
Yes, yes, we hear you.
Okay, great. There seems to be some interruptions of Professor Hassan, so I'm not really sure if you can hear me well.
Yes, yes, we hear you well.
Elena? Are you Elena?
I cannot see my screen and my presentation though.
No, we see it. We see it.
Yes,
I see it.
Please start.
Okay. So the motivation for contacting this work.
Problem with the electricity.
Oh my God. Can you hear me?
Yes.
Yes, Rubina, go ahead.
With Professor Salwa's
Yes,
correction.
go ahead.
So my work would be about the spatial and temporal urban air quality variabilities using the Vaisala air quality monitor. The motivation for conducting this work is, of course, the need of continuous measurements of urban quality, urban air quality, but there seems to be a problem due to the limited spatial distribution of air quality monitoring stations. And the reason for that is the high capital maintenance cost of the reference instruments. So we now use low-cost air quality sensors, which have been evolved rapidly over the last few decades. One category of low-cost sensors are the electrochemical sensors, which, due to their fast response and high enough selectivity and sensitivity, they are often used for air quality measurements. But the problem with these sensors is the poor quality of their data, which forces sometimes the end users to use calibration and post corrections to improve the quality of the data. Recently, Vaisala has commercialized an integrated system which uses custom-made data acquisition and calibration algorithms to correct directly the raw signals and provide concentrations. And here you can see an image of the internal space of this monitor, the AQT 530, which comprises with several electrochemical alphas and sensors, and an optical particle counter giving information of PM2.5 and PM10 mass concentrations, along with a temperature and relative humidity measurements. So the objectives of this work is to evaluate the ability of these monitors to capture spatial and temporal gradients along the city, and to examine whether they provide similar observations to those captured by the reference instruments. As you can see on this map, which is the Nicosia map, we have installed two monitors, one at the traffic station and one at the urban background station, and we try to see their behavior at both stations.
We managed to have 19 months of continuous measurements at both stations for CO, NO2, NO, and ozone gases, and you can see their behavior against reference observations, as well as PM2.5 and PM10 measurements from December 2021 up to June 2023. Moving on to the results. Here are the behaviors of the low-cost sensors for the urban background station, and on the right side you can see the same for the traffic station. As you can see at both stations, the CO low-cost sensors by SALA had the best performance. It showed good agreement and the highest correlation compared to the rest of the sensors with reference measurements. While the rest of the sensors had poor performance as well as low R-square, and especially during high temperature seasons where all gas sensors seem to have degraded performance. And last but not least, the PM measurements tend to underestimate the reference observations, except during major dust events where they experienced higher mass concentrations and larger particle sizes. Moving on to the monthly variability of the sensors, as you can see with solid lines, you have the reference observations for traffic station with blue and orange for urban background station, while with dashed lines you can see the Vaisala measurements at the two stations. They capture well the variability of the reference measurements along the whole measurement period, and they also correctly indicate which station measures the highest CO concentrations. Regarding ozone sensors, they also follow the reference trend, but they tend to over-predict ozone concentrations during the high temperature seasons. They are also not capable to identify which station has the highest ozone concentrations. Regarding NO2 and NO sensors, they show opposite trend to that of the reference instruments, but nevertheless they are capable to distinguish significant differences between the two stations, as well as capture which station has the highest NO2 and NO concentrations. PM10 and PM2.5 sensors, they also follow the trend from reference measurements, but they fail to show which station has the higher PM concentrations. Moving on to the diurnal variability, all low-cost sensors seem to behave better during work days and cold period rather than weekends or hot period. And the reasons for that is due to their deterioration of their performance caused by the high temperatures or due to cross sensitivities with other gaseous pollutants. Regarding the PM2.5 and PM10 sensors, they also have the same behavior, meaning better performance during work days of the cold period rather than the hot period or weekends. To sum up, the CO low-cost sensors exhibited the best performance. They capture accurately the concentrations and spatial variations of reference measurements. The NO2 and NO sensors have a monthly behavior that is opposite to the reference measurements, but they show which station has the highest concentrations. The ozone sensors follow the reference variability, but over-predict during high temperature season. The NO2, NO, and ozone sensors capture to a good degree the spatial and temporal variabilities. And last but not least, the PM sensors follow the monthly trend of reference measurements, having better performance during dust periods rather than non-dust periods. Thank you very much.
Okay. Thank you, Rubina, for your presentation. I can't see any questions in chat.
There are no questions in the chat now.
Okay. Okay, we will move to the next presentation. The next speaker is Andreas from Cyprus Institute. Andreas, are you here?
Yes, can you hear me? Hello?
Yes.
Okay, okay. Okay. You can start. Okay.
Yeah. Yeah. Good afternoon, and thank you for the very nice workshop organization. Also, thank you for the very interesting presentation from colleagues. My name is Andreas Savvidis, and I'm representing a multidisciplinary team of researchers here in the Department of Agrobiotechnology of the Agricultural Research Institute in Cyprus. Today, I will be introducing our infrastructure for greenhouse gas emission surveillance in Cypriot agriculture. Actually, the infrastructure is built to serve the aims of the project monitoring and reduction of greenhouse gas emissions in agriculture in Cyprus. The project funded by the Cyprus Recovery and Resilience Plan and Next Generation EU. The project aims to significantly improve the monitoring of greenhouse gas emissions from agricultural practices and contribute to reducing these emissions. Also, to achieve that, we need to properly quantify GHG emissions from important crops, firstly, then identify and rank the main driving forces for these emissions, and through that provide mitigation measures and suggest mitigation strategies. To substantially quantify carbon dioxide, methane, and nitrous oxide emissions, several sets of high-frequency soil chamber systems were assembled. We can see a part of them in the picture on your left. Each system is primarily consisting of 12 automated non-steady-state soil chambers connected through a multiplexer with gas analyzer. And each chamber is closed for some minutes, and the changes in gas concentration within the chamber are recorded, providing high-frequency data. The raw data are then inserted in an in-house developed algorithm, providing automated and accurate flux calculation and temporal upscaling from instantaneous to deep fluxes. Here you can observe our first raw results from the very important for Cyprus potato crop from an experiment conducted as shown in the picture in 2023. The instantaneous carbon dioxide fluxes shown in the figure here are based on 24,000 measurements over 167 days from 12 chambers, placed in 3 different treatments that represent different strategies of calculation. Each chamber was taking 12 instantaneous measurements per day, covering in this way different time slots within a day, and thus providing high temporal resolution data. Briefly, and as can be seen in the figure, our methodology provides the accuracy and temporal resolution necessary to quantify greenhouse gas fluxes and relate them to the agricultural practices performed and also to temporal crop changes. Our laboratory of agricultural chemistry is equipped with necessary personnel with can see in the images, and facilities to quantify physical and chemical parameters, like the one seen in the slides, like soil organic matter, soil texture, and so on, related to greenhouse gas emissions. Additionally, our molecular biology and agricultural microbiology laboratories, driven by experienced researchers, are equipped with instrumentation such as qPCR and shotgun next-generation sequencing, facilitating valuable insights into soil microbe communities and functions related to greenhouse gas emissions, such as methanogens, nitrifiers, and denitrifiers. Lastly, but not least, the Agricultural Microbiology Laboratory is equipped with a controlled environment experimentation facility, as you can see in the image on our right, allowing microbial studies to evaluate greenhouse gas emissions, soils, and different types of fertilizers. Concluding, the importance of such cutting-edge infrastructure lies in their capacity to provide data and insights needed to monitor and reduce greenhouse gas emissions, promote sustainable farming practices, and of course contribute to the global effort to combat climate change. Thanks a lot.
Thank you so much, Andreas. Also, I can't find any questions in chat.
There haven't been any questions, so we can proceed.
What?
There haven't been any questions in the chat.
Okay, it is not appear for me.
There haven't been. There is no questions. There are no.
Okay. I have a big problem in electricity. It is the cut off in our area. So you may, at any moment, you lost connection with me. Okay?
No problem. Thank you for letting us know. It's okay. You can continue as long as you can.
Network is very, very bad here. Okay?
No problem.
Okay, thank you. Thank you. Marcus, the next speaker is Marcus, yes?
Yes. Hello, I'm here. I hope you can hear me.
Okay. Marcus, are you?
Okay, perfect.
We can hear you. We can hear you. You
Awesome.
can start. Thank you.
All right. Thank you very much for the opportunity to talk here today. I'm going to present you our new Caron Fusion PTR TOF, and that my colleagues and I developed and used for conducting the measurements of condensed polycyclic aromatic hydrocarbons down to the low picogram per cubic meter levels. So first, let me start with a brief overview about the polycyclic aromatic hydrocarbons. So these are compounds that have 2 or more aromatic rings, like you can see on the left side, like naphthalene and benzopyrene. These are a concern for health, and they form due to incomplete combustion of organic materials, like in wildfires, and then they are condensed on aerosol particles and experience long-range transport until they are deposited. Here's a picture where you can see the Valley of Innsbruck. I took this picture on October 3rd, and what you can see is particles in the air. These are particles that arrived from the Canadian wildfires, just as an example. And now I want to show you how we measured those PAHs. So here's our Fusion PTR TOF that we used, and it's a proton transfer reaction time of flight mass spectrometer. So this means it consists of a new improved ion source, where you can select a set of reagent ions for ionization of the analytes. Here's a new fusion radiofrequency reaction chamber operating at low pressure, and there's our time of flight mass spectrometer with a mass resolution of more than 10,000. And you have an inlet where you can selectively analyze compounds from the gas phase or from the particle phase. So the principle is that we have H3O plus reagent ions, and under well-defined conditions, these do react with the VOC under a proton transfer reaction. This results in a protonated VOC, which is then detected by means of mass spectrometry. And the detected VOC signal is then just a simple function of the mixing ratio of this VOC. And yeah, so we improved this instrument and reduced the inlet flow to allow coupling with a Charon particle inlet. And so the Charon particle inlet consists of a gas phase denuder. This removes the vapors in the gas phase. And then this is followed by an aerodynamic lens system where we collimate the particle beam. The neutral gas is pumped away so that we enrich the particle, particles. These enter then the thermodesorber where they are vaporized at reduced pressures. The resulting vapors are then transferred into the PTR-TOF-MS and analyzed by proton transfer. So for this study, it was beneficial that we had this particle enrichment due to the aerodynamic lens system, and we benefited from the enhanced sensitivity of this new fusion PTR. And so now let's move over to the sampling side. So we simply measured outside of the window from our company in Eastern Innsbruck. This was the measurements were conducted in August this year, and you can see from the figure that we had a high pressure system which provided us stable and low speeds of wind at elevated temperatures. And here's a picture of the time series showing the mass concentration over time. You see that during these 11 days, the most abundant fraction of the particle composition was the total organics, and only minor contributions from ammonium and nitrate were detected. What you also can see is that over the period of this measurement time, that the particle mass concentration accumulated until there was a change in weather on the weekend, where you see a drop in the mass concentration. So now let's move on to the compounds of interest, these polycyclic aromatic hydrocarbons. So in the data set, we had a look at the mass spectra, and we could identify about 7 ionic signals of these PAHs. As you can see with a mass resolution of 14,000. These are quite complex peak systems, but even though we were able to design the sum formula, so here we have 3 examples of those compounds. And now I would like to show you the time series of these compounds. So here you see the mass concentration. Overall, this ranges from 0 up to 11 nanograms per cubic meter, but typically most of them appear below 1 nanogram per cubic meter. And highest intensities were found for C20H13+, which could be benzopyrene, for example, or benzofluorantane. Then also, which is remarkable, that we achieved 3 sigma limits of detection at 1 minute integration time for a width of 46 picogram per cubic meter for C24H13+, down to 19 picogram per cubic meter for C24H15+. And yeah, so this is pretty good. And now let's have a close up at these spikes, because here you can also see that the dynamics of these particles is also nicely captured at a high time resolution. So with this, I would like to come to an end and give you a brief outlook about the matrix factorization that we applied. So on the right slide, you see the time series of the compounds of the particle mass concentration, and the dominating factors were the fresh biomass burning OA, then also due to the accumulation of the particle mass concentration over time, the mixed aged oxidized organic aerosol, and then from our colleagues, some cigarette smoke organic aerosol factor. And you can see on the left side of the figure that some factors are dominant for all of these PAHs, like the fresh BBOA, but then some factors, some compounds are only appearing for specific factors. All right, yeah, with this overview, I would like to thank you very much, and I look forward to answer your questions.
We have one question in the chat from Gerbel. Very nice work. How does it compare to the traditional sampling analysis method of PAA?
So from my knowledge, I can only compare to filter-based sampling methods. And so this means here we don't have a filter. We just sample the particles in real time, and these are continuously sampled and vaporized. So what you get is you don't need to accumulate particles on the filter, which could introduce also some sampling artifacts, maybe due to ozone or other radicals, for example, or aging. So this is just the instant picture that you get from the aerosol composition. And we have detected also about 4,000 peaks in the whole mass spectrum. So there might be also a lot of other stuff hidden, so that you don't only detect the pAHs, but also other compounds that are also existing. Yeah, I hope this answers your question.
We have one more question for you, Marcus, from Minas. Very nice work. At this resolution, can the instrument distinguish compounds of similar M-to-Z ratios?
I think this question is related to isomers, if I'm correct. So we have so this instrument has not an isomeric separation method at the moment. So yeah, at the moment we just have some formula, and yeah, so that's all we have at the moment. Yeah.
Thank you, Marcus. Salva has an issue with her connection, so Professor Rafik will continue.
Okay.
Thank you, Eleni. Thank you, Marcus, for the presentation. Now we will move to Nina Sarnella from the University of Helsinki. And she will talking about Actrice.
Yes, thank you.
Okay, so Nina, the floor is yours. If you can just share your.
Thank you. I hope you can. Can you see now in which mode?
Yes, great. Thank you.
It's in the presentation mode. Okay, good. So hello everyone, I'm Nina Sarnella from University of Helsinki, and I come from Actrice, a University of Helsinki unit, and I hope today that I could tell you something about how our topical center units can support the measurements of secondary aerosol formation also in the EMME region. First, I'm going to say something about what is Actrice. We heard something, it was mentioned already before today, but just as a recap, that Actrice is an aerosol, cloud, and trace gas research infrastructure, and we aim to produce high quality data and information on the short-lived atmospheric constituents and the processes of them. And we focus on the measurements in situ measurements and also remote sensing measurement techniques, so that there's more than 100 different atmospheric variables that are included there, and huge amount of data products about the composition and properties and processes in the atmosphere. We have different services, and in practice it means that we have free access of this high quality long-term atmospheric data through our server, and then there's access to different facilities such as chambers and also field stations and mobile platforms. We provide training for the instrument operators inside Actrice, but also outside Actrice. Then we provide measurement guidelines and quality assurance and control tools. Those are also available for everybody to use. Then there's instrument calibrations and data quality monitoring. Then if we look at where is ACTRIS currently, so there was 22 countries in the planning phase, and now this year we started ACTRIS ERIC, and there's currently 17 countries in that, but still some more countries are aiming to join in. And looking at this region, there's Cyprus and Greece involved in ACTRIS. And the leading country where we have the head office is Finland here, where I'm also at, but all the facilities are distributed to very many different countries and places. Then the core of ACTRIS are the national facilities. So those are the places where the data is coming from. So they are the field stations, but also the mobile stations and the chamber units or laboratories. And if you look at the map, they are quite well in Europe, but there are also some stations around. And if we zoom in into this region of EMME, there are several stations in Greece and also in Cyprus. Now, actually, the names of the countries are in Finnish. Sorry about that, but you know the map, so it doesn't bother you probably. So currently there's 123 stations and platforms that are waiting to be officially labeled to be as ACTRIS national facilities, which are the stations where the data is then coming to the website where everybody is able to use and download and look the data from. Then to the topic, sorry, I'm going the wrong direction. The topical centers where I'm working as well. So the topical centers are responsible of really defining the procedures and the tools for the quality assurance and quality control of ACTRIS measurements and data. So that when we have these more than 100 different stations, that we do the measurements everywhere similarly, so that we can really compare the data between the stations and understand that they are measured similarly and that we can really do the comparison and see the trends. So the topical centers are divided between aerosols, clouds, and trace gases, and in each of them there's in situ and remote sensing part. And these topical centers do also the labeling of the stations, the national facilities, and we link to the associated scientific communities, such as this EMME as well. And we also provide the training and transfer knowledge to all the users and operators of ACTRIS. So it's really the topical centers that are in the key role of sustaining the high level of the ACTRIS data and the measurement techniques and methodologies in atmospheric research. So we have in Helsinki 2 center units. One is focusing on the sub-10 nanometer aerosol particles. It's called CCC, Cluster Calibration Center, and it's here in Helsinki. And then we have another unit focusing in condensable vapors, which are measured with high-resolution mass spectrometry. And that's where I'm mainly working with. And we have many people working here, but 3 people in like that are doing this for their first main job. So what do we do? So we really aim for the standardization, and the ways to get to there is doing the labeling of the measurement sites, so the national facilities, and then bringing these different kind of measurement guidelines, quality control procedures, standard operation procedures. We provide calibrations, method development, and the training, and also consultancy for the instrument users, doing measurements with condensable vapors and also the sub 10 nanometer particles. We also this year have started our intercomparison workshops. Right now we have one of them ongoing with nanoparticles, and actually Cyprus, Cyprus Atmospheric Observatory has been involved in all of the 3 intercomparison workshops that we have had this year. One was for the condensable vapors, one was with nice instrumentation, and this one is with the nanoparticles, which is right now ongoing. So they really give us more information about how the individual instruments are working and how well we can get the same results when we do the intercomparisons and the calibrations together. So this was a small summary of the things that we do. So as said, we have 2 of these topical center units here in Helsinki. You can see the contact information on the screen. Please contact us if you have any questions or any ideas what we could do and how we could help you in your field stations or other instrument issues. Thank you for your attention.
Thank you, Nina, for the presentation. So I have some questions, in fact. So practically, we saw that, and you said it, that there are some stations outside Europe. So one in South America, another one more in Central Asia, and so on. So how did you choose, and why did you choose these? That's the first question. And the second question, and in Africa and so on. And the second question, do you intend to expand outside Europe, like in the Middle East, not only the East Mediterranean? If yes, or is there any possibility for these countries, for research groups in these countries in the Middle East to apply or host some stations, and how it goes? What is the administrative procedure?
Yes, I think this is a big question in Actris now, that we are really thinking about the ways how we could expand also outside of the Europe. The thing how it, of course, it was an EU project in the it has been an EU project, so it has started in the EU region, but there is discussions and thinking about how it could be expanded also and being included also in other places in the world. And the stations that currently are in the map, the national facilities, so those are the ones that are actually, so that some European countries have some, they are doing measurements or running a station somewhere there outside of the Europe. So basically they are also run by European countries, or not the whole station, of course, probably, but some part of that. But yes, it's a big question now that is under discussion, how to also include other countries. And I think there are some initiatives happening in the years to come, but of course you can contact the Actris offices also to discuss about the issues if you are interested about it and how can it be done. And many of the things that us in topical centers do, those are also available to countries outside. I mean, these calibrations or training or consultancy, these kind of things are also available to stations outside Actris. it's just like the priority is the Actris stations, but it's also available for others. Thank you for good questions.
Thank you, Nina. So a follow-up question. So you said that the services, or let's say the calibration and so on, like these kind of activities are also available for outside Actris, outside even Europe. So is there a project that, let's say, funds for calibration and so on for this kind of infrastructure for research groups outside Europe, or no, it is a service that is paid by the people that want to send, for example, their instruments for calibration and so on, or for training or whatever? Or are there any let's say any type of fund that the research groups can get for this kind of activity?
Yeah, for example, for the joining like in the comparison or this kind of thing, Atma access or this kind of access applications can be used, and I think they are just suitable for people outside Actris. It's not possible for groups inside Actris. So that kind of access could be applied for Actris in the comparisons or calibration workshops, for example.
Okay, thank you, Nina. There's also still one question that we got. So what is the relation between Actris and ICOS?
It's a good question, and of course there's a lot of things as ICOS is also the headquarters here in Helsinki. So we have been maybe looking them because they started earlier than us. So we have looked them as a model how they have done many things. So we have very similar kind of procedures and these kind of things. But yeah, they are focusing just to different things what we look in the atmosphere. So we are working in side by side, but just the target compounds and the target things that we are focusing on are different, as we are looking at the aerosol clouds and trace gases, and they are working for greenhouse gases, for example.
Okay, thank you, Nina. So with that, we come to the end of this session of new instrumentation and research infrastructure. So Eleni, back to you now.
Great. So I think we're going to have a break now. We're going to have it until the planned time to come back. So we'll have a break until 4 o'clock, where we're going to have our last invited speaker. So we're going to have a 20-minute break, and we should see you all back at 4 o'clock in 20 minutes, in case you're in a different time zone. Thank you.
All right.
Hey, Tariq.
هلو
هاي طارق،
هلو كيف الحال؟
ماشي الحال وانت؟ منيح؟
تمام.
Like we still have till 4 o'clock, okay? We still have like 12 minutes before we begin because Litchi is in the US, and so 4 p.m. our time is 8 a.m. his time, so practically he won't be able to begin before that. Okay, so we will begin again at 4 p.m. So in 11-12 minutes.
Yeah. Well, I am here.
Okay, great. Thanks.
Hello, everyone. Welcome back. So I will introduce the chair for our next and final session, the Atmosphere and Climate Modeling and Prediction session, Professor Tarek Hussein from Jordan University and the University of Helsinki, and he will introduce our invited speaker. Many thanks, Professor.
Thank you very much. Welcome, everybody, for the last session in this workshop. Our invited speaker is Li Qi from Washington University. He is going to present something very interesting, which is about trends in global and East Mediterranean fine particulate matter air pollution. Welcome, Li. Go ahead, please. I think you are muted, or
okay, now can you hear me and see my screen?
yes, we see your screen and you hear you very well. Go ahead.
All right,
please.
thank you. Thank you. Yeah, it's great pleasure for me to be introduced and to be invited to this talk. And today I'd like to present our recent updated understanding of changes in PM 2.5 air pollution globally, as well as over the Eastern Mediterranean region. So I guess this topic is very well understood by the audience, but I think it's never too much to re-emphasize the strong and pervasive health impacts of fine particulate matter air pollution. Exposure to PM 2.5 is associated with major diseases, as it's the leading health risk factor from environmental causes globally, leading to millions of premature deaths every single year. And averagely about 1 year loss of life expectancy is estimated for every one of us on this earth. And because of this strong health burden, there is estimated to be trillions of US dollars of welfare cost globally every single year. But despite such scientific social significance, the available ground-based measurements is by no means sufficient to characterize global PM 2.5 distribution and evolution. Here we can see this rather recent map where we show the annual mean average of PM 2.5 in 2018 from available measurement sites. And despite the high PM 2.5 heterogeneity, as reflected by these concentration distributions, a lot of populous countries actually do not have any regular research quality PM 2.5 monitoring at all at present. So motivated by this gap of knowledge and understanding, the atmospheric composition analysis group at Washington and Dalhousie University took information from space as an alternative data source. So they made dedicated efforts to develop this long-term and high-resolution PM 2.5 estimates from the growing constellation of satellite retrievals. It starts from the aerosol optical depths and use the coincident sampled PM 2.5 to AOD ratio from the geoschem chemical transport model, which can then be used to derive the so-called geophysical PM 2.5 estimates, which can explain roughly 80% of PM 2.5 variability from ground monitoring globally. And this data set can be further improved by statistical fusion with existing measurements to further compensate spatial biases remained in the geophysical PM 2.5. That brings additional about 10% agreement based on out-of-sample cross-validation technique. And enabled by this accurate data set, recently we come up with this time series of global population weighted PM 2.5 exposure on the left, which represents the average exposure or PM 2.5 pollution we are surrounded by for every one of us on this planet for every year from 1998 to 2019, representing the mean pollution level and its evolution. And we see there is a peaking and a pivot point at around 2011, as indicated by the dotted line. The trends before and after that year are opposite, which can also be reflected by the map of trends on the right, with dominance of warm colors representing positive trends for most countries and territories on the bottom, on the top right, and the dominance of cold colors and the decreases on the bottom. We see if we also divide the world into 13 characteristic regions, and we can also draw the draw the regional time series, and we can see a strong PM2.5 exposure, for example, over the polluted regions of China in red, over South Asia countries in green and brown. And these regions also have strong increases, but also there is a substantial decreases after about 2013 over China. And we definitely know that these regional trends on the right must have contributed related to the global trends on the left. But a quantified understanding of that contribution currently is missing in literature. So based on this knowledge gap, we are motivated to define the so-called normalized PM2.5 exposure. So because the global population weighted PM2.5 is the sum of the production of the PM2.5 exposure in E and the population in P over different regions and locations, we can define the contribution of the each region as this red term, which is essentially the exposure in this region multiplied by the global population share. With this framework of normalized exposure, here is again the time series of the global population weighted PM2.5 exposure, but with the normalized exposure term, we are able to decompose the regional color stacked time series from each region that sums up to match this global time series, which represents their contribution to this global exposure. And more intuitively, we can also now quantify the percentage contribution from each region in each year. And with this regional attribution, we can now identify that, for example, in 1998, China is the biggest contributor to the global exposure of PM2.5 because of its both high pollution as well as strong population contribution to the world. And this 28% contribution increases to a peak in 2006, but then it decreases rapidly to 20%, especially in recent years. At the same time, the contribution of India in dark green has increased steadily from 22 to 31% according to our regional attribution. If we included all of the South Asia, including other countries in brown, the exposure contribution has risen up to about twice of the contribution of China in 2019. This highlights another impressive consequence of the recent unprecedented air pollution mitigation success in China. We can also further quantify the regional contribution, not only to the exposure in each year, but also the changes of the global exposure over time. Here we see these three black bars representing the PM2.5 exposure globally in the starting, in the peaking, and in the ending of our exposure investigation. And we also use these colorful bars to represent the contribution from the normalized exposure from each region into the regional changes. And in this framework, we can now quantify that in the first period, pre-2011, China and India together contribute to about 70% of the increases in this time period. Meanwhile, after that, we can now very intuitively and clearly see that China is the dominant force that drives the global decrease of population exposure to PM2.5. Nonetheless, the slowing growth of several tropical regions and populous regions cannot be ignored. On the top right, we see that if the trend in the first period were persistent into the second period, the global exposure actually needs to be increased by about 6.5 micrograms per meter cube, whereas the reality, there is more than 10.5 micrograms per meter cube decreases relative to this business of usual scenario. And in which we can see that the slowed increases in South Asia and the Middle East and Africa is a significant contributor because of their strong changes in the exposure as well as their large population share of the world. So overall, we have reviewed using this normalized exposure framework that there is a determinant role of China as well as substantial contributions from several tropical regions to a recent reversal of global exposure to PM 2.5. We can further calculate global PM 2.5 attributable deaths each year in this framework. So before 2011, we still see these attributable deaths as these markers increasing continuously. Meanwhile, after 2011, we do not see an immediate reversal of the deaths, but more of a slowed increase or near stagnation of this growth. This death number is calculated for each country and territory, diseases, and age as the product of the population in dark blue, the population fraction in specific age in light blue, the mortality rate of the certain diseases in age in orange, and the so-called attribution fraction from a particular matter pollution in dark red. And only the last term, the red term, is associated with the PM 2.5 health impacts. So if we used a decomposition technique, we can actually attribute these changes of the PM 2.5 attributable deaths into the changes driven by these four factors. And from that, we can now see that especially the dark red term, which represents the contribution solely driven by the PM 2.5 pollution, is increasing first and then decrease. This is consistent with the pollution change. Meanwhile, at the same time, the three other demographic factors, including the increase in population, increase in average age of global population, as well as the improved well-being that actually decreases the deaths, also make significant contributions. And on the bottom right of this figure, we listed accumulated deaths each year relative to 2011 in the next following 2011 years for the causes of the four factors. And we can, from these numbers, conclude that after 2011, the reversal of exposure reduction together with the improved well-being has critically counteracted the population growth and aging factors, which caused this near stagnation of growth in the recent global PM 2.5 attributable mortality. And then based on this long-term data, we can also zoom into the Eastern Mediterranean region. And here is the annual mean PM 2.5 map in 1998 on the left, and the changes over the two periods on the center and right. Overall, we see the Balkans has lower PM 2.5 pollution level relative to the Middle East countries. And also it has a stronger or more pervasive reductions of PM 2.5 relative to the Middle East. Specifically over the Balkans, there is weaker changes before 2010, but reductions are more pronounced and prevailing across the region afterwards, suggesting air pollution mitigation over this region has been recently successful. Meanwhile, over the Middle East countries, there is a substantial increases first, and then it transitioned to slowed down increases or reversal at some locations. And on a population-weighted basis, we can still apply our previously introduced normalized exposure framework to decompose and quantify the overall contribution of each country in the two regions to the regional changes of the average population-weighted PM2.5. For the Balkans, on the top right, we again see there is the mixed positive and negative contributions from each country before 2010, and which is followed by consistent reductions from every country afterwards. The big players of this regional exposure changes are from populous countries of Romania, Bulgaria, Greece, and Sub-Siberia. Meanwhile, over the Middle East on the bottom, the strongest contribution to the sharp increases in the first periods are from Egypt, Iraq, Saudi Arabia, and Iran. Meanwhile, after that, there is overall smaller trends and mixed with increases and decreases from different countries. To understand these two different trajectories in the two regions, we can use the PM2.5 source attribution to interpret this change. Here, we adopt the pie charts from a recent paper from Aaron McDuffie, representing the source sectorial contribution to annual mean PM2.5 exposure in each country in 2017. The numbers in the center are the annual mean exposure of PM2.5 in micrograms per meter cube. These source attributions are based on the state of science understanding of aerosol emissions from bottom-up inventory and the sensitivity zero-out simulations of each sector using the geoscam model again. Now we can clearly identify that for the Balkan countries, mostly on the left, the anthropogenic sources, especially this from the energy, industrial, transportation, and residential sectors in the brown, dark blue, and gray colors, are more dominant in PM2.5 over these regions. Whereas the wind blow dust in yellow clearly appears to be the largest source in the Middle Eastern countries, accounting for over a half of PM2.5 pollution in this region. Therefore, regulation measures which targeted on anthropogenic emissions are more effective over the Balkans, whereas over the Middle East, if there were any existing policies, they can be easily masked by nature dust variabilities. And the reversal of dust over the Middle East at around 2010 have been frequently mentioned in recent literature, such as based on purely on MODIS AOD trends from this study. And transition from drying to wetting, according to soil moisture data in met fields, has been used to partially explain this transition, where this soil moisture are negatively related to dust emission. Furthermore, this decadal dust activity time series in red also was found to positively covary with the North Atlantic sea surface temperature anomaly in black, which possibly unveil a teleconnection of the Middle East dust with the Atlantic climate variability. Broadly speaking, the annual warming of the Atlantic Ocean can cause the local low pressure and upward air motion, which can then be zonally transported into the Middle East and descend to the surface, which would cause extra drying in a warming phase. So in the recent years, there actually has been coding over the Atlantic, which might be related to the drying over the Middle East, as well as the wetting of the Middle East, as well as the reduced dust activity. So this tells us that the global efforts to mitigate climate change might be able to finally reduce the extreme dust emissions, but of course, these effects can only be detected at a much longer climate timescale. In terms of health impacts, here again, we are showing the overall reduction of PM2.5 associated health premature deaths in the Balkans and steady increases of the deaths in the Middle East. And using the decomposition, we can see that besides the changes driven by PM2.5 in dark red, the other three demographic factors all appear to be significant. Population aging in light blue seems the biggest challenge of the mitigation in PM2.5 associated deaths in the Balkans, whereas the population growth is also equivalent important over the Middle East. Another interesting fact is that we found the changes driven solely by PM2.5 is relatively small over the Middle East relative to the other factors. And this is because the pollution levels we see on the previous slide over this region are usually in the above 50 micrograms per meter cube regime. And in these high concentration scenarios, changes in the risk, health risk following changes in PM2.5, as indicated by the slope of this risk curve, are significantly weaker than the risk change in the lower concentration regimes. So even currently, the benefits of reducing PM2.5 over Middle East seems to be small. These benefits of further mitigation will become more and more significant once the air becomes cleaner. So overall, based on more than 2 decades of PM2.5 estimates enabled by spaceborne remote sensing, we identified a substantial decadal reversal of global population-weighted PM2.5 exposure, which is attributable to dominantly to the dedicated PM2.5 health mitigation success in China. It is crucial to sustain this and continue these trends by global efforts, which has not completely overturned, as we noticed, the growth of PM2.5 attributable deaths. And finally, over the Eastern Mediterranean region, PM2.5 mitigation has recently become successful in a sustained manner over the Balkans, whereas the climate-driven dust activity and emissions seems the major challenge of reducing PM2.5 in the Middle East. With that, I'll thank you all for your attention and welcome any question. Thank you.
Thank you very much, Lee, for the constructive presentation. Do we have any questions?
Is it in the chat or verbally?
There is one in the questions section. In PWPM 2.5 pie chart, is secondary PM considered?
Oh yeah, so these pie charts are generated based on geoscam simulations, which includes both the primary emissions as well as secondary aerosols in accordance to our current understanding. So I guess the primary question arises from this surprising high fraction of dust, but in our model configuration, dust is indeed contributing significantly to PM2.5 over dust source regions. And yes, secondary aerosols are considered.
Yeah, okay. That's good. Thank you, Lee, but we are running out of time. We have to move to the next presentations.
Thank you.
But thanks again.
Should I stop sharing?
Yes, please.
I actually don't know how to do that. Sorry.
Yeah, but our next presentation is about an estimation of the anthropogenic aerosols effective radiative forcing based on 7 Earth system models presented by Alkiviadis. Please go ahead, Alkiviadis. And remember, we have 7 minutes for presentation. Thank you.
Okay, I hope you can hear me and you can see my screen.
Yes, perfectly.
Okay, thank you. Hello, everyone. My name is Alkiviadis Kalisoras. I'm a PhD student in the Department of Meteorology and Climatology of Aristotle University of Thessaloniki, Greece. And I will present you our work on the effective radiative forcing of anthropogenic aerosols based on 7 CMIP6 Earth system models. A few introductory slides. Aerosols are a suspension of liquid or solid particles that remain for some time in the atmosphere with a range of sizes from a few nanometers to a few micrometers. They can be either emitted directly or can be formed within the atmosphere. and can influence the energy and radiative balance of the atmosphere through absorption and scattering of solar and terrestrial radiation. Aerosols can modify the Earth's radiative budget through direct and indirect processes. The absorption and scattering of solar radiation as well as terrestrial radiation, we usually call these processes aerosol radiation interactions, while the indirect effect is the modification of cloud properties, as aerosols can act as cloud condensation nuclei and ice nuclei. These processes are called aerosol cloud interactions. And a few info about the effective radiating forcing is basically a metric that quantifies the energy that is either lost or gained by the Earth system due to an imposed perturbation. In our case, this perturbation is anthropogenic aerosols. It is typically expressed in watts per square meter and is a metric of how human activities change the energy flow within the climate system. We use 7 Earth system models that participated in the coupled model comparison project phase 6. We used 2 sets of experiments, as you can see here. And we used simulations that were carried out from the aforementioned CMIP6 Earth system models. Those simulations used fixed sea surface temperatures and sea ice cover that corresponded to the year 1850, or used historical prescribed sea surface temperatures. In this table, the first and the last experiment are the control experiments, while the rest of them are the perturbation experiments. And as you can see, we either have all aerosol precursors set to the year 2014, or specific aerosol subtypes set to 2014 emission rates. In order to estimate the effective radiative forcing, we use the method developed by Gunn in 2013. We split the effective radiating forcing in 3 components: ERF ARI due to aerosol radiation interactions, ERF AKI, which is due to aerosol and cloud interactions, and ERF albedo, which is mainly a residual term, but we call it albedo because it's largely due to the contribution of surface albedo changes caused by anthropogenic aerosols. These equations may seem confusing, but we use the radiative fluxes that either ignored the scattering and absorption of radiation by aerosols, or neglected the scattering and absorption of radiation by both aerosols and clouds. Here are main results. As you can see in subplots A and E, the ERF total is pronouncedly negative over South Asia, East Asia, Europe, and North America. And if you can see in subplots C and G, this is mainly due to aerosol and cloud interactions. In fact, the global means are very close to each other. It's minus 1.11 watts per square meter and minus 1.28 watts per square meter for the historical experiments. And here we see the contributions of anthropogenic aerosols by subtypes. In the first row, we see the contributions from sulfates. We see that the spatial pattern at the top of the atmosphere is almost similar, almost identical to the one we saw earlier due to all anthropogenic aerosols. Whereas, as we can see in the third row, black carbon induces positive radiating forcing, especially over South Asia and East Asia, and mainly due to aerosol and radiation interactions, as you can see in subplot J.
1 minute.
left.
We also studied the time evolution of ERF by region. We see globally that there is a negative peak around 1980, and if you can see in West and Central Europe, the Mediterranean and East North America, we have the same peak around 1980, and then a shift towards more positive values. Whereas in South Asia and East Asia, we see a continuously growing ERF towards more negative values. And our conclusions from our study is that scattering aerosols exert a negative top of the atmosphere radiative forcing, whereas aerosols that strongly absorb solar radiation, such as black carbon, have a positive radiative forcing at the top of the atmosphere. Globally, there is a negative radiative forcing due to all anthropogenic aerosols as a whole, and certain industrialized regions of the northern hemisphere show a negative peak around 1980, and then more positive values, whereas over South Asia and East Asia, we have a continuously growing more negative ERF trend. That's all. Thank you.
Thank you very much. Do we have any questions in the chat? It seems no. I have only one short question. You don't need to answer in a long way. How did you combine the 7 models together?
We created the multi-model ensemble. We performed a bilinear interpolation in order to change the native grid to a common grid for all models. And then it's basically the ensemble mean, the mean value of the 7 models.
Okay.
For each grid point.
Yes, so all the numbers you presented are the mean value. Thank you.
Yeah.
Thank you very much. I think we are ready to move to the next presentation by Eva. And it's also about modeling high-resolution paleoclimate simulations with the COSMO CLM model in the Eastern Mediterranean and Middle East. Please go ahead.
Hi, can you hear me and see my screen?
Yes.
Okay, great. Hi everyone, my name is Eva Hartmann. I am a PhD student of Elena Soplaki in the Justus Liebig University in Gießen in Germany. And yeah, we are doing high resolution paleoclimate simulations, meaning the last 2,500 years with the COSMO CLM model, which is a regional climate model in the Eastern Mediterranean and the Middle East. Yeah, now I'll first start with the motivation, some methods, my results, and then the summary. Yeah, what motivates us is that the Eastern Mediterranean and Middle East is in the last 2,000 and 2,500 years really a hotspot of plenty long, high quality instrumental records, documentary information, and natural proxies, which are collected here in this area. You can see it, how many there are available. And yeah, also it is influenced by several centers of action. So it has also a very complex morphology. We can see lengthy interaction and large volcanic eruptions also in this period of the last 2,500 years. as well as some major social historical events, which we want to combine with climate. And therefore, we use the Cosmos CLM, which is a regional climate model. And this is really unique because most of the time, only global climate simulations are used for the past. So this is something new to use also the regional climate model, and we want to increase the resolution. And with the help of the increased resolution, then we can better compare the simulation results with the proxies I've just shown. And to make it better usable in the regional for the past, we had to do some implementations in the regional climate models. So we introduced the forcings, which are the volcanic forcing, the solar forcing, the orbital, and the greenhouse gas forcing, which we used the same as in our forcing global climate model, and which are also used in the CMIP6 and PMIP4 simulations for the historical run. So we used the exact same forcings and implemented them in our regional climate model. And additionally, we used the land use change from the global simulation to have the leaf area index and the plant coverage that is more realistic in the past periods. And then, when we modified our model, then we did some simulations. Here are some details about our settings. So our climate model is forced by the MPI ESM, which has also the CMIP6, PMIP4 settings. And for the external data, which is for example, land use data, we use also the output of the MPI model, and then do the simulation on a 0.44 degrees resolution. And then we had a little bit larger domain, but now I want to focus really on this Eastern Mediterranean and Middle East. And at the moment we're doing a transient simulation from 500 BCE to in future 1850, but now we are in 1500. And now I want to focus in this region, and I also separated it again into 4 subregions, which are the Mediterranean, the Western Central Asia, the Sahara, and the Arabian Peninsula. And here you can also see the resolution of our simulation and how the altitude is here in our simulation. So it is not 100% realistic, of course, because mountains are much higher, but compared to the global climate simulation, it is much more realistic. And now some results. I want to focus now on the 6th century of the Common Era, because this is really a special century, because we had some 2 major volcanic eruptions that were in 536 and 540. So they were really close to each other. So the climate conditions, they were really strongly impacted by those eruptions. So as you can see in those years after the 2 eruptions, the temperature decreased by almost 2.5 degrees Celsius, which, sorry?
About 1 minute is left.
Okay.
Please go ahead.
And so and this is the mean over the whole area. And in precipitation, we can't say much for the mean of the whole area. But now we are going more into detail and look at the seasons and also the four subregions. So as you can see now, so we have two realization, meaning we did the whole simulations, but let it run from doing it like an ensemble. So we have two realizations, and you can see in both that the temperature, especially in winter, is lower in those years. And maybe for the precipitation, it can be highlighted that especially in the spring season, in the Sahara and Arabian Peninsula, the precipitation really decreased a lot in the years after the eruptions. So what can be said is that we had a cooling between 536 and 550 after the two successive major volcanic eruptions, and with the highest negative temperature anomalies in winter and in most seasons in the regions Mediterranean and Western Central Asia, and the highest negative precipitation anomalies in spring in the Sahara and Arabian Peninsula. And yeah, that's it. Thank you very much for your attention. And yeah, if you have further comments and questions, you can always contact me.
Thank you, Eva. I think there are no questions in the chat.
Okay.
And yeah, we can go ahead in the next presentation. Thank you.
Thank you.
So our next presentation is entitled A Statistical Approach to Estimate Future Burnt Area and Greenhouse Gases Emissions from Mediterranean Wildfires, presented by Tim from the National Observatory of Athens.
Thank you.
Yes, Tim.
Can you hear me? Can you hear me?
Perfect.
Okay. Can you see my screen correctly or not?
Yes.
Okay. So, sorry, it's moving. So I'm going to talk about a statistical approach to estimate future burnt area and greenhouse gas emissions from Mediterranean wildfires. And these are some of the results from a Mediterranean 3 project, which we've participated in. My name is Tim van der Sliek, and you can see here the other names who were involved in this study from the Klimadapt research group. I'm sorry, my screen is just blocked completely. Okay, sorry, can you see my screen now?
Yes.
Yes, we can see it.
Okay, I will go to the next slide. All right, so why are we doing the study? First of all, climate change will increase the wildfire burnt area and greenhouse gas emissions, but by how much? So we want a method to assess and compare future changes across the Mediterranean basin, because at the minute this is difficult because different studies use different methods. So we had a need for a uniform, relatively rapid method to assess the impact of future climate change on burnt area and greenhouse gas emissions associated with the Mediterranean wildfires, because climate is not only increasing the frequency and the magnitude of wildfires, but of course, if the wildfires increase, it increases the greenhouse gas emissions as well, and it is affecting the climate system itself if you look at a large enough scale. So this study is especially was made to support national climate change mitigation and adaptations policies and strategies. So our methodology wanted to use publicly available data and to be applicable throughout the Mediterranean. So our assumption is we use this study, but we assume non-significant changes in all other external factors, such as land use, vegetation, fire suppression, fire prevention, and human activities. So we looked at 3 pilot study areas. One is the Chania province, the western part of Crete. The other is the National Regional Park of Luberon in the south of France, which has about the same surface area as Chania. And the third area is Montenegro, where we had to take the entire area of Montenegro because of data limitations, data availability. In yellow, you can see the percentage of annually burned area. And in green is the average greenhouse gas annual emission from wildfires for the respective areas. And you see that there are quite large differences, which basically reflect differences in firefighting, differences in prevention, but also differences in climate and especially fuel conditions for Montenegro. I should point out that Chania and Luberon have similar vegetation, but Montenegro is covered in forest with very old trees, so there's a lot more fuel. As data sources, we used meteorological data from the ERA 5 Landsat dataset. We had access to low-resolution burnt area data from the Global Wildfire Information System for Montenegro, and we had high-resolution burnt area data for Chania province and for the Luberon National Park. And greenhouse gas emission data from past wildfires were downloaded also from the Global Wildfire Information System. So first of all, we calculated the correlation coefficients between the monthly burnt area and multiple variables over the various season. So the months June, July, August, and September over 21-year period to establish the best matches. And we found that the optimum variables, the best variables for all the target areas were similar, and they constitute the fire weather index, a fire danger index, the maximum average temperatures, and the drought index, the SPEI 6. We found also that there is no significant correlation between climate indices of the remaining months and the burnt area. For this study, we assumed that the percentage of burnt area over the fire season and the other months is stable also in the future. And we should point out that more than 95% of the area that is burned by wildfires is burned over the fire season. So then we used generalized additive models to model the response variable, total burned area, from selected independent variables for each of the study areas. The statistical model was optimized using leave one out cross-validation and then tested against the observational data. And finally, the relationship between burnt area and the greenhouse gas emissions of the respective target study areas was assessed using reduced major axis regression. And then we used 3 state-of-the-art climate models, which were developed within the EuroCordex initiative to feed the statistical models to estimate future burnt area and greenhouse gas emissions from wildfires for the pilot study areas. And future burnt area was calculated under 3 future climate change scenarios up to 2070. So the RCP scenarios 2.6, 4.5, and 8.5 were used.
Yeah, Tim, about 1 minute is left.
Okay, so a summary of the results in one table. Future changes for Chania, Luberon, and Montenegro. We see that the burnt area increases for all the areas and the greenhouse gas emissions increase as well, but least for the Chania area and most for Luberon and Montenegro. So Chania has high emissions from wildfires, but limited future increases. The Luberon areas has low emissions that will double, but will still be the lowest of the study areas. And Montenegro has very high emissions and large absolute future increases. And these results are in line with publications indicating that climate change has stronger impacts on wildfires in the North Mediterranean and in the mountainous areas. So as we're finishing off, I don't need to read out these conclusions. I will just finish here. We've summarized all the results in detail on the webpage, and you can download the various documents there if you're interested. Thank you for your attention.
Thank you very much, Tim. I will check if we have any quick questions in the chat. No, we don't. And we can move on to the last presentation in this session, which is presented by Pak Fung, who is known as Alan from our group. He is going to talk about estimating black carbon concentration in the Eastern Mediterranean region using a generalized proxy, which was developed using the data from Europe, different cities in Europe. So, Alan, you have 7 minutes. Go ahead.
Yeah, thank you for the introduction. Can you hear me and see my screen?
Yes.
Okay, good. Thank you for the introduction. I'm Alan. I'm from the University of Helsinki, currently a postdoc researcher. So thank you for having me as the last presenter of the day. And on behalf of my collaborators, I would like to introduce you a study recently done to estimate black carbon concentration, focusing on the EMME region. So I will first of all talk about the motivation, methods, and then results, focusing on the 2 case studies in the EMME regions, and then I will give my conclusion. So black carbon has recently gained quite a lot of attention because of its climate change impact and also the health impact. Although the WHO addressed the measurements of black carbon, it doesn't really give the guidelines for the air quality of black carbon. That's why a lot of countries, they do not really take black carbon as a regulatory measuring parameter. So we have a lack of data for black carbon due to this reason, and also even though in the countries with black carbon data, there might be some technical errors and instruments and maintenance. So there, from time to time, there are some missing data. So this study is to create models as a virtual sensor as a solution to improve spatial and temporal resolution of black carbon measurements. And but however, we know that not every stations measure the same input variables. Some measure more, and then another measure probably only 1 or 2, or some just meteorological condition. So how can we really make use of these statistical models to extend it to everywhere in the world? So this is kind of the knowledge gap that I would like to address. So the method for this study is that we have 3 stages. The first stage is to train the data with a long enough data set in Barcelona. It's an urban background site. And then second stage, we have validate and test the model in 4 locations, actually, in 4 sites in 2 locations, in Germany and in Finland. These sites have some sort of black carbon measurements so that we can validate. And in the last stage, we test in 2 cities in the EMME region with no black carbon measurements currently. So we just want to see how these generalized models can work there. So we are adopting a model called an input adaptive proxy. So the main feature of this model is that it can select the input variables selectively. It uses a robust ordinary least square model with penalties of outliers, and it takes maximum 3 input variables. Because it can automatically remove the combination, take in the input variables, so it could also remove the combinations of high interlinearity within the model, and it can reject some of the models with non-normality distribution of residues. And for this purpose, we use a standardized procedure, 80-20 training testing speed, and also a 5-fold a 5-fold cross validation. And the input variables that we use for this purpose is NOx, ozone, PM10, PN, and some modes of particle number concentration, meteorological conditions, etc. So some results is that we found that in all the 5 locations, black carbon correlates quite well with accumulation mode and also NO2. And it in all the locations, you can see the correlation is quite similar to each other. So it has it can kind of demonstrate that it's possible to create these kind of generalized model. And for the testing validation process in Helsinki and in Germany, we found that the R-square are quite high, over 0.8, and the calculated black carbon also lies along the 1-to-1 line. So it seems that the models work quite well in these 2 places. So the next stage is to bring this model to the 2 locations without any black carbon measurements. So for first one is the Nicosia in Cyprus. So this bottom left subplot is the diurnal cycle of the calculated black carbon. It seems that they follow quite well diurnal cycle, but it's strongly dominated by the input variables, for example, NOx and PM10. They have very similar diurnal cycle. For ozone, it has totally different diurnal cycle. So it seems that ozone doesn't influence the estimation of black carbon that much. So this is one case study, very briefly. And then the second one in Jordan, also on the bottom right corner, we can see the black carbon diurnal pattern. It has quite similar diurnal cycle as accumulation mode. And we also have some meteorological condition in that site, and it seems that it doesn't really work that well. Yeah, something that I forget to mention is that these 2 colors, one is during work days and one is during weekends. So so they seems to have quite similar diurnal cycle from the estimation. But of course, one of the limitations is that because we don't have black carbon measurements in these 2 sites for validation, so we don't really know how well these black carbon estimation works. So it also comes to my take-home messages that so we trained the black carbon model using Barcelona data, and it works well in Germany and Finland at 4 locations. And this generalized model also estimates black carbon in EMME regions as a virtual sensors. I would say is with a reasonable diurnal cycle pattern, but we also don't know how well it is. So the outlook of the study is to carry out some measurements to evaluate this input adaptive proxy, so that it's like because it's like a virtual sensor. So of course, for the first time when you use a sensor, you have to do calibration. So I can take this as a calibration step for future use. So yeah, this is my our study, and thank you. If you have any questions, you can contact me, and then yeah.
Okay, thank you very much, Alan. Is there any question? I can see, how do you determine what is the 3 input factors in cities without black carbon measurements?
Yeah, I didn't. These are the 3 examples that I show in the diurnal cycle, but I just put all the variables that I can get from that locations, because that input adaptive proxy can select the best input variables itself. So I didn't choose them by myself. I just get all the open source input variables to put in the model, and then the model selects for me.
Okay.
Thank you for the question, by the way.
Thank you very much. So we come to the end of this session, and I step down this so for the organizers to make the closing. Thank you very much all.
Thank you, everyone. I don't know if Charbel would like to say something before we close the session as the chair of the organizing committee. Rahis, floor to you.
Thank you, Eleni. So I would like to thank everybody, the presenters, the people that attended, and also the organizing committee. So Atina, Eleni, and Marina for the work, all the work and all the efforts, and the scientific committee again. So thank you all. Don't forget that. So we will have another. We will meet again. So in the fourth workshop next year, and we will be also we will have the recording also online if you would like to again check some of the presentations that were really good and really interesting. So thank you everybody for staying here this whole day with us, and see you soon. Thank you.
Thank you, Charbel. Goodbye, everyone.
Thank you. Bye-bye.
Bye, everyone.